In this session, we're going to talk about evaluation in Spark, and in particular, reasons why Spark is very unlike Scala collections. So, as I've already pointed out in previous sessions, there's this laziness, eagerness thing going on between transformations and actions. We covered some simple examples which showed how evaluation was different in Spark. These differences can compound and lead to inefficient programs. So it's very important to understand completely how your Spark programs are being evaluated, because there are many situations where you want to avoid unnecessary evaluation in Spark. So in this session, we're going to look at exactly how evaluation works and some common scenarios that you should think about when writing Spark programs. So let's first start with a little bit of a digression. So why is Spark good for data science? In order to answer that question, let's start by recapping some major themes from previous sessions. So in the last session, we learned about the difference between transformations and actions, in particular that transformations are deferred or lazy, and actions are eager. They kick off stage transformations. So we learned that last session, and a few sessions earlier, we learned that latency is important. It makes a big difference in the experience of the actual data analyst using Spark, and that if we can shift things in memory as much as possible, we can significantly lower these latencies and save a lot of time and improve the experience of the analyst analyzing data. This analyst can get more work done, basically, with lower latencies. There are these 2 points that we've learned in previous sessions, and somehow they're going to come together into an answer about why Spark is good for data science. Can you see why? Is it clear yet? I'll give you a quick hint. Most data science problems, when you think about them, they involve some kind of iteration. So how do transformations, actions, and in-memory computation, how are these things somehow important to data science problems that involve iteration? Well, first, let's look at iteration in Hadoop. So here's a graphical illustration trying to show what an iterative program would look like, a program with, at least 3 iterations, probably more. In this example, what we have is some kind of input, perhaps some data in HDFS. And then we have iterations that are implemented as little MapReduce programs, and we iterate by running these individual MapReduce programs many, many times. So at each iteration, we probably have a map and a reduce step. And between iterations, we want to write the data that we computed, and then we want to read it again for the next iteration. So we know that there's probably reading and writing going on in each of these iterations. And there's also reading and writing going on between these iterations. So we have to read and write this intermediate data each time we want to end or start a new iteration. So one thing that might jump out at you, if you recall the latency lecture, is that a lot of time is spent then in I/O, disk I/O, or even network I/O. One figure has attributed around 90% of this time being spent in I/O operations, which Spark can avoid. So if you want to do iteration in Spark, it can be much more performant because all of this reading and writing to disk can be completely avoided in Spark. We have to, of course, read in data from HDFS, but once things are in memory, we can just iterate on it in memory. We can run the same sort of MapReduce steps or filter or whatever steps many times again and again and again for however many iterations that we want, and it's all sitting in memory. It can still be recovered if there is a failure, and there's a lot of reading and writing and things that just don't have to happen because we don't need to persist things to disk all the time. So to begin to answer this question about why Spark is good for data science applications and why transformations and actions and in-memory computations are important, we can start to see here that it's better for iterative programs to be done in memory because they'll be faster. But what does it have to do with transformations and actions? To understand why transformations or actions have to be carefully thought about in this situation, let's look at a quick example. So let's look at logistic regression, which is kind of the hello world of big data iterative algorithms. Logistic regression is a popular iterative algorithm that's typically used for classification tasks. So assuming you have 2 different classes of data, blue and red, and what we want to do is we want to come up with a classifier, a way to separate out these 2 different classes of data. So the classifier would be basically this line. We would move it around on this space here, until it separates these two classes of data, and then if we ever get new data, we assume that it follows the same trends as the red and the blue, and hopefully it should work for any new data that's added, right? That's the idea of a classifier. So just visually, to get an idea of what we're doing here, on one iteration, we move the line a little bit. On another iteration, we move the line a little bit. We keep doing this. And like I said, we're iterating through all of the data every time. We're doing some math with all of the data. And then eventually, we find a good separating line here, and the algorithm stops. What we're focused on is less the details of logistic regression, but we're really focused on the shape of the computation, the fact that we pass through all of the data on many iterations to come up with a new estimate for this line separating the two sets of data. That's the shape of the computation that we're going to be looking at. And this is how we're going to update those weights that represent the position of that line that separates the two classes of data, right? So as you can see here, there's a number of iterations that we're going to do, and we're going to iterate through this XY data set. And there's some function g, which doesn't need to be shown here, but it's part of the logistic regression algorithm. So this algorithm can be implemented in a very straightforward way in Spark. And here it is. So just to step through it, what we have here is first we have an RDD points, and this is read in from some text file somewhere. And then this text file is parsed, so we have a map function that goes through all of the lines of this text file. Remember, text file gives you an RDD full of strings, so we have to convert all of these strings into most likely doubles here. We have a vector of weights, so these W's here, which we initialize as 0. And then for some number of iterations that we determine elsewhere, we go through the entire data set several times. So here we go through all of the points, and then we apply this g function here, okay? And then we reduce, and now we update the vector of weights here, using what we have just computed, using this gradient that we just computed. Okay? Okay, cool. So now we understand the basic shape of this algorithm. It's pretty concise, isn't it? Essentially, we iterate on applying a map and a reduce. For some number of times, on a certain RDD, we apply map and then reduce. So we do this perhaps 30 times. And you update some local vector with the results every single time you go through this entire data set. Okay, so that's the general shape of this algorithm, but what's really happening here? Remember on the first slide, we were talking about trying to keep computations in memory and having to think about what are transformations and what are actions. So what's really going on here? I'll give you a second to think about it, and then we'll talk about it on the next slide. Well, the short answer is that we're doing a lot of work that we don't have to do. Remember, transformations like map get reevaluated every time an action is used. So we do have one map here, which gets reevaluated when we call this reduce here, but we also have a map here. That means we're applying this map function again and again and again when we don't have to. So points is being reevaluated on every iteration. If we have 30 iterations, we're reevaluating points 30 times. That's completely unnecessary. We shouldn't have to do that. That's a lot of extra work that we don't want to be doing right now. It would be much better if what we could do is create this points RDD, leave it sitting in memory because we know that's faster, and then reuse it on every iteration. Instead, what we're doing is we're recomputing it on every iteration, which is surely very expensive. So we see here a major consequence of these lazy semantics of these transformation operations. By default, RDDs are recomputed each time you run an action on them. That's something you can't forget about. And of course, as we just saw, especially in the case of an iterative algorithm, this can be very expensive in time if you need to use the data set again and again. But what's nice about Spark is that it gives you a way to control what data you have cached sitting in memory available to reuse again. And in order to instruct Spark, hey, I'm actually going to use this again, don't recompute it 1,000 times, you can use a method persist or a method cache. What these methods do is after an RDD is evaluated, it keeps them in memory so you can reuse them again. So here's a quick example of a situation where you might want to use this cached function or this persist function. So recall this example where we have an RDD full of strings that represent a year's worth of logs. And let's just say we want to go through all of these logs and we want to filter out the ones that are actually errors, right? And we know we're going to have to use this a few times. So here we have an action take. And in this case, so far, if we didn't use persist, this would be okay. What we would be doing is we would be evaluating it once at the point which we call take 10, and that would be it. We wouldn't need to evaluate filter a bunch of times because we only really use it once. However, if I add a line of code here, here's another action, so I have now take and count. It's beneficial now to persist this logs with error RDD, because if we don't persist this, if this is not cached in memory, then what happens is I do this filter on last year's logs twice. I do it when I compute take 10, and I do it when I compute count. So what we can do is, if we do persist, that means that this logs with errors, this RDD sits in memory, and it can be reused. So it can be, we just use that again without having to recompute this filter for the take 10, and then we again reuse the same RDD that's sitting in memory to compute this count without having to go through that filter again. So if we go back to this logistic regression example that we just saw, we can add persist to this points method here, and what that'll do is that'll prevent us from having to evaluate it on every iteration. Now we just evaluate it once, and then we reuse that data set that's sitting in memory each time we do this map and this reduce on this points data set to compute this gradient on each iteration. So here we can save a lot of effort and not have to continually recompute this RDD by caching it in memory the first time we use it. Okay, to delve just a little bit deeper into caching and persistence in Spark, it's possible to persist your data set in many different ways. For example, as just regular Java objects sitting in memory. So just as your program normally runs, nothing special, just keep your data in memory. You can also persist it to disk as regular Java objects. You can persist in memory as serialized Java objects, so that is converting these objects in memory to byte arrays or arrays of bytes, which is much more compact, but it takes some effort serializing and deserializing. So it saves memory, but it costs a little bit of compute time. Same thing, put these on disk, or a mixture of keeping data in memory and on disk. And in particular, in this case, rather than reevaluating many transformations a bunch of times, anything that needs to spill over to disk, in case you don't have enough memory, everything that you can keep in memory, you keep in memory, but if you don't have enough memory, then we persist the thing that you tried to cache to disk. That's actually very different from this here. If you run out of memory, in this case, you don't have enough memory between all of your nodes to hold the data set in memory. What happens is a least recently used policy for evacuating things out of memory. So let's say you have an RDD. Let's say you've done 20 transformations on this, and it takes a long time to go through all of them, right? If you don't have enough memory to hold that resulting data set, if you call persist on it, and you've chosen this mode here, what happens is Spark only holds as much as it can in memory, and anything else that it can't hold in memory, it throws it out. If ever those pieces of data need to be reused, then it will reevaluate them. It will go through all of those many transformations that are required to reevaluate the missing pieces of data it doesn't have. So in this case, this right here could be very useful in a situation where it takes a lot of work to get to whatever thing you try to persist, and then can persist at least the thing that you've already computed. So just to give some context, there's many different ways you can configure actually how persistence works in your Spark job. And the two methods that you use are cache or persist. Cache is the shorthand for the default storage level. So the storage level is what we use to configure these things. But you can just write cache with some parentheses behind it. And that will be the default storage level, which is memory only for regular Java objects. That's this one here. And persist is another method that you can pass different arguments to, representing one of these so-called storage levels in order to customize how the persistence works. So this is the method you use if you want to change the default behavior. And just to show you a quick chart of the different storage levels that are available, these are the things that you pass to that persist method, and here's just a chart kind of showing the pros and cons of different storage levels. So for example, memory only uses a lot of space, but it's pretty fast because you don't have to do any extra processing on this data. It's always in memory, never on disk. Whereas some of these other ones, like memory and disk serialized and whatnot, again, they have different trade-offs, right? So when you keep things serialized, it costs a bunch of time to serialize and deserialize it, CPU time. But of course, it uses very little space in memory. So you can put more data in memory, but of course, you're going to have to serialize and deserialize each individual element of that data set if you want to ever access it. So there are different trade-offs. These is for you to decide depending on the job that you're doing. But just be aware that there are a lot of choices. But in general, throughout this course, we're always really just going to use the default. So we're going to use this memory-only storage level, which you can get by just calling cache or persist without arguments. So a key takeaway of this session is to remember that despite how similar Spark looks to Scala collections, this deferred semantics of the RDDs that you're using have a very different behavior compared to Scala collections. So the need to use this cache function to prevent things from being evaluated multiple times, for example, this is completely unlike Scala collections, even though the same interface is available to you. And you've got to remember this because this could be the difference between you waiting a really long time for a job to complete or a job being finished in a few seconds. Just to reiterate, due to the lazy semantics of these RDD transformation operators, and due to many users' sort of implicit reflex to assume sort of the eager semantics of regular Scala collections, one of the most common issues that newcomers have when they start using Spark is this issue where people are unknowingly reevaluating several transformations. So you're just kind of doing the same computations again and again and again without realizing that you're doing these many computations again and again and again. And you could save all that effort by doing caching. And of course, this is something important to point out when you do your programming assignments. This is something that students mistakenly do all the time. And as a result, during the programming assignments, lots of students have a tendency to run out of memory and to not know why. This is a big hint. This is probably going to be the main reason why you might be running out of memory in your programming assignments. So just before we conclude, I want to remind you that actually this laziness is really useful. Because after the last slide, you must be like, oh my gosh, I have no idea what's happening under the hood. How do I know if things are being reevaluated all the time? I have to look much more closely than I thought at my Spark programs, which might seem like a bad thing off the top of your head, but I will remind you again, via two examples real quick, why laziness is a good thing. So we saw this example actually in the last session. Just to remind you, let's assume we have an RDD full of strings, which represent a year's worth of logs, and then we do a filter on it to filter out the logs that have errors, and then we just take the first 10 out of those, right? So why is laziness useful here? It's because because filter is delayed until take is applied, that gives Spark the opportunity to inspect this chain of operations that are sort of queued up before being executed. And it lets Spark figure out how to do important optimizations. So, for example, in this case, what Spark can do is it can say, so I only need to find 10 results that match this predicate here from the filter because I'm only going to take 10 of those. So rather than having to go through the entire data set, Spark can intelligently just say, okay, once I've got 10 items that match this predicate here, I'm just going to quit and save a whole bunch of time and not have to iterate through the whole data set just not to use it, right? So Spark can do important optimizations like these. So another important optimization that Spark can do is fusing transformations together. So just like before, Spark now has the opportunity to make an optimization before the count is actually executed. And in this case, what Spark can do is it can stage these computations and then fuse them together, so it has to do less work. So in this case, because map usually requires that you do one entire traversal through a dataset, and filter also requires you to do one entire traversal through a dataset, Spark can say, hey, look, I've got 2 traversals that I've got to do. Maybe I should only traverse this dataset once rather than many times, and I can compute the result of both the map and the filter in a single pass before returning the count. So what Spark can do here is it can basically optimize this, and instead of pass through the dataset many times like would be the case for eager collections like Scala's regular collections, in Scala's regular collections we would be passing through the dataset many times, Spark can very intelligently say, I don't have to do that, I can do less work. So laziness, remember, it's a very good thing. You just got to remember that you have to think about it when you are writing programs. You can't just write code and imagine that everything is eager. You have to remember that transformations are lazy. In this session, we're going to try and bridge the gap between data parallelism in the shared memory case, which is what we learned in the parallel programming course, and distributed data parallelism. So taking that idea of data parallelism and extending that to the situation where you no longer have data on just one node anymore, and now you have data spread across several independent nodes. As usual, let's get started by trying to develop a little bit of intuition first. Let's try to visualize these differences between shared memory and distributed data parallelism. So let's start with the shared memory case. So if I had to draw a picture of data parallelism, what does it look like? Since we're talking about the shared memory case, we assume just one node, one computer. That means we have some data set on one computer, and we'd like to exploit the ability of the computer's multiple processors to try and compute this data more quickly by doing it in parallel, by breaking up the work and trying to do many things at once. So let's assume that our data is in a collection, Scala parallel collection. So this jar is going to be a collection of jelly beans, let's just say. And our collection of jelly beans is called jar. It doesn't matter if we're doing this in parallel collections or sequential collections, we generally have the same API available to us. We can say, okay, I have this collection jar, and I can do a map on that collection. So I want to do the same operations, all of the jelly beans in the jar. So for each jelly bean in the collection, I'm going to do something to it. I don't know, whatever it is. Maybe I change the color. Now, in the shared memory case, we can have this API, but under the hood, what parallel collections will do, if we use parallel collections in Scala, is it will somehow split up the data, so there's some way to make chunks of the data, and then to have some kind of task or worker or some kind of thread abstraction, something that does processing on these individual data shards in parallel. So typically you have many of these. And then whenever that work is done, we start combining the result into a complete result again, if necessary, right? So visually, we can chunk up our data set into several pieces. And so we have something like a worker or a thread doing individual work on individual pieces of that data all in parallel at the same time. So again, this is the shared memory case. We have all of this data sitting in memory, and then different pieces of that data are being worked on by different individual processes, whatever our process is realized as. Okay, so that's the visual picture of the shared memory case. What's important to note is that this can all live underneath a collections abstraction. So, for example, we can take exactly the same abstraction that we already use in the case of regular collections. So, for all you know, because I've left out the types here, this jar could be a list or it could be a par array. You don't know. It has the same API. It looks exactly the same as a regular Scala collection or a parallel collection. So, the point here is that we can have underneath the hood this data parallelism automatically happening for us, and we can reuse the same already very familiar and comfortable API that people already use. So key takeaway here is that this collections abstraction fits over this data parallel model very well. And we can extend this to the distributed case as well. So what would the same data parallel execution look like in the distributed case, sort of under the cover, independent of the abstraction? So in the case of distributed data parallelism, as we saw in the shared memory data parallelism, we split up the data on the same machine. In the distributed case, we split the data over several nodes. Okay, that's the difference. We split it up over several nodes. In the shared memory case, workers or threads independently operate on the data shards in parallel. In the distributed case, nodes operate on the shards in parallel. So it's not workers or threads, it's independent nodes, independent machines working on the data in parallel. Okay. So this very high-level description of data parallelism in the distributed case is very similar to the shared memory case. The only difference really is that we're splitting things over several nodes, and the nodes are the things that do the work instead of individual threads. So what does this look like? We can go back to the example of having some kind of collection. Once again, let's have a collection of jelly beans. In this case, what we've done is we've got individual nodes, right? Individual compute nodes, and each one has a piece of the data set as an independent collection on each independent node. But one thing that we didn't have to deal with in the parallel programming course, the prerequisite to this course, when we were learning about data parallelism in the shared memory case, was the network, was the latency involved with these nodes having to share data or to communicate with one another in some way. The latency imposed by needing to do this was never a worry when we were learning about shared memory data parallelism. So this is a big fundamental difference now that we'll see in later lectures is actually going to impact the programming model. Latency is something that we will never be able to forget about. However, just like in parallel collections, we can still keep the same familiar collections abstraction over our distributed data parallel execution. So just like before, we can have code that looks just like this. And in this case, a jar can be one of these distributed collections in Spark, and yet we have this wonderful collections API that looks just like Scala collections over top of this distributed data parallel execution. So this model in general fits very, very nicely underneath this collections abstraction is sort of the key takeaway here. So just to summarize the differences between shared memory and distributed data parallelism, in the shared memory case, you have this data parallel programming model, this collections programming model, and underneath the hood, the way that it's actually executed is that the data is partitioned in memory and then operated upon in parallel by independent threads or using like a thread pool or something like that. Yet in the distributed case, we have the same collections abstraction or data parallel programming model on top of this distributed execution, but now instead we have data partition between machines, the network in between, which is important, and just like in the shared memory case, we still operate on that data in parallel. So what does this mean? It means that a lot of what we learned in the previous course, in the shared memory data parallelism part of that course, can actually be applied to the distributed counterparts. For example, non-associative reduction operations. So just to remind you what that is, if you had a parallel collection and you did reduce on it, and you subtracted the elements in your reduction operation, that's a non-associative operation. And in parallel collections, that will give you a non-deterministic result. Spark is exactly the same way. When you do these things in parallel and they're non-associative, when you have a non-associative reduction, the same exact thing happens. You can have non-deterministic results. So the same things that we learned, the same sort of key takeaways that we got from the shared memory data parallelism part of the parallel programming course, we can apply a lot of that to the distributed data parallelism in Spark. However, the one thing that we have to really think about carefully when we're using Spark's programming model is to think about latency, and we'll see that more in subsequent lectures. So as you know, the implementation of this distributed data parallel programming model is Apache Spark. Apache Spark has an abstraction called resilient distributed datasets. We call them RDDs for short, and an RDD is basically the distributed counterpart of a parallel collection. So throughout the course, we're going to be focusing a lot on these RDDs, how they work, and how to get the best performance out of them. So this is the last sort of high-level illustration that I'm going to give you about sort of how to think about Spark and how it works. So let's assume that we have a very large data set. Let's assume that, for example, we have the English Wikipedia, which we've reduced so we don't have all of the possible data per article. We have just the titles and the text of those articles, and it's just the English part of Wikipedia. And already that reduced data set is pretty big. We can't fit that into the memory of one machine unless you have, really a special machine. But most normal people's laptops can't fit this into memory. So we know we have to split it up over a couple of nodes. So assuming that we have a data set like this, what Spark will do is it will chunk up this data set somehow via some partitioning mechanism, and then it will distribute this partitioned data set over a cluster of nodes. And what you get back from Spark is a reference to this distributed dataset, to this entire distributed dataset. So now you have a very large collection that's spread over, in this example, let's say 8 machines, and you have one name to refer to all of that distributed data with. And now I can think of it as if it's a single collection, because to me, it's going to look like a single collections abstraction, like a single list or something, right? So I can now refer to this thing called wiki, and in fact, I'm referring to the distributed data that's distributed all over these, for example, 8 machines here, okay? And I can then just use this collections abstraction that we're already very comfortable with. I can, so this thing, we've named it wiki, and now I can just do a map on this wiki, and for every single article, I can just the text, I can get the text, and I can convert the text to all lowercase, so getting rid of any uppercase characters in the Wikipedia text, for example. So this is just a high-level picture of how we're going to be interacting with this distributed data. And as you can see, it's going to look very familiar. It's going to look just like collections that you're already very comfortable with, except that it's going to be distributed over many nodes. So, before we get into how to use Spark, how to get good performance out of Spark, and how to express some basic analytics jobs in Spark's programming model, let's first look at some of the key ideas behind Spark in an effort to get a bit of intuition about why Spark is causing such a shift in the world of data science and analytics. As we'll see in this session, Spark stands out in how it deals with latency, which is a fundamental concern when a system becomes distributed. So, earlier in the sequence of Scala courses, in the parallel programming course, we learned about data parallelism in the single machine, multi-core, multi-processor world. So we thought about how to parallelize something in this data parallel paradigm in the shared memory scenario, so one machine. And we saw parallel collections as an example of an implementation of this paradigm. Today, what we're going to do is we're going to extend what we've learned from the parallel programming course when we were focused on shared memory. We're going to extend that to the distributed setting. And as a real-life implementation of this paradigm, we're going to get into Apache Spark, which is a framework for big data processing that sits in the Hadoop ecosystem. So we've started with shared memory, one machine, and now we're shifting to many machines. And many machines working together to complete a data parallel job. However, when we switch into this distributed paradigm, suddenly there are a lot more things that could go wrong that were not even a concern in the shared memory case. The list is actually much longer than these 2 points here. However, these 2 points are really the most important points to keep in mind when you're thinking about Spark and, in general, other frameworks for distributed computing. In particular, Spark handles these 2 issues particularly well. So one issue is partial failure, the situation where you might have one or a few machines, involved in a large computation, for some reason failing. Maybe an exception gets thrown. Maybe the network between a master node and that worker node goes down. Something happens where suddenly one machine no longer is available or is no longer able to contribute its piece of the work. This is something that wasn't really an issue in the case of shared memory. Another issue is latency. There's this general observation that sometimes certain operations will have a much higher latency than other operations. So in particular, network communication, we'll see, is very expensive, which is something that is a reality in order to do any sort of distributed job. You cannot get rid of the need to communicate between nodes when you're doing a distributed computation. So just to summarize, latency is a really big concern that pops up that can really affect the speed at which a job is done, and partial failure can really affect whether or not a job can even be completed. What happens if a machine goes down and we have no way of recovering what that machine was working on? So Spark handles these 2 issues particularly well. And the big takeaway that I hope you get from this lecture and some of the others in the series is that fundamental concerns to distribution, like latency, they cannot be masked completely. They cannot be forgotten about. You can't pretend that this doesn't exist. You cannot pretend that the network is not involved in the computation that you have to do. You always have to think about it. And in fact, things like latency actually bubble up into the programming model. Perhaps it's not immediately obvious, but we'll see over the course of several lectures that dealing with latency actually gets into the code that you're writing. You're actually reasoning a little bit about whether or not you're going to cause network communication. So this is one very important thing to remember. When you do a distributed job, you always have to remember that you're going to cause some kind of network communication. And because it's often expensive, you typically want to reduce the amount of network communication that you cause. Okay, so let's back up some of these loose arguments that I'm making. I'm saying, okay, there's a spectrum, and sometimes in-memory computations are cheaper, computations that involve the network are expensive, and perhaps writing things to disk and reading things from disk can also be expensive, and as a programmer, you should be aware of when you're doing some of these things. So there's a famous chart called Important Latency Numbers that every programmer should know. These numbers were originally compiled by Jeff Dean and Peter Norvig at Google, and also later extended by Professor Joe Hellerstein and Professor Eric Meyer. And the idea here is to actually show the relative amount of time that different sorts of operations cost. And okay, so what do we have here? We have a bunch of numbers. Lots of zeros. Okay, I can see that this is cheaper and this is more expensive. So this is half of a nanosecond, this is 1 million nanoseconds, 150 million nanoseconds. We can see that there are some pretty big orders of magnitude differences between some of these operations. Okay, that's fine. Okay, so let's zoom in on two of these numbers here. So this is reading 1 megabyte sequentially from memory. There's a typo on the slides. And this is reading 1 megabyte sequentially from disk. Now, if we look at the numbers here, if we focus on the nanoseconds, we can see that there's around approximately a 100x difference between reading 1 megabyte sequentially from memory and reading 1 megabyte sequentially from disk. That's a pretty big difference. Likewise, if we look at the cost of referencing something that exists in main memory and sending a packet all the way from a data center in the US to a data center in Europe and then back to the data center in the US, there's likewise a very big difference here too. So again, if we focus on the nanoseconds, we can see that there's a 1 million times difference in the amount of time that it takes to reference something that's in memory or to do a round trip sending a piece of data over the network and back. That means that it is 1 million times slower to send a packet round trip over a long distance than it is to simply reference something that already exists in main memory. That's a huge difference. Okay, so let's try to make a little more sense of these numbers. So we can see that they're going from smallest to largest, and there's kind of a little bit of a trend here where we can organize things into groups. So the stuff that's blue refers to things that tend to happen in memory. They involve no disk, they involve no network. This as well. The things that are orange, they tend to involve disk. And finally, the things that are purple involve network. So in this case, we're sending 2 kilobytes of data one way over a local area network. In this case, we're doing a round trip in the same data center in the same network. And in this case, we're doing another round trip over a very long distance. Things that involve network in purple. Okay, so this is perhaps getting to be a little bit confusing with all of the arrows, but what we see is a general trend. Memory operations tend to be faster. Disk operations tend to be pretty slow, but not horribly slow. And any operation involving the network tends to be the slowest. Okay, so we have this general feeling that doing things in memory is fast, doing things on disk is kind of slow, and doing stuff that involves a lot of network communication is really slow. And we have some numbers. We can see that this versus this is 1 million times this is a million times slower than that. And this here, reading 1 megabyte sequentially from memory, this is 100 times, reading 1 megabyte sequentially from disk is 100 times slower than reading it from main memory. So we have these numbers, 100 times slower, 1 million times slower, but these are orders of magnitude, and it's really difficult to wrap your mind around the cost of these things when it's just some orders of magnitude. So let's try to humanize these numbers. Let's try to get a better intuition between really the meanings of these order of magnitude differences between these latency numbers. So to do that, let's multiply all of these numbers that we just saw by 1 billion. So now suddenly, instead of nanoseconds, we're dealing with seconds. So we can then map each of these latency numbers to human activity. So we just kind of shift this into our realm of understanding, our realm of times that we operate on, and then look at how expensive some of these things are relative to our lives. So let's have a look at some of these latency numbers mapped to some kind of human activity. And I should note that these come from GitHub just posted by Joe Hellerstein. So you can find these online on GitHub if you search for humanized latency numbers. So let's look at some of these numbers. So we can start to group things into categories, things that take seconds to a minute, things that take hours, things that take days, so on and so forth. So if we start at the top of our list, and we have our nanoseconds now mapped to seconds, we have L1 cache reference. If it's equivalent to half a second of time, that's about 1 human heartbeat. Okay, so we have some feeling now for how fast referencing something in your L1 cache is. And in the L2 cache, it's about 7 seconds comparatively, so kind of the equivalent of a long yawn. Locking and unlocking things in memory, about 25 seconds, which is about the amount of time it takes to make a push-button coffee. Okay, so if we keep moving down our list, referencing main memory is equivalent to about 100 seconds, which, depending on the person, is how long it takes to brush your teeth. Okay, so now we're starting to get into some of the first networking numbers. Sending 2 kilobytes of data one way over a 1 gigabit network, that's about 5.5 hours. Whoa, so that's a big difference already. So on a local area network, a one-way send is equivalent to about 5.5 hours relative to our half-second L1 cache reference. That's huge. So the difference goes from 1 heartbeat to the amount of time that it takes for you to go to lunch and then leave your job at the end of the day. That's a pretty big difference. And so let's continue. A random read on an SSD, 1.7 days, about the duration of a normal weekend. This is getting crazy, isn't it? So we go back now to reading 1 megabyte sequentially from data. That's about 2.9 days, even longer. That's like a weekend plus a holiday. Round trip within the same data center, 5.8 days. That's kind of a 1 week vacation. Reading 1 megabyte sequentially from SSD, 11.6 days. That's almost 2 weeks. That's an enormous difference compared to an L1 cache reference. Again, half a second to 11.6 days. And as programmers, we have a tendency to kind of just intermix these things without really having a good appreciation of these order of magnitude differences. We don't really have a good feeling for how different these things are. So we can keep on going. Reading 1 megabyte sequentially from disk is 7.8 months. That's almost as long as it takes to have a human pregnancy start and a baby be born. So the difference between referencing L1 cache and reading 1 megabyte sequentially from disk is enormous. And finally, sending this example of a long distance round trip send and receive, 4.8 years. That's about the time it takes for a bachelor's degree student in the US to complete a bachelor's degree. There's an enormous difference then between referencing L1 cache and doing a round trip overseas. Okay, so let's try to pluck some of these numbers and look at them a little bit differently. We can put them again into these categories: memory, disk, and network. And we can really start to appreciate the differences between these things. So here you have durations on the order of seconds to minutes, worst case days. But in this case, in the disk case, you have operations that take on the order of weeks or months. And in the network case, you have operations that take a week to years. So a round trip on the same local area network is 5.8 days. So this is why locality is important in distributed systems. You want to have two servers next to each other if they have to do some sort of network communication. You don't want one server to be on the other side of the planet, because the difference here is between days and years. In any case, if you have to make some request to some service that you don't know where it is, maybe it's on the other side of the planet, this could cost relative to an L1 cache reference taking half a second, 4.8 years. These differences are enormous once they're humanized. Okay, now that we've seen this table of latency numbers that every programmer should know, in particular the humanized version of this table, we should now have some intuition about how expensive network communication disk operations really are relative to doing things in memory. So now that we have this intuition, now that we have this feeling of indeed how expensive these things are, one might ask, well, okay, great, but how do these numbers about latency relate to big data processing or big data analytics? So to try and understand how these latency numbers matter in big data processing, let's have a look at the big system that everybody used before Spark appeared on the horizon. Let's have a look at Hadoop. So you may have heard of Hadoop before. Hadoop is a widely used large-scale batch processing framework. It's an open source implementation of a system that Google introduced, or that Google uses in-house, called MapReduce. MapReduce was a big deal in the early 2000s when Google began developing it and using it internally, because it provided a really simple API, these simple map and reduce steps, so these kind of functionally oriented map steps, and then these functionally oriented reduce steps where you kind of combine data. And this was very easy for programmers to wrap their minds around over large clusters of many machines. If all you had to do was think in terms of map and reduce, and then suddenly you're controlling a lot of machines, but using these two operations, that's a really simple way to do these large-scale distributed operations. But really, the big thing that it offered, in addition to this API that lots of people could wrap their mind around easily, was fault tolerance. And fault tolerance is really what made it possible for Hadoop/MapReduce to scale to such large configurations of nodes. So that meant that you could do processing on data whose size was completely unbounded. Things that could never, in anybody's wildest dreams, be done in weeks worth of time on one computer could be easily done on a network of hundreds or thousands of computers in the matter of minutes or hours. So fault tolerance is what made that possible. Without fault tolerance, it would be impossible to do jobs on hundreds or thousands of nodes. And the reason why fault tolerance is so important in distributed systems or in large-scale data processing is because these machines, weren't particularly reliable or fancy, and the likelihood of at least one of those nodes failing or having some network issue or something was extremely high midway through a job. What Hadoop/MapReduce gave programmers was the ability to ensure that you could really actually do computations on unthinkably large data sets, and that that they'll succeed to completion somehow. Because even if a few nodes fail, the system can somehow find a way to recompute that data that was lost. So these two things, this simple API and this ability to recover from failure so you could then scale your job to really large clusters, this made it possible for a normal Google software engineer to craft complex pipelines of MapReduce stages on really, really big data sets. So basically, everybody in the company was able to do these really large-scale computations and to find all kinds of cool insights in these really large data sets. Okay, so that all sounds really great. Why don't we just use Hadoop? Why bother with Spark then? Well, if we jump back to the latency numbers that we just saw, fault tolerance in Hadoop/MapReduce comes at a cost. Between each map and reduce step, in order to recover from potential failures, Hadoop will shuffle its data over the network and write intermediate data to disk. So it's doing a lot of network and disk operations. Remember, we just saw that reading and writing to disk is actually 100 times slower, not 1,000. That was a typo. It's actually 100 times slower than in memory. And network communication was up to 1,000,000 times slower than doing computations in memory if you can. So that's a big difference. So remember these latency numbers that we just saw. If we know that Hadoop MapReduce is doing a bunch of operations on disk and over the network, these things have to be expensive. Is there a better way? Is there some way to do more of this in memory? Spark manages to keep fault tolerance, but it does so while taking a different strategy to try and reduce this latency. So in particular, what's really cool about Spark is that it uses ideas from functional programming to deal with this problem of latency, to try and get rid of writing to disk a lot and doing a lot of network communication. what Spark tries to do is it tries to keep all of its data, or all of the data that's needed for a computation, or as much of it as possible, in memory. And it's always immutable. Data is always immutable. If I can keep immutable data in memory, and I use these nice functional transformations like we learned in Scala collections, like doing a map on a list and get another list back, if we do these sorts of things, we can build up chains of transformations on this immutable functional data. So we can get fault tolerance by just keeping track of the functional transformations that we make on this functional data. And in order to figure out how to recompute a piece of data on a node that might have crashed, or to restart that work that was supposed to be done on that node somewhere else, all we have to do is remember the transformations that were done to this immutable data, read that data in somewhere else or on the same node, and then replay those functional transformations over the original data set. So this is how Spark managed to figure out a way to achieve fault tolerance without having to regularly write intermediate results to disk. So everything stays in memory, and only when there's a failure is a bunch of network communication or reading and writing operations actually done. As a result, Spark has been shown to be up to 100 times more performant than Hadoop for the same jobs. And at the same time, Spark has even gotten more expressive APIs. So you're not limited anymore to only map and reduce operations. Now you have basically the entire API that was available to you on Scala collections. This is also very cool. So you have something that's very fast, still fault tolerant, and on the other hand, you have even more expressive APIs available to you than you did in Hadoop. This is great. So to go back to this image that we drew, we've put things into categories: memory, disk, network, right? Network is weeks and years, disk is weeks and months, and memory is seconds and days. And what we have is this pattern. Ultimately, Hadoop sits here. So many of Hadoop's operations involve disk and network operations, right? So Hadoop is doing a lot of this stuff. Whereas Spark is here. Spark is doing its best to try and shift many of its operations in this direction. More things being done in memory, less things being done on disk and over the network. As we'll see, it'll come out in the APIs that we're going to learn, but Spark does its best to aggressively minimize any network traffic that it might have to undertake. So we have this. We have Spark favoring in-memory computations and operations, aggressively minimizing network operations as much as it can, and Hadoop still doing a lot of its work involving the disk, and perhaps a little less aggressive about minimizing network communication. So just looking at these words, within months, and much Hadoop operates kind of on this side. Then we look at Spark here. We have more operations sitting on this side and fewer hopefully in the network box. We have this trend. It's been shown on numerous occasions that Spark is significantly faster than Hadoop. So Hadoop, it takes 100 seconds per iteration, 110 seconds to be exact, per iteration for this logistic regression application, and Spark only takes 0.9 seconds. So in this case, it's about 100 times faster than this equivalent program in Hadoop. That's a big deal. And just to show a few more numbers related to the same application, logistic regression, what we see is that the first iteration that Spark does is kind of expensive. It takes 80 seconds for the first iteration, but then the next iterations are 1 second. I hope this gives you some intuition about why Spark's different approach to handling latency is so important to, in the end, developer productivity. This enables developers to have a much tighter feedback loop where they can experiment with the same amount of data, but only in few seconds to a few minutes they can have a result, tune their algorithm, and then try again. Whereas if they were to use Hadoop for the same algorithm, it would take them minutes to hours to see any sort of results, tune it, and go back. Quantitatively, it's a lot of time that developers are saving by this clever approach to dealing with latency, and it's all built up on functional ideas, which is pretty neat. So intuitively, day to day, these differences in performance, it has real impacts on developer productivity. If you try to complete an equivalent job both in Hadoop and Spark, the same job in Hadoop, you could start the job, go get lunch, then get some coffee with your colleagues, pick up your kids from school when you get home, SSH back into your work computer and see that the job just completed. Whereas Spark, you can start your job, go grab some coffee while your Spark job is running, and then by the time you're back at your computer, the job is finished. This means people are more productive, and you can get many more iterations done in one working day than you can a solution built on top of Hadoop MapReduce. So Spark delivers real productivity improvements to the analyst, to the developer. And these benefits haven't gone unnoticed. You can check Google's trends. You can compare search queries for Apache Spark versus Apache Hadoop. And as you can see, since about 2013, early 2014, Spark has really experienced a massive uptick in interest, so much so that it's eclipsed search queries for Apache Hadoop. These benefits to developer productivity are driving the popularity of Spark, and especially relative to Hadoop. People really see a benefit in this framework. In this session, we're going to focus on resilient distributed datasets, or RDDs for short. RDDs are Spark's distributed collections abstraction, and they're really at the core of Spark. In this session, we're going to learn the basics of RDDs, and we're going to learn a little bit about the APIs that are available, and we're going to consider some of the basic differences between the RDD API and APIs that you may be more familiar with in collections. So off the bat, RDDs seem a lot like immutable, sequential, or parallel collections. So think about, for example, a list. Lists in Scala are immutable collections, and we often use them with higher-order functions like map, flat map, or filter. Just like lists, RDDs have a similar API full of lots of higher-order functions like map, flat map, filter, reduce. This is a simplified definition of the RDD class. Of course, there are many more methods, and it's much more complex than this, but this is a simplification of the RDD class as defined in the Spark codebase. And as you can see, these signatures all look very familiar. They look just like the signatures that we've seen on lists for things like filter, flat map, and map. And it's important to note that RDDs really make heavy use of higher-order functions. So just as a reminder, higher-order functions are operations like map, flat map, filter. They're methods or functions that take as an argument another function. So just to look at some more methods on both RDDs and lists, also other parallel and sequential collections, map, flat map, filter, reduce, fold, aggregate, all of these things exist as well on RDDs. So we have really some of the core APIs still available to us that we're already used to in sequential collections on RDDs. They even have mostly the same signatures, macroscopically, of course. So in the case of RDDs, of course, the return type is going to be an RDD rather than a list if we compare the signatures of map, flat map, and filter. Otherwise, everything is basically the same. In the case of map, both RDDs and lists take a function from A to B and apply this to all of the elements in the collection. The same is true for flat map and filter. When we look at these reduction operations, same thing. We have effectively the same signatures. The only difference is aggregate. As you can see here, in the case of Scala's sequential and parallel collection, aggregate its 0 as a by name parameter, whereas in Spark it's not. Do you have any idea why this might be? I'll give you a hint, but I'd like you to think about it on your own and perhaps discuss it in the forums. Remember distribution. Remember that we're going to send things to another computer. So think a little bit about whether or not a by name parameter is the best idea versus something that is not by name when it comes to having to distribute code. So I hope by just looking at some of these basic APIs, you'll agree that using RDDs in Spark, it looks a lot like, a normal Scala sequential or parallel collection. The only difference is that you know that your data is distributed amongst several machines. So assuming we don't know anything else about RDDs, and we only know Scala's collections API, let's try to solve a simple problem with Scala's collections API and see if it works for RDDs. So let's assume we have an RDD full of encyclopedia articles. Each encyclopedia article, each string represents the text of one article, for example. And let's just say we want to search this RDD full of these articles or these article pages, and we'd like to count the number of times that EPFL, the university that the Scala programming language is developed at, let's say we want to count the number of times that the pages mention EPFL. What would we do? How would one write this code knowing that we have something called encyclopedia and we want to search for mentions of EPFL and then sum up the mentions of EPFL? Well, it looks very much like regular Scala collections. This is all you need to do. So assuming that each page is a string, and all I got to do is do page.contains my substring, so in this case EPFL, all I got to do is do encyclopedia.filter, and I have this very simple predicate, and then I can just count the number of pages that have EPFL in the text. That's it. It looks exactly the same as how you would do it on a list. Let's look at another example. So word count is the hello world of programming with large-scale data. How would we do word count in Spark? Hint, looks a lot like Scala collections. So let's assume we have an RDD. This is an example of one way you can create an RDD. We'll talk more about how to create RDDs later. But let's say I've created an RDD called RDD, and now I want to count all of the words in this RDD. The signature isn't written here, but let's assume that this RDD has type RDD string. And let's assume that each string represents a line of text in a text file. So what do? If we had a regular Scala list, we could use flatmap to take each individual line and then split each individual line into individual words. Now you have a collection of individual words, and then we flatten that back down all to one collection. So the result of this here is, again, an RDD of string. But this one represents now words. So it represents an RDD of all of the words in this base RDD that contains lines of a text file. Next, what we can do is we can map every single word in the RDD to a pair of word and the number 1. So we have something that we can now sum up and count. So then, next step would be to use a reduce operation. So reduce by key is a little bit special for Spark. We'll look a little bit more into depth about exactly the differences later. However, what we're doing here now is we're just summing up the ones in the pairs. That's it. Now we have a count of all of the words in this text file. What's important to note is that we've done word count in only 3 lines of code. Another reason why people tend to favor Spark over Hadoop is that this program can be done in so few lines of code so clearly, whereas if one had to write this program in Hadoop, it would take many more lines of code of lots of boilerplate. So people find Spark also much more concise than Hadoop. So the last thing we're going to discuss in this lecture is the different ways that one can create an RDD. So how might you create an RDD? There are 2 main ways that we can create RDDs, either by transforming an existing RDD or from something called the Spark context, or in later versions of Spark, it's being renamed to Spark session. But we have this thing called a Spark context or a Spark session. It's an object, and you can populate a brand new RDD with it. Either you populate a brand new RDD with this Spark context or Spark session, or you can get an RDD from an existing RDD. So in the case of transforming an existing RDD, it's just like when you call a high-order function like map on a list. You get a new list back. In the same exact way, when you call a map, for example, on an RDD, you get back a new RDD. So you can get an RDD as a result of doing a transformation on another RDD, just like you can with lists. Now, the other way is to use this Spark context or Spark session object, as I mentioned earlier. This is important to remember, because you're going to see this in your assignments later. Remember what this Spark context or the Spark session object is, because this thing might have a weird name, but this is the handle to the Spark cluster. This is how you talk to Spark. You talk to Spark always through this thing called the Spark context. So whenever you want to start a new Spark job, you got to create a Spark context first. You got to pass some parameters to it to configure your Spark job. And then you got to start creating RDDs using this Spark context. Now, this Spark context does a lot of the smart work surrounding distribution. figures out lots of things that you don't want to ever have to worry about. Most important to remember that this is your handle to your Spark cluster. And the two methods that are the most important to remember that we're going to see in all of the subsequent slides and in the assignments are parallelize and text file. Parallelize creates an RDD out of a regular Scala collection. You're not really going to come across this in real code bases where you're doing really big jobs, because the assumption is that you've already got the collection in memory in a Scala collection, like in a list or something else, and now you just want to create an RDD. Most of the time, when you're using large data sets, you're going to be using this text file method, which basically can read a text file, usually from HDFS, Hadoop's file system, or a local file system like a regular text file, and then return an RDD of strings. So after you get this RDD of strings back, then you need to figure out how to transform it into something else. If you don't want it to be strings, maybe you want it to be integers or something like this. But the text file will return an RDD that you can then do all kinds of subsequent transformations and analyses with. In the next session, we're going to delve a little bit deeper into RDDs and some of the most important operations that exist on RDDs, transformations and actions. In this session, we're going to focus on transformations and actions. Transformations and actions are the different kinds of operations on RDDs. To understand transformations and actions in Spark, first recall transformations and accessors from Scala's sequential and parallel collections. If you don't remember what these terms mean, I will briefly remind you. Transformers are operations that return new collections as a result, so not a single value. If you, for example, call a method on a list and you get back another list, typically this is a transformer. So in this case, if we call a map on list, we get back another list. An accessor is a method that returns a single value as a result and not a collection. So examples of accessors are things like reduce, fold, or aggregate. So just to remind you what reduce does, it goes through and according to some kind of function you give it, it combines all of the elements together and it will give you the single combined result back. This is an accessor. Now where we had transformers and accessors in regular Scala collections, we have in Spark transformations instead of transformers and actions instead of accessors. So the definition of a transformation, very similar to a transformer, is an operation that returns not a collection, but an RDD as a result. And likewise, an action is something that computes a result based on an RDD, and it returns or saves that result to an external storage system, but it doesn't return an RDD. It returns something like a value or something that's not like an RDD. But this is the most important thing. If you remember anything from this lecture, you need to remember that transformations are lazy and actions are eager. Okay, this is extremely important to remember. This is an enormous difference from Scala collections. So while you might have a method with a very similar signature, like map, similar to the signature of map on Scala's lists, the fact that it's lazy and not eager is an enormous semantic difference that you need to keep in mind when you are writing Spark programs. And the reason why this is so important is because this is the way that Spark deals with the network. The fact that transformation operations are lazy and actions are eager lets us aggressively reduce the amount of network communication that's required to undertake Spark jobs. So if you recall, in an earlier session, we were talking about how important latency was, and I mentioned at some point that this is going to sneak out into the programming model. This is how it gets into the programming model. Okay, so let's make that more concrete by looking at an example. So let's assume that we have a large list, and you remember we're going to use this parallelize method. So I didn't define it here, but SC is a Spark context. We'll see later more concretely how to create an instance of these, but typically you always create a Spark context once in your program, and then you keep reusing it. You create RDDs from it. And in this case, we can use that parallelize method we learned in the last session to transform this large list of strings into an RDD now of strings. So now this has type RDD of string. And so now that we have an RDD of string, we can do a map on it. We can go to each element and call length on each individual element. Then we'll get back an RDD now of lengths. So now the type of lengths RDD will be an RDD of integers. Okay, cool. So what's happened on the cluster now at this point? Well, the answer is nothing. Because remember, a map is a transformation method. It's deferred. Nothing happens. All we get back is a reference to an RDD that doesn't yet exist. So how do we ensure that this computation is done on the cluster? What do? Well, to kick off the computation and to wait for its result to be completed and returned, we can add an action. So in this case, we get the total number of characters in the entire RDD of strings. And we can do that using this reduce operation, which we saw on an earlier slide is an action. Reduce returns not another RDD, but a single value like an integer, for example. In this case, we're going to get back an integer. So this is important to remember. This is probably one of the most common problems that people have when they're just learning Spark. They erroneously assume that after a map or a filter operation has been done, that their computation has started or been completed. When in reality, nothing happens on the cluster. Nothing happens until invoking some kind of action to return a result. So this is going to be very important for you to remember in your first programming assignment. So just to give you a flavor of some of the more commonly used transformations that you'll see in Spark programs. So there are the usual suspects here. Map, which again, note that it's a transformation because of its return type. In all of these cases, an RDD is being returned. So these are transformations because the return type is an RDD. Which means these things are lazy, right? I'm just going to remind you again. Lazy operations. So map, we already know pretty well. Apply a function to each element in the RDD and then return another RDD of the result of all of these applications per element. Flat map, same idea, but flatten the result. So return an RDD of the contents of the iterators returned. In the case of filter, we use this predicate function, and we return an RDD of elements that have passed this predicate condition. In this case, it's a function from some type to a Boolean. Right? And finally, distinct. This is also another rather common operation, and basically this is kind of like distinct on a set operation. So it will remove duplicated elements and return a new RDD without duplicates. Now that we've seen a few common transformations that you're going to stumble across in your assignments and in the wild, let's look at common actions that you might find in the wild. And again, I'm going to remind you with big letters that these are eager. These are how you kick off staged up computations. So some of the most commonly used operations are collect. So collect is very popular because it's a way, after you've reduced your data structure down, let's say you did a bunch of filter operations and you've gone from some RDD that was 50 gigabytes and now perhaps you've only got a handful of elements in it. This is how you get the result back. After you've reduced the size of your data set, you can use collect to get back the subset or the smaller data set that you filtered down. So you get all elements out of the RDD, but typically you use collect after you've done a few transformations. You know your data set's going to be smaller, and then you do collect to get all of those results collected on one machine. The next operator which we've used so far actually is count. So the idea behind count is very similar to the idea behind counts in collections API. Just return the number of elements in the RDD. Take is another very important action. Okay, it's an action because we go from an RDD to an array. So you maybe have a very large RDD of 50 gigabytes worth of elements, and you say, okay, take 100. And you get back then an array of those 100 elements of type T. So you basically are converting what was once in an RDD into an array. That's the same with collect. I didn't mention that the return type of collect is an array of T because you're taking things out of an RDD and you're putting it into an array on one machine instead of spread out on many machines in an RDD. Finally, we have reduce and for each. Reduce, I think we know pretty well, combine all of the elements in the RDD together using this operation function, and then return the result. So the return type of this is A instead of an RDD. That's how we know it's an action. And finally, for each, because for each returns type unit. So this applies this function to each element in the RDD, but since it's not returning an RDD, it's an action. So again, How do you determine whether something is an action or a transformation? You look at the return type. If it's not an RDD, it's an action, which means it's eager. Never forget this. Let's look at another example. So let's assume we have an RDD of type string. So doesn't matter where it came from, we have this RDD of type string now, which contains gigabytes and gigabytes of collected logs over the previous year. And each element of this RDD represents one line of logging. Okay, so this is a very realistic scenario which you might want to use Spark for. Perhaps you have many devices or machines constantly logging to some persistent storage somewhere like S3. Okay, and now you want to analyze maybe how many errors you have in the last month. So assuming that, we have these dates in a typical year, month, day, hour, minute, second format, and errors, when there is an error, the errors are logged with a prefix that includes the word error in it. How would we determine the number of errors that were logged in the month of December 2016? Easy. We can start by calling filter, and on each line in the log, we can check to see if the string 2016-12 exists, and if so, only pass this predicate if also this is satisfied. So if error exists also in that line of text, so if you have both 2016-12 and error in that line of text, then filter it down into a new RDD with just these elements. So of course nothing happens at that point. This is just a staged up computation. And again, by staged, I mean it's a computation that we know we're going to eventually do, but we haven't started it yet. And you could imagine that we could stage up many more computations as well. We could do another filter on this. We could do a map on it. We could convert everything in the logs to uppercase. We can do many more transformations that don't actually get executed yet. We can just stage them up. We can queue them up. Okay? And finally, in this case, we'll call count, and that actually gives the order to Spark to send this function over the network to all of the little individual machines to do their computations, and then to add them up and then send back the result, the count call, and to aggregate it, combine it all up so that you have one integer or one long with the number of errors in the logs. I bring up this example because it illustrates why laziness is useful. So even though this is very simple, it still illustrates something that is really useful about doing this in a way where transformations are lazy and actions are eager. By staging up computations in this way, we can optimize them. So Spark can be very smart and decide when it can stop doing work to save time. So in a very similar example, it's basically the same example where we have an RDD of strings, we do a filter, contains error, and then we do an action, in this case take 10. You could imagine that it's exactly the same code as here. What's really happening is that the execution of filter is being deferred until this take function is applied. And this means Spark can be very smart. Spark can stop filtering elements once we've gotten 10 of these. So Spark does not have to first go through everything, make a new RDD all over the place, all over the whole network, with all of the instances of error. It can just stop when we've gotten to 10. So this is beneficial because it saves time and work, and it can do smart things, like not computing intermediate RDDs. This is why it's advantageous that transformations are lazy, because then we can do all kinds of optimizations on them. Finally, I just want to run through a few other kinds of transformations that you might encounter in this course. There are a special group of transformations that combine two RDDs. These are typically set-like operations, like union or intersection. So if I have an RDD1 and an RDD2, I can create the union of those two RDDs by saying val RDD3 equals RDD1 union RDD2. In this case, RDD3 will be a new RDD containing the elements from both RDD1 and RDD2. So these are regular set-like operations. And the same goes for intersection, so you can do the same thing with two different RDDs, or you can return a new RDD containing the elements only found in both RDDs. Subtract is also quite useful. It's the same idea, but you can subtract the elements out of another RDD. This is kind of like when you're using a vector editing program and you can like subtract shapes from one another, right? And then finally there's the Cartesian product with other RDDs. And again, you know that these things are transformations because the return type is always an RDD. So it's lazy. Finally, there are a handful of actions that you're going to come across. These are actions that don't exist in Scala collections. Surely there are some things that are different between Scala collections and Spark. These are operations which are useful when dealing with distributed data or very large data sets. So just to repeat, we know that these are actions because the return type is not an RDD, which means that they're eager. Okay, so operations like take sample, if you want to sample down or decrease the size of your data set, take sample will give you a random sample of a certain number of elements that you want, but it returns an array to you. So you take a very large data set, you sample different pieces of it, and then collect the subsampled data set to one array on one machine rather than have it be distributed in RDDs. Likewise, there's another operation called take ordered. So you can, in this case, do a take, but have them be ordered. So you can return the first n elements of an RDD using either their natural order or a custom comparator. So that's this implicit ordering parameter here. And finally, there are two different kinds of save as functions. So this is, of course, very important when you're doing distributed jobs. So these are side effecting operations. You can call save as text file on an RDD. It's an action. You had queued up many transformations, and then now you say, okay, save as a text file. It causes all of these transformations to be computed, and then this thing to be written to file at this path. This lets you write to a file either in the local file system or on HDFS, and save as sequence file is very similar. So you can save the elements of your data set as a Hadoop sequence file in the local file system or HDFS. So again, these are actions, and these are things that are very practically useful and that you might come across in this course or in Spark code bases elsewhere. In this session, we're going to talk about evaluation in Spark, and in particular, reasons why Spark is very unlike Scala collections. So, as I've already pointed out in previous sessions, there's this laziness, eagerness thing going on between transformations and actions. We covered some simple examples which showed how evaluation was different in Spark. These differences can compound and lead to inefficient programs. So it's very important to understand completely how your Spark programs are being evaluated, because there are many situations where you want to avoid unnecessary evaluation in Spark. So in this session, we're going to look at exactly how evaluation works and some common scenarios that you should think about when writing Spark programs. So let's first start with a little bit of a digression. So why is Spark good for data science? In order to answer that question, let's start by recapping some major themes from previous sessions. So in the last session, we learned about the difference between transformations and actions, in particular that transformations are deferred or lazy, and actions are eager. They kick off stage transformations. So we learned that last session, and a few sessions earlier, we learned that latency is important. It makes a big difference in the experience of the actual data analyst using Spark, and that if we can shift things in memory as much as possible, we can significantly lower these latencies and save a lot of time and improve the experience of the analyst analyzing data. This analyst can get more work done, basically, with lower latencies. There are these 2 points that we've learned in previous sessions, and somehow they're going to come together into an answer about why Spark is good for data science. Can you see why? Is it clear yet? I'll give you a quick hint. Most data science problems, when you think about them, they involve some kind of iteration. So how do transformations, actions, and in-memory computation, how are these things somehow important to data science problems that involve iteration? Well, first, let's look at iteration and Hadoop. So here's a graphical illustration trying to show what an iterative program would look like, a program with, at least 3 iterations, probably more. In this example, what we have is some kind of input, perhaps some data in HDFS. And then we have iterations that are implemented as little MapReduce programs, and we iterate by running these individual MapReduce programs many, many times. So And each iteration, we probably have a map and a reduce step. And between iterations, we want to write the data that we computed, and then we want to read it again for the next iteration. So we know that there's probably reading and writing going on in each of these iterations. And there's also reading and writing going on between these iterations. So we have to read and write this intermediate data each time we want to end or start a new iteration. So one thing that might jump out at you, if you recall the latency lecture, is that a lot of time is spent then in I/O, disk I/O, or even network I/O. One figure has attributed around 90% of this time being spent in I/O operations, which Spark can avoid. So if you want to do iteration in Spark, it can be much more performant because all of this reading and writing to disk can be completely avoided in Spark. We have to, of course, read in data from HDFS, but once things are in memory, we can just iterate on it in memory. We can run the same sort of map reduce steps or filter or whatever steps many times again and again and again for however many iterations that we want, and it's all sitting in memory. It can still be recovered if there is a failure, and there's a lot of reading and writing and things that just don't have to happen because we don't need to persist things to disk all the time. So to begin to answer this question about why Spark is good for data science applications and why transformations and actions and in-memory computations are important, we can start to see here that it's better for iterative programs to be done in memory because they'll be faster. But what does it have to do with transformations and actions? To understand why transformations or actions have to be carefully thought about in this situation, let's look at a quick example. So let's look at logistic regression, which is kind of the hello world of big data iterative algorithms. Logistic regression is a popular iterative algorithm that's typically used for classification tasks. So assuming you have two different classes of data, blue and red, and what we want to do is we want to come up with a classifier, a way to separate out these two different classes of data. So the classifier would be basically this line. We would move it around on this space here until it separates these two classes of data, and then if we ever get new data, we assume that it follows the same trends as the red and the blue, and hopefully it should work for any new data that's added, right? That's the idea of a classifier. So just visually, to get an idea of what we're doing here, on one iteration, we move the line a little bit. On another iteration, we move the line a little bit. We keep doing this. And like I said, we're iterating through all of the data every time. We're doing some math with all of the data. And then eventually, we find a good separating line here, and the algorithm stops. What we're focused on is less the details of logistic regression, but we're really focused on the shape of the computation, the fact that we pass through all of the data on many iterations to come up with a new estimation for this line separating the two sets of data. That's the shape of the computation that we're going to be looking at. And this is how we're going to update those weights that represent the position of that line that separates the two classes of data, right? So as you can see here, there's a number of iterations that we're going to do, and we're going to iterate through this XY data set. And there's some function G, which doesn't need to be shown here, but it's part of the logistic regression algorithm. So this algorithm can be implemented in a very straightforward way in Spark. Here it is. So just to step through it, what we have here is first we have an RDD, points, and this is read in from some text file somewhere. And then this text file is parsed, so we have a map function that goes through all of the lines of this text file. Remember, text file gives you an RDD full of strings, so we have to convert all of these strings into most likely doubles here. We have a vector of weights, so these W's here, which we initialize as 0. And then for some number of iterations that we determine elsewhere, we go through the entire data set several times. So here we go through all of the points, and then we apply this G function here, okay? And then we reduce, and now we update the vector of weights here, using what we have just computed, using this gradient that we just computed. Okay? Okay, cool. So now we understand the basic shape of this algorithm. It's pretty concise, isn't it? Essentially, we iterate on applying a map and a reduce. For some number of times, on a certain RDD, we apply map and then reduce. So we do this perhaps 30 times. And you update some local vector with the results every single time you go through this entire data set. Okay, so that's the general shape of this algorithm, but what's really happening here? Remember on the first slide, we were talking about trying to keep computations in memory and having to think about what are transformations and what are actions. So what's really going on here? I'll give you a second to think about it, and then we'll talk about it on the next slide. Well, the short answer is that we're doing a lot of work that we don't have to do. Remember, transformations like map get reevaluated every time an action is used. So we do have one map here, which gets reevaluated when we call this reduce here. But we also have a map here. That means we're applying this map function again and again and again when we don't have to. So points is being reevaluated on every iteration. If we have 30 iterations, we're reevaluating points 30 times. That's completely unnecessary. We shouldn't have to do that. That's a lot of extra work that we don't want to be doing right now. It would be much better if what we could do is create this points RDD, leave it sitting in memory because we know that's faster, and then reuse it on every iteration. Instead, what we're doing is we're recomputing it on every iteration, which is surely very expensive. So we see here a major consequence of these lazy semantics of these transformation operations. By default, RDDs are recomputed each time you run an action on them. That's something you can't forget about. And of course, as we just saw, especially in the case of an iterative algorithm, this can be very expensive in time if you need to use the data set again and again. But what's nice about Spark is that it gives you a way to control what data you have cached sitting in memory available to reuse again. And in order to instruct Spark, hey, I'm actually going to use this again, don't recompute it 1,000 times, you can use a method persist or a method cache. What these methods do is after an RDD is evaluated, it keeps them in memory so you can reuse them again. So here's a quick example of a situation where you might want to use this cached function or this persist function. So recall this example where we have an RDD full of strings that represent a year's worth of logs. And let's just say we want to go through all of these logs and we want to filter out the ones that are actually errors, right? And we know we're going to have to use this a few times. So here we have an action take. And in this case, so far, if we didn't use persist, this would be okay. What we would be doing is we would be evaluating it once at the point which we call take 10. And that would be it. We wouldn't need to evaluate filter a bunch of times because we only really use it once. However, if I add a line of code here, here's another action, so I have now take and count. It's beneficial now to persist this logs with error RDD, because if we don't persist this, if this is not cached in memory, then what happens is I do this filter on last year's logs twice. I do it when I compute take 10, and I do it when I compute count. So what we can do is if we do persist, that means that this logs with errors, this RDD sits in memory, and it can be reused. So it can be, we just use that again without having to recompute this filter for the take 10, and then we again reuse the same RDD that's sitting in memory to compute this count without having to go through that filter again. So if we go back to this logistic regression example that we just saw, we can add persist to this points method here, and what that'll do is that'll prevent us from having to evaluate it on every iteration. Now we just evaluate it once, and then we reuse that data set that's sitting in memory each time we do this map and this reduce on this points data set to compute this gradient on each iteration. So here we can save a lot of effort and not have to continually recompute this RDD by caching it in memory the first time we use it. Okay, to delve just a little bit deeper into caching and persistence in Spark, it's possible to persist your data set in many different ways. For example, as just regular Java objects sitting in memory. So just as your program normally runs, nothing special, just keep your data in memory. You can also persist it to disk as regular Java objects. You can persist in memory as serialized Java objects. So that is converting these objects in memory to byte arrays or arrays of bytes, which is much more compact, but it takes some effort serializing and deserializing. So it saves memory, but it costs a little bit of compute time. Same thing, put these on disk, or a mixture of keeping data in memory and on disk. And in particular, in this case, rather than reevaluating many transformations a bunch of times, anything that needs to spill over to disk, in case you don't have enough memory, everything that you can keep in memory, you keep in memory, but if you don't have enough memory, then we persist the thing that you tried to cache to disk. That's actually very different from this here. If you run out of memory, in this case, you don't have enough memory between all of your nodes to hold the data set in memory. What happens is a least recently used policy for evacuating things out of memory. So let's say you have an RDD. Let's say you've done 20 transformations on this, and it takes a long time to go through all of them, right? If you don't have enough memory to hold that resulting data set, if you call persist on it, and you've chosen this mode here, what happens is Spark only holds as much as it can in memory, and anything else that it can't hold in memory, it throws it out. If ever those pieces of data need to be reused, then it will reevaluate them. It will go through all of those many transformations that are required to reevaluate the missing pieces of data it doesn't have. So in this case, this right here could be very useful in a situation where it takes a lot of work to get to whatever thing you try to persist, and then can persist at least the thing that you've already computed. So just to give some context, there's many different ways you can configure actually how persistence works in your Spark job. And the two methods that you use are cache or persist. Cache is a shorthand for the default storage level. So the storage level is what we use to configure these things. But you can just write cache with some parentheses behind it. And that will be the default storage level, which is memory only for regular Java objects. That's this one here. And persist is another method that you can pass different arguments to, representing one of these so-called storage levels, in order to customize how the persistence works. So this is the method you use if you want to change the default behavior. And just to show you a quick chart of the different storage levels that are available, these are the things that you pass to that persist method, and here's just a chart kind of showing the pros and cons of different storage levels. So for example, memory only uses a lot of space, but it's pretty fast because you don't have to do any extra processing on this data. It's always in memory, never on disk. Whereas some of these other ones, like memory and disk serialized and whatnot, again, they have different trade-offs, right? So when you keep things serialized, it costs a bunch of time to serialize and deserialize it, CPU time. But of course, it uses very little space in memory. So you can put more data in memory, but of course, you're going to have to serialize and deserialize each individual element of that data set if you want to ever access it. So there are different trade-offs. These is for you to decide depending on the job that you're doing. But just be aware that there are a lot of choices. But in general, throughout this course, we're always really just going to use the default. So we're going to use this memory-only storage level, which you can get by just calling cache or persist without arguments. So a key takeaway of this session is to remember that despite how similar Spark looks to Scala collections, this deferred semantics of the RDDs that you're using have a very different behavior compared to Scala collections. So the need to use this cache function to prevent things from being evaluated multiple times, for example, this is completely unlike Scala collections, even though the same interface is available to you. And you've got to remember this, because this could be the difference between you waiting a really long time for a job to complete or a job being finished in a few seconds. Just to reiterate, due to the lazy semantics of these RDD transformation operators, and due to many users' sort of implicit reflex to assume sort of the eager semantics of regular Scala collections, one of the most common issues that newcomers have when they start using Spark is this issue where people are unknowingly reevaluating several transformations. So you're just kind of doing the same computations again and again and again without realizing that you're doing these many computations again and again and again. And you could save all that effort by doing caching. And of course, this is something important to point out when you do your programming assignments. This is something that students mistakenly do all the time. And as a result, during the programming assignments, Lots of students have a tendency to run out of memory and to not know why. This is a big hint. This is probably going to be the main reason why you might be running out of memory in your programming assignments. So just before we conclude, I want to remind you that actually this laziness is really useful. Because after the last slide, you must be like, oh my gosh, I have no idea what's happening under the hood. How do I know if things are being reevaluated all the time? I have to look much more closely than I thought at my Spark programs, which might seem like a bad thing off the top of your head, but I will remind you again, via 2 examples real quick, why laziness is a good thing. So we saw this example actually in the last session. Just to remind you, let's assume we have an RDD full of strings, which represent a year's worth of logs, and then we do a filter on it to filter out the logs that have errors, and then we just take the first 10 out of those, right? So why is laziness useful here? It's because because filter is delayed until take is applied, that gives Spark the opportunity to inspect this chain of operations that are sort of queued up before being executed. And it lets Spark figure out how to do important optimizations. So, for example, in this case, what Spark can do is it can say, so I only need to find 10 results that match this predicate here from the filter because I'm only going to take 10 of those. So rather than having to go through the entire data set, Spark can intelligently just say, okay, once I've got 10 items that match this predicate here, I'm just going to quit and save a whole bunch of time and not have to iterate through the whole data set just not to use it, right? So Spark can do important optimizations like these. So another important optimization that Spark can do is fusing transformations together. So just like before, Spark now has the opportunity to make an optimization before the count is actually executed. And in this case, what Spark can do is it can stage these computations and then fuse them together, so it has to do less work. So in this case, because map usually requires that you do one entire traversal through a dataset, and filter also requires you to do one entire traversal through a dataset, Spark can say, hey, look, I've got 2 traversals that I've got to do. Maybe I should only traverse this dataset once rather than many times, and I can compute the result of both the map and the filter in a single pass before returning the count. So what Spark can do here is it can basically optimize this, and instead of pass through the dataset many times like would be the case for eager collections like Scala's regular collections, in Scala's regular collections we would be passing through the dataset many times, Spark can very intelligently say, I don't have to do that, I can do less work. So laziness, remember, it's a very good thing. You just got to remember that you have to think about it when you are writing programs. You can't just write code and imagine that everything is eager. You have to remember that transformations are lazy. In this session, we're going to talk about the anatomy of a Spark job. We're going to look at how clusters are typically organized that Spark runs on. And this is actually important. It's going to come back to the programming model once again. You can't just pretend like you have sequential collections that are on one machine. You actually have to think about how your program might be spread out along the cluster. So let's start with a simple example to try and motivate this. Let's say we have a case class person. It's got a name, which is of type string, and an age, which is type int, okay? And let's say we have an RDD full of these person objects. So we have an RDD called people. Now, if we say people.forEach and we print line, so we just want to print out all of the people in our RDD, what happens? I'm going to give you a minute to think about it, or maybe even to look back at your previous notes. Actually, before answering that question, let's look at a second example. Assuming, again, we have an RDD full of these person objects, and I say people take 10, what happens? Where will the array of person objects that is returned by take 10 end up? I'll let you think about this too. Before I give you the answer for both examples, let's first look at how Spark jobs are executed. Spark is organized in a master-worker topology. Remember, you are writing a program which is then getting distributed to a bunch of workers where your data is, and typically roughly the same operation is being done across all of the workers. So usually there's one master and many workers. In the context of a Spark program, we refer to the node that acts as the master as the driver program, and we refer to the workers as worker nodes. Now, The driver program is where this Spark context is. So this is the thing that we are using to create new RDDs, to populate new RDDs. So when we do Spark context or sc.parallelize or sc.textfile, we're actually using this thing here in the driver program. When you write a Spark program, you write a Spark program from the perspective of this node here. So you think as if you are the driver node and you're giving commands to worker nodes. So this is the node that you're interacting with when you're writing Spark programs, and these are the nodes that are actually doing the jobs. So the executors are actually doing all the work, and this is coordinating the work. You can think of it that way. But of course, how do they communicate? They communicate via something in the middle called a cluster manager. And a cluster manager is what actually does the work of doing all of the scheduling and managing resources across the cluster. It keeps track of everything. It does a lot of bookkeeping. Popular cluster managers are Yarn or Mesos. So often when you're running on a real big cluster that you're maintaining yourself, you typically choose one of these cluster managers to run on top of. Okay, so this is more or less the anatomy of a Spark job. So you have this driver program, you have your Spark context in it. All of it is kind of passing through this cluster manager thing that takes care of stuff like memory and whatnot. And all of the work is being done in these things called executors on the worker nodes. So when you take a step back, it's best to think of a Spark application as a set of processes that are running on a cluster where the driver program, the driver node here, the master node, is coordinating all of these processes. And it's important to remember that the driver is where the main method of your program runs, and the process running the code that creates the Spark context, creates RDDs, and it stages up and sends off transformations and actions, that all lives here on this driver node. So the driver node, or the driver program, is really the brains of your Spark job. So these processes that make up a Spark application, these are all running in these executor things here, and this is also where your data is stored and cached. So just to summarize, executors run the tasks that represent the application. They return the computed results to the driver. So whenever an action is done on one of these executors, the executor is the one that returns the result back to the driver program. And of course, executors also provide in-memory storage for cached RDDs. So to summarize the steps that represent the execution of a Spark program, the driver program runs the Spark application, which creates a Spark context upon startup. Then the Spark context connects to a cluster manager. For example, like I said, the most popular are Mesos and Yarn, which then allocates all of the resources everywhere. After that, Spark acquires executors on nodes in the cluster. So now that you have a few nodes and you have this cluster manager running, then you establish executors everywhere. And these executors are the processes that run computation and store data for your application. Next, your driver program then sends your application code to the executor. So the driver program is actually sending code around. Think about it. You're sending a function around to the individual nodes here. So if I want to do a map on an RDD, this guy is actually sending that function to all the individual worker nodes and saying, hey, apply this function to the data that you have on your node. And then, maybe there's an action and then send the result back to me. And finally, the Spark context sends tasks for the executors to run. So the Spark context figures out what to do and then sends it along to the executors to actually execute that work. So let's go back to our first example, now that we know a little bit about the anatomy of a Spark job. So remember, we had an RDD of these person objects. We did people.forEach println. So the question was, what happens? Well, on the driver, nothing happens. Why might that be? I'll give you a hint. For each is not a transformation. Remember that for each is an action, and it has return type unit, so it's a side-effecting thing. Therefore, because it's an action, it's eagerly executed on the executors, and it's not being executed on the driver. So any calls to println that happen inside of this for each thing end up happening on the individual worker nodes. So then whatever this println is doing is being executed on the worker nodes, and it's going to the standard out of the worker nodes, which you can't see if you're looking at the standard out of the master node that you're on. So basically what this does is it prints lines on the workers that you can't see because you're sitting on the master. Okay, what about this? The second example here. So what if we have this RDD of people and we do people.take? What happens? Where will the array of person representing first 10 end up? Well, by now I think you'll guess the driver program, because in general when you execute an action, it involves communicating data back from the worker nodes to the driver program. So what you do here is you're telling the executor nodes to do this computation and to send it back to the driver nodes. So running an action actually sends data back to the driver nodes. So what you're doing is you're giving an order to the worker nodes to do some work, and then the work nodes are sending their data back to the driver node. So the driver program is the one that has this array of 10-person objects. So the moral of the story is to make effective use of RDDs, you really have to understand a little bit about how Spark works under the hood. In particular, you have to know the anatomy of a Spark job. You have to know that there's something called a driver program, and that's sort of the brains of the application, and that a bunch of work is being farmed out to worker nodes and executors all over the place, right? And due to this API, which is mixed, eager and lazy, it's not always immediately obvious upon first glance which part of the cluster a certain line of code might run on. For example, transformations. So transformations are queued up, and then when an action comes along, then all of that stuff that got queued up gets optimized by the driver program, sent to the worker nodes, and then the worker nodes send something back to the driver node. So when you write a line of code like for each, you really have to think about where that code is going to execute. If you write for each and you want to do some for each print line to see what is going wrong with your data set, you're not going to see the result of that because that's being executed on the workers. So you really got to think about where your code is executing. It's on you to know where that code is executing. So remember, even though RDDs look like regular Scala collections upon first glance, unlike Scala collections, RDDs require you to have a good grasp of the underlying infrastructure that they're running on. That's the takeaway for this session. In this session, we're going to talk about the anatomy of a Spark job. We're going to look at how clusters are typically organized that Spark runs on. And this is actually important. It's going to come back to the programming model once again. You can't just pretend like you have sequential collections that are on one machine. You actually have to think about how your program might be spread out along the cluster. So let's start with a simple example to try and motivate this. Let's say we have a case class person. It's got a name, which is of type string, and an age, which is type int, okay? And let's say we have an RDD full of these person objects. So we have an RDD called people. Now, if we say people.forEach and we print line, so we just want to print out all of the people in our RDD, what happens? I'm going to give you a minute to think about it, or maybe even to look back at your previous notes. Actually, before answering that question, let's look at a second example. Assuming, again, we have an RDD full of these person objects, and I say people take 10, what happens? Where will the array of person objects that is returned by take 10 end up? I'll let you think about this too. Before I give you the answer for both examples, let's first look at how Spark jobs are executed. Spark is organized in a master-worker topology. Remember, you are writing a program which is then getting distributed to a bunch of workers where your data is, and typically roughly the same operation is being done across all of the workers. So usually there's one master and many workers. In the context of a Spark program, we refer to the node that acts as the master as the driver program, and we refer to the workers as worker nodes. Now, the driver program is where this Spark context is. So this is the thing that we are using to create new RDDs, to populate new RDDs. So when we do Spark context or sc.parallelize or sc.textfile, we're actually using this thing here in the driver program. When you write a Spark program, you write a Spark program from the perspective of this node here. So you think as if you are the driver node and you're giving commands to worker nodes. So this is the node that you're interacting with when you're writing Spark programs, and these are the nodes that are actually doing the jobs. So the executors are actually doing all the work, and this is coordinating the work. You can think of it that way. But of course, how do they communicate? They communicate via something in the middle called a cluster manager. And a cluster manager is what actually does the work of doing all of the scheduling and managing resources across the cluster. It keeps track of everything. It does a lot of bookkeeping. Popular cluster managers are Yarn or Mesos. So often when you're running on a real big cluster that you're maintaining yourself, you typically choose one of these cluster managers to run on top of. Okay, so this is more or less the anatomy of a Spark job. So you have this driver program, you have your Spark context in it. All of it is kind of passing through this cluster manager thing that takes care of stuff like memory and whatnot. And all of the work is being done in these things called executors on the worker nodes. So when you take a step back, it's best to think of a Spark application as a set of processes that are running on a cluster where the driver program, the driver node here, the master node, is coordinating all of these processes. And it's important to remember that the driver is where the main method of your program runs, and the process running the code that creates the Spark context, creates RDDs, and it stages up and sends off transformations and actions, that all lives here on this driver node. So the driver node, or the driver program, is really the brains of your Spark job. So these processes that make up a Spark application, these are all running in these executor things here. And this is also where your data is stored and cached. So just to summarize, executors run the tasks that represent the application. They return the computed results to the driver. So whenever an action is done on one of these executors, the executor is the one that returns the result back to the driver program. And of course, executors also provide in-memory storage for cached RDDs. So to summarize the steps that represent the execution of a Spark program, the driver program runs the Spark application, which creates a Spark context upon startup. Then the Spark context connects to a cluster manager. For example, like I said, the most popular are Mesos and Yarn, which then allocates all of the resources everywhere. After that, Spark acquires executors on nodes in the cluster. So now that you have a few nodes and you have this cluster manager running, then you establish executors everywhere. And these executors are the processes that run computation and store data for your application. Next, your driver program then sends your application code to the executor. So the driver program is actually sending code around. Think about it. You're sending a function around to the individual nodes here. So if I want to do a map on an RDD, this guy is actually sending that function to all the individual worker nodes and saying, hey, apply this function to the data that you have on your node. And then, maybe there's an action, and then send the result back to me. And finally, the Spark context sends tasks for the executors to run. So the Spark context figures out what to do and then sends it along to the executors to actually execute that work. So let's go back to our first example, now that we know a little bit about the anatomy of a Spark job. So remember, we had an RDD of these person objects. We did people.forEach print line. So the question was, what happens? Well, on the driver, nothing happens. Why might that be? I'll give you a hint. For each is not a transformation. Remember that for each is an action, and it has return type unit, so it's a side-effecting thing. Therefore, because it's an action, it's eagerly executed on the executors, and it's not being executed on the driver. So any calls to print line that happen inside of this for each thing end up happening on the individual worker nodes. So then whatever this print line is doing is being executed on the worker nodes, and it's going to the standard out of the worker nodes, which you can't see if you're looking at the standard out of the master node that you're on. So basically what this does is it prints lines on the workers that you can't see because you're sitting on the master. Okay, what about this? The second example here. So what if we have this RDD of people and we do people.take? What happens? Where will the array of person representing first 10 end up? Well, by now I think you'll guess the driver program, because in general when you execute an action, it involves communicating data back from the worker nodes to the driver program. So what you do here is you're telling the executor nodes to do this computation and to send it back to the driver nodes. So running an action actually sends data back to the driver nodes. So what you're doing is you're giving an order to the worker nodes to do some work, and then the work nodes are sending their data back to the driver node. So the driver program is the one that has this array of 10-person objects. So the moral of the story is to make effective use of RDDs, you really have to understand a little bit about how Spark works under the hood. In particular, you have to know the anatomy of a Spark job. You have to know that there's something called a driver program, and that's sort of the brains of the application, and that a bunch of work is being farmed out to worker nodes and executors all over the place, right? And due to this API, which is mixed, eager and lazy, it's not always immediately obvious upon first glance which part of the cluster a certain line of code might run on. For example, transformations. So transformations are queued up, and then when an action comes along, then all of that stuff that got queued up gets optimized by the driver program, sent to the worker nodes, and then the worker nodes send something back to the driver node. So when you write a line of code like for each, you really have to think about where that code is going to execute. If you write for each and you want to do some for each print line to see what is going wrong with your data set, you're not going to see the result of that because that's being executed on the workers. So you really got to think about where your code is executing. It's on you to know where that code is executing. So remember, even though RDDs look like regular Scala collections upon first glance, unlike Scala collections, RDDs require you to have a good grasp of the underlying infrastructure that they're running on. That's the takeaway for this session. In the last few sessions, we focused on operations like map, filter, and flat map, and we got a lot of intuition about how these sorts of operations are distributed over a cluster. So, for example, how a distributed map or how a distributed filter is done. And also along the way, we got a little bit of intuition about the anatomy of a Spark job, where these operations are actually running. Though so far we haven't focused on distributed reduction operations. In this session, we're going to focus on reduction operations in Spark. So far, we've defined distributed data parallelism, and we saw intuitively that Spark implements this model. And most importantly, in the first few sessions, I hope you got a feel for what latency really means to a distributed system. Then we covered Spark's programming model. In the beginning, we learned that from 10,000 feet from really far above, Spark looks like Scala collections, but internally, Spark doesn't behave very much like Scala collections. In particular, Spark uses laziness to save time and memory on the latency front. In that vein, we saw transformations and actions, and we learned about caching and persistence. Or said another way, we learned how to selectively cache data in memory in order to save compute time. We also saw how the cluster's topology comes into the programming model. You can't forget where your code is running. So far, most of the intuitions that we've developed have focused on distributing transformations such as map, flat map, and filter. And we spent a lot of time visualizing how transformations like map, flat map, and filter are parallelized and distributed. Though if you notice, we didn't yet consider how actions are distributed. So think about operations like reduce. How are these actions distributed? They're very different from operations like map or filter. Okay, since they're so different, maybe we should first clarify what we mean by reduction operations. By reduction operations, I mean operations such as fold, reduce, or aggregate from Scala collections. All of these operations, including their variants like fold left or reduce right, have something in common about how they're computed. They have some shared structure of computation. Can you remember what that is? So we can conceptually say that reduction operations walk through collections and combine neighboring elements together to produce a single combined result. Note that this is unlike map because map returns a new collection and a reduction operation essentially combines the elements of the collection into some kind of single value like an integer or a double or a string. So many of Spark's actions can be considered reduction operations, but some actions are not reduction operations. For example, saving things to a file, that's not a reduction operation, yet it's still an action in Spark. So just to give you a more concrete example of what we mean by a reduction operation, let's look at a simple illustration. Let's say we have the case class taco with two fields, one named kind, which is of type string, and one named price, which is of type double. And let's say we have a list of instances of taco, and we'll name that list taco order. So we have this list here of tacos. We can use a reduction operation to calculate the cost of the taco order. In this case, we'll use a fold left operation, and we'll walk sequentially through the collection of tacos, accumulating and summing up the price of all the tacos, starting with the initial price of the 0. So starting with this 0.0 double here, we're going to accumulate up the prices and sum them up. And at the very end, we'll have the price of all of these tacos summed up. This is very simple, and I hope you remember these kinds of operations from the last few Scala courses. But my point in showing it to you is just to remind you of the difference between this kind of operation, where the goal is to combine together the elements and to return a single result, with that of the transformation-like operations we saw earlier, like map or filter, where we apply some kind of function to each element in the collection when we return a new collection. So now that you remember what I mean by a reduction operation, let's recall parallel reduction operations from the parallel programming course. In that course, we learned about fold left and fold. Do you remember which of these two were parallelizable? I'll give you a moment to think about it. Try to visualize the two operations and think carefully about why the pattern of computation for one might be parallelizable and why the other one might not be. You might remember that fold left is not parallelizable. According to the Scala API documentation, fold left applies a binary operator to a start value, and all elements of the collection are iterator going from left to right. So this is the start value here. Notice here we have to execute things from left to right sequentially. And if you remember from the parallel programming course, Alex gave this really cool visualization with a Lego block, which shows how having these two types that you combine down to one type, so AB to B, AB to B, this forces us to have to execute things sequentially. Though for me, this isn't the clearest illustration, even visually, so let's step through a simple example to see why we can't parallelize fold left. In particular, this Lego block visualization tries to show that if we have to change the result type from A to B, we have to execute things sequentially from left to right. So let's say we have a list with 4 integers in it, 1, 2, 3, and 4. And now we want to use fold left to walk through all elements in the list and to combine them together into a single string. So at the end, what we want is a string, 1, 2, 3, 4. So just something like this. So let's step through this simple example and let's try to parallelize it by hand to understand why the types are stopping us from doing this in parallel. So remember that the idea in parallel programming was that we would be breaking these collections into pieces and individually working on each piece. So let's break this XS list into 2 pieces. And let's try to compute this fold left function on each individual piece in parallel, and then let's combine them later. So let's start with the first element in our first chunk. We take the 0, the empty string, and then we concatenate it with the first element. This gives us 1. Then we do the same for the next element. Now we have 1. We add 2. Now we have the string 1, 2. And we can imagine that in parallel, the same thing is happening here. So we start with our 0, and we take the first element, which is 3, and we get the string 3. Same thing happens for the next element. We have now 3. We concatenate with 4, and now we have 3, 4. So these things can be done in parallel, independently of one another. Now we have to combine them together. Notice our function is from type string int to string. But the types of these individual pieces now, if we want to try and combine them together, is string, string, which doesn't fit into this function anymore. So now we would have a type error if we tried to combine these things. So I hope that illustrates what we mean when we say that because the type has to change, we can't do this operation in parallel. Suddenly we can't combine these 2 individually computed pieces together anymore, due to the types. So this is why fold left is not parallelizable. So that brings us to the fold operation. And as a reminder, fold is very similar to fold left, except with the requirement that we always have to return the same type. So remember in the signature of fold left, we had BA here, now it's AA. Everything is the same type. And if we recall our last example, if this list here was a list of strings instead of a list of integers, then I hope you can see how, due to the types being all the same, where everything is a string and we're taking strings and combining strings and returning strings, then it's easy to parallelize these operations. So said another way, the fold function enables us to parallelize things using a single function as a parameter, where the types are all the same, and by enabling us to build parallelizable reduced trees. And if the Lego visualization helps, here's how it would look to build one of these reduced trees. Here you can see how the tree could be broken up and worked on independently by different workers. So you can have somebody working on this part of the tree and somebody working on this part of the tree totally independently of one another. And then they can still combine all of the results together. So I hope you have some intuition now for the differences between fold and fold left and why it's easy to parallelize one operation but not easy to parallelize the other one. And that brings me to the aggregate operation. Does anybody remember what aggregate does? This is important, so I'll give you a second to try and remember. I'll give you a hint though. As it sounds, it's similar to fold left or fold. However, the signature is a little different. Okay, so here's the signature of the aggregate method for regular Scala collections. Now we have 3 parameters in 2 parameter lists. Like before, we have a start value of type B, but now we have 2 functions instead of 1. We have seekop and comboop. The first one, seekop, represents a sequential operator, and like in fold left, it operates on two types. The second one is called combo op, and it represents a combination operator. And like in regular fold, it only operates on one type, in this case B. So this is kind of like the function in fold left, and this is kind of like the function in regular fold. While the signature might seem complicated, it's actually great for parallelizing things over a cluster. In fact, it's considered to be even more general than fold or fold left because it's both parallelizable and it makes it possible to change the return type to something else. So to just bring back the cool Lego visualization, we can now visualize how it's possible to parallelize the aggregate operation. As you can see, what this does is it allows us to do the work of the fold left on separate chunks in parallel. So you can have individual workers doing this work, so think individual nodes or individual executors doing this work. We can change the types using this fold left sequential style reduction operator, but we can do it in parallel on chunks. And now that we have this combo op function here, it makes it possible to build these nice reduced trees that are so easy to parallelize. Okay, great. Now that we have an intuition about why some operations can be done in parallel and why some can't be, and how to do everything we want to do, like changing types and still doing reduction computations in parallel, though how does this relate to RDDs? How do we distribute these things? Well, let's start by looking at which of these reduction operations exist on regular Scala collections and on Spark. Of course, what we see here is that one operation we knew couldn't be parallelized simply doesn't even exist on RDDs. So sequential fold left and fold right operators are simply not defined on RDDs at all. You have no choice to use them. This could be perhaps a little frustrating because fold left tends to be a pretty commonly used reduction operator when working with collections. It seems to be one of the more popular variants. And now you suddenly don't have access to it at all. So what does this mean? Well, since in regular Scala collections, our only choice for changing the return type of a reduction operation was to use either the fold left or fold right operation or aggregate, this means that now in Spark, since there is no fold left or fold right operation, we can only use the aggregate operation if you have to change the return type of your reduction operation. So now you have no choice. You can't reach for this familiar fold left anymore. You have to use this weird aggregate thing that maybe you didn't use so much before in regular Scala collections. But you might be saying, hey, hold on a second. Why not still have a serial fold left or fold right operation in Spark? It would mean a simpler and more convenient API for users to use, and it would be more in line with regular Scala collections, right? Well, it turns out that trying to do anything serially across a cluster is actually very difficult. Enforcing ordering in a distributed system is very hard and sometimes impossible. And in any case, it requires a lot of communication and synchronization between nodes, which we've learned throughout several of our sessions now is extremely costly. So it simply doesn't make sense to try and make sure that something happens before another thing in a distributed system. Which means it simply doesn't make a lot of sense to try and make available serial operations like fold left on a cluster. In fact, I'll even argue that in Spark, the aggregate operation is actually a more desirable reduction operation a lot of the time. Why do you think that's the case? So remember, we're in distributed thinking now. We have big data sets. What is it about the jobs that you might want to do with Spark that would make an operation like aggregate so desirable to use? Think about it. As you get to know from the programming assignments and hopefully from real data analysis jobs, as you'll get to know from the programming assignments, and hopefully from real data analysis jobs you may one day do on real clusters with a Spark, much of the time when you have some large amounts of data, you typically have very complicated records or elements of your RDD. So like the individual element types are very big, nested, complex things. They're often not simple integers or strings like we've been looking at, but instead they're a really complex data type. And often you don't need the whole thing to do the analysis that you may want to do. You may want to project down this really complicated data type into something simpler to actually work on. For example, if you wanted to do a computation involving the data stored on Wikipedia, you may have a data type called Wikipedia page which contains all kinds of fields, probably more than what's listed here, but which could include things like the title of the article, the redirect title of the article, the timestamp of the article, the username of the last person to contribute to the article, and the actual text contained within the article. So you can also imagine many more possible fields, like a list of articles linked to in that Wikipedia article, etc. And you can imagine that to do some kind of interesting computation or some kind of interesting analysis on your Wikipedia data, you may only care about the title of the article and the timestamp. In this scenario, if you had to keep the full text of every Wikipedia article around in every element of your RDD, it could waste a lot of time and a lot of memory to carry around this perhaps very big full text string around in your accumulator. This is why you might find that you would use the aggregate operation more often in Spark than you did in Scala collections, because typically you want to get rid of stuff that you don't need and project down to a smaller data type. In this session, we're going to focus on distributed key-value pairs, which are a popular way of representing and organizing large quantities of data in practice. And in Spark, we call these distributed key-value pairs pair RDDs. If we think back to the functional programming and Scala courses, when we were focusing only on sequential Scala and the basics of functional programming, we didn't work with any data types called key-value pairs, though we did work with a collection type called a map. And if you recall, maps are essentially collections of keys and values, so while we didn't call a map a key-value pair, conceptually it's the same thing. And this concept goes by other names in other languages, such as associative arrays or dictionaries in languages like JavaScript or Python. Though if you think back to the single machine scenario, even though most languages have something like a map or a dictionary as a core data structure, maps, dictionaries, etc. maybe weren't the most often reached for data structure on the shelf of data structures that you had to choose from when you were doing these programming exercises in the earlier functional programming courses. You might have used other data structures like lists or even arrays more often than you might have reached for something like a map. However, in the world of large-scale data processing and distributed computing, the opposite is actually true. It's actually more common to operate on data in the form of key-value pairs than anything else. In fact, when Google designed MapReduce, focusing on all data as key-value pairs was a key design decision based on real use cases involving large amounts of data at Google. In fact, the original designers of MapReduce even explained the rationale surrounding their focus on key-value pairs very clearly in their original research paper which presented MapReduce to the world back in 2004. They said here, "We realized that most of our computations involved applying a map operation to each logical record in our input in order to compute a set of intermediate key-value pairs, and then applying a reduce operation to all of the values that shared the same key in order to combine the derived data appropriately." Or said another way, computations that they were already doing at Google always ended up producing key-value pairs, so they focused the design of MapReduce around this common pattern for manipulating large amounts of data. This is due in large part to the fact that large datasets are often made up of unfathomably large numbers of complex nested data records. So complex elements of a large dataset like the Wikipedia case class we saw in the previous session. And of course the case class that I showed you was just an example and a simplification of such a record. Given such complex records and the need to do computations on them, often data analysts need to project down these complex data types into key-value pairs in order to operate on them. Here's another example of a record. A single element in this case, and it's in JSON, but this is the shape of perhaps a single element that you might find in an RDD. The intuition I want you to get here is that often there are many fields and there are lots of rich nested structure to these records. There can be objects nested in objects, and it could go quite deep. So let's say we have something like this JSON record on the left as our input data, and the analysis that I want to do may focus only on the cities that certain properties are in. So here we have some properties, and I care about the cities and perhaps the street addresses, but maybe I want to do some analysis, and I don't care about the rest of this data, I only care about this part of the data set here. So in this case, it may be desirable to create an RDD of properties of type pair string property, where the key of type string represents the city that a property is in, and the property type here represents the corresponding value like we see in the record to the left. We have a case class for it here, where the property contains a street of type string, a city of type string, and a state of type string. So you could imagine that given a bunch of these properties, it could be desirable to group them by their cities as the key, to do computations then on these groupings of properties by city. This is one scenario where on a large dataset, manipulating your data into a key-value pair might be desirable. As alluded to earlier in the session, in Spark, we call these distributed key-value pairs pair RDDs. And they're particularly useful because they allow you to do special operations per key in parallel, and they allow you to group data by keys across the network. Very importantly, pair RDDs come with special methods for working with data that's associated with a corresponding key. That is, pair RDDs have extra methods related to keys that regular RDDs don't have. So if you try to call some of these methods on an RDD which is parameterized by type integer, so an RDD full of integers, the compiler would say, nope, I can't do it, and it will give you errors saying the method cannot be found. So remember, if you have an RDD with a type parameter that is a tuple or a pair, it is treated specially by Spark. It has special extra methods. And just to give you a sense of a handful of these special methods that we have on pair RDDs, some of the more commonly used ones are group by key, reduce by key, and join. We'll cover these methods in a lot more detail very shortly. But first, you might ask, well great, how do I actually create a pair RDD? It's actually quite simple. Pair RDDs are most often created from already existing regular RDDs using operations such as the map operation on RDDs. So that said, let's do a quick quiz. Let's say I wanted to create a pair RDD from an RDD full of these Wikipedia pages that we saw on a previous slide, such that the key of the pair RDD represents the title of the Wikipedia article and the value of the pair RDD represents the text of the Wikipedia article. What method would I have to call with which arguments to create this pair RDD from this val RDD above? So again, as a hint, you can use some kind of transformation operation to then create a pair RDD. What would you use? It's simple. In this case, I can just call map on the original RDD here, and I pass a function here, which selects the title and the text from the Wikipedia article, and then makes them into an element of a pair. So this is now a pair RDD, and it has all of these special key-value pair transformation methods available to you to be used now. So now the type is what we saw on the previous slide. The type looks something like this now, so it gets all the special methods. So now you can do things like reduce by key or join on this new pair RDD that you couldn't do before on this Wikipedia RDD. In the next session, we're going to dive into a lot more detail about these operations on pair RDDs, so these and more. Now that we've seen pair RDDs, in this session, we're going to focus on some of the most commonly used pair RDD operations that you're going to find in the wild. Just like we saw before for regular RDDs, these common operations can be broken into two categories, transformations and actions. There are several special transformations specific to pair RDDs that we'll cover, and one special pair RDD action that's called count by key. Now, if we look at some of the transformations that we'll cover, many look familiar. In the functional programming in Scala course, we remember operations like group by, for example. So there's this group by key that seems kind of similar. And of course, remember stuff like reduce, map values, this guy here. It sounds kind of like map. We might be familiar with some idea of what join is from some experience that we've had with databases in the past, so these guys kind of sound familiar as well. But let's drill a little bit deeper into some of these operations. Let's start with group by key. To do that, let's first recall group by from regular Scala collections. Do you remember what this operation does? So just remembering group by from regular Scala collections, if we look at the API documentation, group by has the following signature. Group by takes a function from A to K, so a function from some type to the type of the key that the group by should return, and of course it returns a map, where the key maps to a collection of elements of type A. The API docs succinctly describe the semantics of this operation as follows. So group by partitions this traversable collection into a map of traversable collections according to some discriminator function. We can also say this a little more simply by looking at it in the following way. So assuming you have some kind of collection, the group by operation will break up that collection into two or more collections themselves according to some function that you pass to group by. So according to this function here. The results of the function are the key, so that if you apply this function to individual elements of the original collection, whatever the result is of that function application is the key that that element should correspond to in the resulting map returned by the group by operation. So the map returned by this group by method contains keys mapped to collections of those keys' corresponding values. It still sounds a little confusing, doesn't it? I'm trying to make it simpler, but I don't know if you can visualize it. So let's make this a little bit clearer by looking at an example from regular Scala collections. So let's assume that we have a list of integers here. It's called ages. And these integers represent the ages of people. Now let's group this list of ages into categories. One for a child, one for adults, and one for seniors. So we have three categories. That means we need a function that when it's applied to the integers in this list, it determines which key that age should correspond to. So let's do it with a simple conditional expression. If the age is greater than or equal to 18 and less than 65, then we know that this person should be an adult. They have to be an adult. Else, if this person is under 18 years old, then this person is a child. And finally, anything else, we say this person is a senior. So we assume that they're over 65, and that means they're a senior. So now what group by does here is applies this function to each element in the ages list here, and it determines the string that corresponds to the age, whether it's a child, adult, or a senior. And then it produces a map as a result, with a list of the ages that correspond to each key. So now we have a map containing 3 keys, senior, adult, and child, where the corresponding values are lists of the ages that we found in our original list of ages that fall into those categories, that are grouped into those categories. Hence, why we call the operation group by. We're grouping elements into a category based on some discriminating function. I hope that makes the group by operation a little clearer now. Okay, so let's get back to Spark now. Spark's group by key operation can be thought of as group by on pair RDDs, but it's specialized on grouping all of the values that have the same key. So that means we're doing it on a collection that's already a collection of pairs, or in this case, an RDD of pairs, a pair RDD. That means that we don't have the discriminating function anymore. Now, group by key has no arguments. In this case, we only want to group things by the keys that they already have. So we just want to take an RDD that's full of many key value pairs, and we want to now return an RDD with all of the values collected that correspond to a specific key. All of these collected values should be put into some kind of iterable, so some kind of regular Scala collection. So we go from countless little pairs of keys and values with possibly many of the same keys floating around with different values, and now we have just one key that matched to a collection of all of the values that correspond to that key. And then they've been grouped into a regular Scala collection. To make that a bit more concrete, let's look at an example. Let's say we have a case class called events that represents events. Here. And each event should have an organizer. So let's just say there's a concert or something coming up and somebody is organizing it. The concert will have a name, and that's the string here. And then each event should have a budget of some kind. And so our first step is to make a pair RDD. So we do that with this map function here. And we organize things such that our key is the event organizer's name, and then the value is the budget for the given event. Now we call group by key on that new pair RDD we just created on the previous line. So what does this call do? I'll let you think about it for a moment. Remember, the key is the organizer. Haha, it was a trick question. The answer is that it does nothing as it is. It returns a reference to an unevaluated RDD. Remember that group by key is a transformation. It's a transformation. So that means it's lazy and nothing happens when you call it. It returns a reference to an unevaluated RDD. But okay, if we called an action on it, in this case collect here, now we have an array that we've gotten back from our RDD, which forces that computation to take place. Then we can call for each on that array and then print line to just print the elements of the array returned by the collect to see what the result looks like. Assuming that we have a few events that have been organized by the same organizer, the result would look like this here. The organization Prime Sound, for example, has just one event with a budget of $42,000 or francs or whatever currency it's in, and then the other organization called Sport.org seems to be organizing 3 different events, each with budgets of $23,000 or francs, $12,000 of francs, and $1,400 of francs. So that's group by key, and it's actually quite an often reached for method on large data sets. You might find yourself deciding, oh my gosh, it would be really useful to group these things by key and then do something with these grouped elements. However, there's another important transformation operation on pair RDDs called reduce by key. Conceptually, you can think of reduce by key as 2 operations. First, the group by key that we saw on the previous slide, and then reducing all of the values in the collection that corresponds to each key. So the resulting collections that come back, then we reduce on those that correspond to each key via some function. And what's really, really important to note here is that reduce by key is actually a lot more efficient than doing group by key and then reduce independently. We'll see why shortly, but this is an important little note that you should hold on to. So let's look at the signature of reduce by key. As we can see, reduce by key takes a function which only cares about the values of the pair RDD. So we're using v here to represent the values. So we don't actually do anything with the keys in this function. We only operate on the values. This is because we conceptually assume that somehow the values are already grouped by key, and now we apply this function to reduce over those values that are in a collection. So this function, we imagine it reducing on all of the elements in the compact buffers here. Again, to make this more concrete, let's look at an example. Let's reuse the events pair RDD from the last example. Now let's say we would like to calculate the total budget per organizer over all of their organized events. Now that we have a little bit of intuition for what reduce by key does, how might we use it to calculate the total budget per organizer given a pair RDD where the key is the organizer and the value is the budget of some event? I'll give you a minute to figure out how to implement budgets RDD on your own. This should be quite easy. We just call reduce by key on the events RDD, and we pass into it a function literal that sums up the adjacent values. Again, remember that reduce by key is a transformation, so that means it's lazy and nothing happens after you call it, even though it looks kind of like a reduce, which, if you recall, is an action on regular RDDs, but on pair RDDs, reduce by key is a transformation. So that means we have to call some kind of action after our call to reduce by key. In this case, again, we call collect to start the computation, and then we can print out the results with a regular for each on the returned array. And here what we can see in the results are that there are 4 organizations organizing events, and the total budget across each organization is shown as the second element in the returned pairs here. So I hope that illustrates clearly reduce by key for you, and it's pretty important because you're going to find this useful in your programming assignments as well. Let's look at another kind of transformation called map values, and the one action I mentioned at the beginning of this session called count by key. So let's start with map values. The map values transformation, as its name suggests, applies a given function only to the values of a key value pair. This is something often you may want to do when you want to do a map on a pair RDD, but you remember that you have to somehow handle the key in the function argument that you pass to the map. So you can think of this operation as a shorthand for skipping over having to deal with the keys. It just is a little bit shorter in this example. It has some other benefits as well. We'll talk about that a later lecture. So said simply, map values applies functions only to the values in the pair RDD, and it skips over the keys. It's pretty straightforward, and it's the way people typically do mapping operations on pair RDDs. They don't really use the map operation a lot of the time. The other operation that we'll look at is count by key, which is an action. Like its name, it simply counts the number of elements per key in a pair RDD. Importantly, it returns a regular Scala map, so not anything distributed, but like a regular Scala collections map, and that maps the keys to the corresponding counts. So you then have a count per key of all of the values that you maybe have per key. And it's very simple, and remember it's an action, just like the count operation on regular RDDs, but it's specialized in this case for pair RDDs. As usual, let's look at an example to make these operations a bit more concrete. Again, let's use the event pair RDD that we recall from the previous slides, and instead, let's use each of these operations, if we can, to compute the average budget per organizer. So now we're taking an average. I'm going to help you out a little bit in the beginning, so let's do this step by step, but let's start with an intermediate RDD here. Let's calculate a pair as the corresponding value of the organizer key. That means our value is also a pair, which will represent the total budget and the total number of events that correspond to that event organizer. So this is the value here. The value is a pair itself, and it has the first element is the budget, and the first element is the number of events that correspond to that organizer. Okay, so first question, can we use count by key here? Let's start with map values. Remember, our pair RDD called events RDD contains key value pairs where the key is the organizer and the value is the budget for some event. We know we need to take a sum of the number of events, so we can use map values to make a new pair from our existing key value pair that makes it easier to sum up the events per organizer. So later on, we're going to want to sum up the events. So for the value in the key value pair, we make a new pair where we just leave the value as it was, whatever the value was before, and we have a second element of the resulting pair, which is just the number 1. Just to write this out, in the events RDD, we have the organizer as our key and the budget as our value. This is before the map values. And now after the map values, what we're going to have is this. Since we're using map values, the key stays the same, nothing happens to it, and the value changes. So basically what we're doing here, this B is the budgets. So we say, okay, we keep the budget, whatever, and we add a 1 as well. So we do budget and an integer 1. And this is now the result of the map values call. Now let's use reduce by key to return a pair RDD whose value is another pair representing an organization's total budget and the total number of events that this organization is organizing. So now what we want is this here, this budget and events, we want this to be the result that we get back from this reduced by key. And this is the data that we have to start with. So our data is in this shape right now. So what do I have to pass to reduce by a key here to make sure that the result ends up in this shape? Try it for yourself. So remember that the function passed to reduce by key operates only on the values of the pair RDD, right? So let's remember the signature of reduce by key. There was a function that was on the values only. No keys were involved. And the value in this case is a pair. Do you remember? So each of these V's are pairs. And these pairs are representing a budget as the first element, and then just the number 1 as the second element. Both of these. So that means in the result here, we can take the two adjacent elements, which are each pairs themselves, and we just have to sum up the first elements of the pairs with the first elements of the adjacent ones, and the second elements with the second elements. So basically we're summing up budgets with budgets and the number 1s with number 1s. And then the result type should be another pair RDD where the key remains the organizer string and the value is a pair of integers that represents the total budget and the total number of events organized by that organization. Do you see what we've done? Both operations that we called on our pair RDD managed to focus only on the values of our pairs, map values, and reduce by key. In both cases, we never had to worry about messing around with the keys. We could just focus on the values associated with those keys. So does this make sense? Here we sum up the budgets. Here we sum up 1s for the total number of events. Okay, but we're not done yet. Remember, we said we wanted to compute the average budget per event organizer over all of their events. So now we finally have the information that we need to compute this average. So then I leave it to you again. Given this RDD that's called intermediate now, we're going to use this guy, how would you compute the average budgets per organizer? So we need the average budget per event organizer now. What operations would you use? Again, try it for yourself first. So here, I've used map values again. Remember, map values focuses only on the values and not on the keys when it applies its mapping function. So I can use it to compute the average budget per organizer by simply dividing the total budget by the number of events organized by each organizer. That should now give me a pair RDD where the key still corresponds to the name of the organizer, but now the value is an integer representing the average budget per event of that organizer. And of course, just like before, I just call collect and for each again to materialize my RDDs and kick off the computation, and then now I can see the results. But wait, didn't I ask you to think about using count by key? Why didn't I use it here? Well, the answer is pretty simple. In all cases so far, I've been carrying around as my value another pair. So I've had a pair as a value, and I wanted to do something more complicated than simply counting it each time. I wanted to compute an average. So in this case, it was easier for me to use map values and reduce by key to get the info that I wanted. It doesn't mean that it's not possible to do this somehow via count by key. It's just that in this case, I chose map values and reduce by key to get it done. Let's move on to a different transformation called keys. The signature of keys looks like this. It takes no arguments and returns a new RDD, which represents only the keys of the pair RDD on which it was called. Now remember, this is a transformation, which means that it's lazy. At this point you might ask, well, why is that the case? Because operations like collect are not. They're actions and they return an array back to the master node. In this case, keys is a transformation because the number of keys in a pair RDD could be huge. So if we tried to return all of the keys to the master node like we do for collect, we could find ourselves in a situation where we overwhelm the master node and run out of memory because we simply weren't aware that there were so many keys. This is why it's a transformation. We don't want to accidentally return an entire RDD to our master node where it doesn't fit into memory. As usual, let's look at an example to try and make the keys method a little more concrete. In this example, we're going to try and use this method to count the number of unique visitors to a website. So let's say we have a case class visitor here, and we have various pieces of information. In this case class, we have the IP address of the person who visited the site, the timestamp that they visited at, and the duration that they visited for. So let's say we have an RDD full of instances of this visitor type, and then here I make a pair RDD out of it. The slides were missing a line. So here we have, for each visitor, we create a pair where the key is the IP address and the value is the duration. So what methods do we call to get a number that represent the number of unique visitors? Well, we simply have to call keys distinct, and then we have to count them up. And note that the action here is the count method, because both the keys and distinct methods are transformations. So this is how we kick off the computation here when we call count. So I've shown you some of the more common operations on pair RDDs. In the next session, we'll dive into joins, but I should note that other than what I've showed you in this session, and other than these join operations that you'll see very soon, there are many more operations unique to pair RDDs. To see all of the available methods that you can possibly call on pair RDDs, you can visit the pair RDDs functions page right here. This is what it's called. It's a class in the Spark's API documentation. This link should work for quite some time, but if for some reason the URLs get changed on the Spark website, all you got to do is remember that this is a class called pair RDD functions, and all of the methods inside of it are the ones that you're going to find available to you on pair RDDs. In this session, we're going to be focusing on joins. Just like in the previous session, the join operations that we'll be focusing on are unique to pair RDDs, so that means you can't call the join methods that we show you on regular RDDs, it just won't work. You may already be familiar with the concept of joins from databases, and indeed the joins found on pair RDDs are conceptually similar to those that you might have come across in databases. We're going to focus on joins in Spark in this session, which are amongst the most commonly used operations on pair RDDs. So that said, what's a join? It's pretty simple. It's just an operation that will combine two different pair RDDs into one pair RDD. So visually, it's something like this. You have two RDDs. Oops, it's one. That's two. And you want to combine them together somehow into a resulting RDD. And the way that you do that is using the join operation. There are two main kinds of joins. So on one hand we have inner joins, which is called just regular join in Spark. So the method join, just called join, refers to an inner join. And the other kind is outer join, or outer joins, which have two variants. So the method names in Spark are left outer join and right outer join. The difference between these two variants, inner joins and outer joins, only has to do with what happens to certain elements based on their keys, depending on whether both RDDs in the join contain a certain key or not. Said another way, when we try to join together two pair RDDs containing different customer IDs as the key, for example, the difference between the inner and the outer join is what happens to the customers whose IDs don't exist in both RDDs. Of course, it's easier to look at an example to better understand this difference. In this session, all of our examples are going to focus on the Swiss rail company. So Switzerland has a very famous train system, and the company behind it is referred to as the CFF in the French-speaking part of Switzerland. So we're going to focus on examples as if we are the CFF, and we're trying to make decisions about our train service based on the travel habits of our regular customers. Rail customers in Switzerland and in other European countries almost always have some kind of discount card for traveling on trains. So in Switzerland, most of the country has some kind of discount card. They pay yearly for it. For example, the card called here Demi Tarif gives a 50% discount on train fares. And there's also another one called Abonnement Général, in this case AG we call it. You pay for it and you get a free pass to take any public transit. So in this example, let's say we have two datasets collected by the CFF. This dataset is called ABOS, which stands for abonnement. It just means subscriptions. So one dataset represents customers and their subscriptions. So this should be the customers and their subscriptions here, called ABOS. And the other one represents the customers and the cities that they most frequently travel to. So this one called locations here. And in this one, you could imagine that it's perhaps collected from the smartphone app that people use to buy their train tickets on the go. So this is locations. It's a data set of customers and their most frequently traveled city. And this one is ABOS, and it's information about the customer's subscriptions. So in this case, this customer's last name is Gress, and he or she has a demi-tariff, so a half-fare card, credit card. Note that both of these data sets are pair RDDs, so I've taken a list of pairs and I've created an RDD out of it. This produces a pair RDD in both cases. So these are both pair RDDs, ABOS and locations. And an important thing to note is that it's possible for a customer to be in both data sets. So we can see here that this customer ID 101 is in both data sets. So this customer who has this AG card frequently travels to, for example, Bern. Here's a little visualization of the same data set. So in the ABOS data set, we have key value pairs where the values are pairs themselves. So these are the values here. And they represent the customer's last name, this here, and the customer's subscription or yearly subscription to the train service. For now, these subscriptions, we'll just assume that they are an instance of a case class that has no fields, so don't worry about exactly how they're implemented. Well, on the other hand, the locations dataset is a little bit simpler. It's just one pair RDD with a string as a value. In this case, the key is the customer number, and the value is the name of the city that the customer most frequently travels to. So in both pair RDDs, the keys are the customer numbers. Also note that locations is bigger than ABOS. There are more elements in locations, so both of these datasets have different sizes. And again, you could imagine that the ABOS dataset here comes from the CFF's customer database of subscriptions. And the location dataset, you could imagine, could come from months of collecting data about how registered users are using the train service from the mobile application, so on the smartphone app for buying train tickets. Importantly, this means that it's possible to be a registered user of the smartphone app, so you can be in this dataset here, but you don't necessarily have to have a yearly subscription like the 50% discount card called the demi-tariff. So it means it's possible to have people in this data set that don't yet exist or don't exist at all in this data set because they don't have any kind of yearly subscription. And vice versa, it's possible for people in the ABOS data set here to not be in the locations data set because they don't have or use a smartphone, for example, to buy their train tickets. Maybe they just buy their train tickets using a regular paper ticket machine, so that's also possible. So this is something like a real data set because there are little imperfections between the two data sets that we have to somehow take care of if we'd like to merge them together somehow. We'll be able to handle these cases using one of a few different choices of join operations in Spark. The first one we'll look at is called inner join. We'll be able to handle these cases using one of a few different choices of join operations in Spark. The first one we'll look at is called inner join. The simplest explanation of what this operation does is as follows. Inner join returns a new RDD containing combined pairs whose keys are present in both input RDDs. What does this mean? The signature here can help us out a little bit. So this method join here can be called on a pair RDD, passing another pair RDD as a parameter. It assumes that both RDDs have keys of the same type, as we can see here, and that they can have values of different types. In this case, values of type V and W. But what this operation does is it returns a new pair RDD where the value of the resulting pair RDDs is itself another pair containing both values of the two input pair RDDs. And what's most important to remember is that the inner joins are special because the resulting pair RDD will only contain key value pairs for keys that are present in both RDDs. That means that this join is kind of lossy. If there's a key in one RDD that's not in the other, it gets dropped. Of course, these things are always much clearer with an example, so let's use the dataset that we just looked at. How do we create a new RDD which can tell us which customers, 1, have both a subscription, and 2, who also use the CFF smartphone app, so we can keep track of which cities they regularly travel to. So how would you implement this value called tracked customers here? What would you do to do this? I'll give you a second to think about it. So you can probably guess that we're going to use the join method that we just introduced, right? This one called join. But first question is, which pair RDD should we call this join on? Do we call it on locations, and then do we pass abos as an argument, or do we call it on abos and pass locations as an argument? Does it matter? The answer is that no, it doesn't matter. We can just do abos join locations. And we can look at this little visualization here to get an idea of what's happening to the actual data when we do this join. So remember, the goal is to combine both pair RDDs into one pair RDD, and in particular, what we want to do is we want to put customers who have both subscriptions info and location info into the resulting pair RDD. Visually, that means that we want to make an RDD with only these highlighted elements inside of it because they exist in both RDDs. So 101, 102, 103, these customers, we've got them also in the locations RDD here. So customer 101, customer 102, customer 103 are here. So we want to make a new RDD with only these elements in it. And this is what our resulting pair RDD looks like after calling abos join locations. Remember that the value of the new key value pair is another pair representing both input values. So in this case, the first element of the value pair, so here's the values, the first element is another pair representing the last name of the customer and their type of subscription. And the second element of the value pair is the city that they frequently travel to. Do you notice anything else weird about these results? There are kind of sort of duplicates, right? Before we only had one element for this customer, but now we have one for each element that was in the locations RDD. This is because if we go back and look at the original two datasets, some customers, like 102 and 103, they have a handful of cities that they like to frequently visit. But in the abos dataset, we have just one entry per customer number. So in the resulting pair RDD, that customer info is duplicated for each different frequently visited city by that customer. So this is how the data is merged together. Oh, and remember, joins are transformations. Just like in all of the other sessions so far, if we actually want to see the resulting dataset like we saw in the previous slide, we actually have to invoke some kind of action to kick off the computation. And again, like we've done in previous sessions, we're just going to call collect on the RDDs here, on this tracked RDD, this tracked customers RDD, it's a pair RDD, and then once we get back this collection, in this case an array, we'll do for each on it and print line to just see what the results look like. But wait a minute, what happened to customer 104? Look back at this abos data set on one of the previous slides. Notice that this person is gone. Remember, there was this customer here. Customer 104 doesn't exist in the output. See? This person is missing. Customer 104 does not occur in the result because there's no location data for this person in the location data set. Remember that inner joins require keys that occur in both source RDDs, else they're dropped from the result. Let's now shift gears a little bit and visit the other kind of join. Outer joins. Said most simply, outer joins return a new pair RDD containing combined pairs whose keys don't have to be present in both input pair RDDs. So that means this kind of join is particularly useful for figuring out how to deal with missing keys between pair RDDs. This is why there are two kinds of outer joins, left outer joins and right outer joins, because it lets you decide which RDD's keys are the more important ones to keep, the ones on the left or the ones on the right of the join expression. To better understand, let's have a look at the type signatures here. They look a lot like the type signature of the inner join, with the exception of the option type here and the return type. This means that if a key isn't present in both input RDDs, the optional value could simply be none. So you have an entry still, but instead of the result being sum and then the value, you have then just none. And notice for the left outer join here, so on this one, what we have, the option is on the second element of the value pair in the result. And on the right outer join, the option is on the first element of the value pair in the result. This is how we decide which input RDD we prioritize for the keys. As usual, it's always nice to try to better understand these operations with a concrete example. So let's go back to our CFF dataset and let's try to solve a slightly different problem. So let's say the CFF wants to know for which subscribers it has collected location information. For example, we know it's possible that somebody has a subscription like a demi-tariff, but doesn't use the mobile app and will always pay for tickets with cash at a machine. Which of these two outer joins do we use? Again, let's return to our visual depiction of the data. So we want to combine both these pair RDDs into one pair RDD. We want to know for which subscriber, that means for which people in this abos data set, that we've also collected information for about location. So which kind of outer join do we choose to compute this abos with optional locations value? We can also highlight the elements that we want to keep when doing this join. So we can highlight the elements that we want to keep when doing this join. We want to make a new RDD with these elements that are in yellow. So which join do I choose, and on which pair RDD do I call that join operation? Does it matter? Think about it and give it a try yourself. Go back and look at the signatures of the outer joins if you need to, and when you look at those signatures, ask yourself which part of the resulting value pair should be the optional part. Well, the answer is that the elements from the location dataset should be the optional part of the resulting value pair. Because remember, we care about subscribers, so we prioritize the subscriptions RDD called abo. So with this information, we can now choose which join we want to use and on which RDD we want to call that join on. So since the important RDD is the subscriptions RDD called abos, that means we call join on abos. Now we just have to figure out which outer join method to use. So let's look at the type signatures. The left outer join method makes it possible for the second element of the resulting pair to be optional. So the answer is that we call left outer join on abos and we pass locations in as an argument. Here are the results visualized. Like last time, the key is the customer number, and the value is a pair, where the first element is a subscription data here, last name and subscription type, and the second element is the optional value for the customer's frequently visited city, so here. And of course, this is what it looks like when we use collect and for each to actually kick off that computation, because we can't forget the left outer join method, like all the other join transformations, they're transformations, so we have to do something like collect, some kind of action to start the computation. So said another way, since we use a left outer join, keys are guaranteed to be kept in the left input pair RDD. This is why we can see customer 104 here. That's because this customer has a subscription. He or she has a demi-tariff here, which is on the left side of the join. So the element must be kept even though there is no location data for this key, for this customer, in the location dataset. Hence why we see the value none here for the most frequently visited cities. Let's flip this problem the other way around. Let's imagine instead that the CFF wants to know for which of its smartphone app users it has subscriptions for. You can imagine that perhaps the CFF would like to offer a discount maybe on a subscription to one of these users. So maybe the CFF would like to identify the people who use the mobile app but don't yet have a demi-tariff subscription, and they maybe want one. So which outer join should we use, and which RDD should we have on the left and on the right side of the join operation to find these users? Visually, that means we want this part of the dataset. That is, we don't care about customer number 104 because that customer doesn't use the smartphone app. Therefore, we want to make a new RDD with only these elements. Which join should we use, and on which pair RDD should we call the join on? Of course, the slide gives the suggestion away. Let's just try to use the right outer join. Why? Remember the signature of the two outer joins. For the right outer join, the optional element is the first element of the resulting pair. In our case, that would be the value from the abos dataset, which is the less important dataset in the join. Since we're focusing on smartphone users, we want to make sure that we keep every key/element of the locations datasets. Therefore, we should do abos right outer join locations. This is what the resulting combined dataset looks like after calling abos right outer join locations. This result isn't the most interesting result because there is no customer which uses the mobile app but which doesn't have a subscription already. If there was, we would see at least one element where rather than this optional sum here, last name subscription, we would just see type none, and then the cities that customer frequently travels to. Here's what it looks like printed out after calling collect and for each print line. What's important to note is that we lose customer number 104 again, you see, because that customer number is not in the right side of the join, so it gets dropped. We don't need it, so it doesn't end up in the resulting join dataset. Phew, so those were the different kinds of joins in Spark. In this session, we're going to try and wrap our minds around something that is inevitable that we might not have considered when writing Spark programs thus far. It's called shuffling, and it can happen quite a bit. You never call a method called shuffle, but as we're going to see, there are many methods which transparently cause shuffles to happen. We're going to dive into some of those scenarios in this session. So let's first start by looking at a group by or a group by key operation. For a moment, just try to think about what these methods do and what might happen when one of these methods are called. Importantly, you can't forget that our data is distributed. Now think again about what a group by or a group by key does now with the fact that our data is distributed in your mind? Or what about when you've been using Spark on your own? Did you notice anything when playing around with Spark for your programming assignments about the types when you use group by or group by key? Here's a very quick example. Here we just make a pair RDD and then we call group by key on it, and this is the return type that Spark gives us. It's something called a shuffled RDD. That's weird. To do a distributed group by key, we typically have to move data between nodes so that the data can be collected together with its key in a regular, normal, single machine Scala collection. Remember that group by key collects all of the values associated with a given key and stores them in that single collection. That means that data has to move around the network, and doing this, moving the data around the network, is called shuffling. What's important to note is that shuffles happen. They happen transparently as a part of operations like group by key. And what every Spark programmer learns pretty quickly is that these shuffles can be an enormous hit to performance because it means that Spark has to move a lot of its data around the network. And remember how important latency is. Let's try to better understand what's really happening when we do operations like group by key. As usual, we'll look at an example to help clarify. Let's assume we have a case class called CFF purchase, which contains 3 fields: an integer for the customer ID, a string for the destination city, and a double representing the price of the ticket that's been purchased as a part of this CFF purchase. And remember, the CFF is the Swiss train company. Assuming that we have an RDD that's full of purchases made in the past month, let's try to calculate how many trips and how much money was spent by each individual customer over that last 1 month period. So with all of the knowledge that you have so far, what would you do? Which methods would you use? We've been working on pair RDDs quite a bit now, so perhaps the first step is to make a pair RDD. Okay, but what other methods do you use? I'll give you a moment to try and figure it out yourself. Since the end goal of this example is to try and figure out how many trips each customer has made this month and how much money they spent over the month, the destinations that they've gone to in each purchase isn't important, so we'll drop that when we make our new pair RDD here. We'll have as the key the customer ID, and as the value the price of the purchase that this case class instance represents. Next, since the goal is to focus on each individual customer and to then calculate the number of trips they've made and how much money they've spent in the past month, it would make sense to group together all of the purchases per customer. So in that case, we reach for good old group by key, which returns a pair RDD with a collection of values that correspond to the values that go along with each key. So now we have a pair RDD where customer ID is the key, and then a collection of all of the purchase prices of that customer's purchases over the past month is the value. So we have almost everything we need now. The last step is just to figure out how many purchases were made per customer and how much money was spent in total by each customer. What method should we use next? We can use a simple map, or we can even use mapped values. Here I've used map, but map values also works just fine. All we have to do is make a new pair containing the number of purchases as the first element of the pair, which is easy to do. We can just call size on the collection of values. And for the second element of the pair, we just need to sum up all of the prices in the collection. So we can simply call the method sum on the collection of values. And finally, since none of the methods we called so far are actions yet, we have to call an action just to kick off the computation. So in this case, we call collect to collect all of the results onto the master node. Now that we understand an example solution to this problem, let's step through what's really happening with the data, given some sort of example data set. So here, let's imagine our purchases are this short list of instances of CFF purchase. How might the cluster look with this data distributed over it? So let's start with the data in the purchases RDD. Let's imagine that we have 3 nodes, this one, and this one. And we split up our data over these 3 nodes evenly. So since we have 6 data elements in the purchases RDD, that means for the sake of this example, we can put 2 elements on each node. So 2 here, 2 here, and 2 here. Let's, for a second, imagine that the map function is executed on this data, thus producing a set of pairs on each node. Because remember, after we had these CFF purchases, what we did was we created a pair RDD. So assuming that was eagerly executed, it would look like this. So remember in our code example, we got rid of the destination cities and we kept only the customer ID number and the price paid per purchase as the key and the value in our key value pairs. So now we went from 6 instances of CFF purchase to 6 instances of key value pairs, 2 on each of the 3 nodes. Now if we look back at the code in the example, the next step was to do a group by key. And remember, group by key results in a single key value pair per key. So think about it. Therefore, a single key value pair cannot span across multiple worker nodes. So let's go back to our visualization of the cluster. What does group by key look like in this case? Remember, we have concrete instances of data, so how would this data have to move around? Well, as you might have guessed, to create collections of values to go with each unique key, we have to move key value pairs across the network. We have to collect all of the values for each key on the node that the key is hosted on. So in this example, we've assumed that since there are 3 unique keys and 3 nodes, each node will be home to one single key. So we put 100 on this node, 200 on this node, and 300 on that node. So then we move around all of the key value pairs so that all purchases by customer number 100 are on this node, and all purchases by customer number 200 are on this node, and all purchases by customer number 300 are on this node, and they're all in this value, which is a collection. This highlighted part here is where all of the data moves around on the network. This part of the operation is the shuffle. And I'm just going to step back to one of the slides from the beginning of the course about latency. Remember the humanized differences between operations done in memory and operations that require sending data over the network? The humanized difference between these two kinds of latency was, on the one hand, seconds to minutes, and on the other hand, up to years. With these numbers in mind, of course we don't want to be sending all of our data over the network if it's not absolutely positively required. Having to do a lot of network communication kills performance, especially if it's being done unnecessarily. So this is why shuffling is bad. We want to do as little shuffling as possible because of these orders of magnitude. So how can we do a better job? What can we do differently to make this example more performant? After all, if we want to do a group by key kind of operation, we definitely have to move data over the network. But can we somehow do it in a more efficient way? Perhaps we can reduce before doing the shuffle. This could potentially reduce the amount of data that we actually have to send over the network. To do that, we can use the reduce by key operator. Do you remember this one? We learned about it in one of the previous sessions. And remember, you can think of it as a combination of first doing group by key and then reducing over all of the values that were grouped by that key in those collections. And I also told you back when we covered this method that this one was much more efficient, but I didn't show you how yet. We'll look at exactly how this is more efficient in the next example. But first, let's recall reduce by key's type signature. Remember, since it operates on the values that you assume are already grouped by some key, we focus only on the types of that value. So the function passed to the reduce by key operator only operates on the value part of the key value pair. So let's go back to our earlier example. Remember, our goal was to figure out how many trips and how much money was spent by each individual customer over the course of the month. So if we were to replace our call to group by key with a call to reduce by key instead, what would we have to pass to reduce by key? What would the function be here that would have to calculate the total number of trips and the total amount of money spent by each customer? Note, to make things a little easier for you, I changed the function that I've passed to map here, so it's a little different than it was in the previous example. Now, instead of a pair RDD with only the customer ID and price, I've also added an integer 1 here to make it easier to do the count of the purchases later. So given that, what should the functional literal be that we pass to reduce by key in order to get a result that looks like this? A pair of customer ID with a value that itself is a pair of trips, comma, total money spent. Remember that type signature I just showed you for the reduce by key operator. We're reducing over the values per key. And since our values are types integer double, where here we have the price and here we have an integer that we can count up, the function that we pass to reduce by key must reduce over two such pairs. I'll give you a moment to try and come up with a solution with this information now available. The solution is pretty simple. Since the values that we're reducing over are pairs, where each element of the pair must be summed with the same elements of the adjacent pairs, all we have to do is sum up the two first elements of the adjacent pairs, then we have to sum up the two second elements of the adjacent pairs, and finally kick off the computation with collect here. So all we're doing is summing up the first two elements and summing up the second two elements in the pairs. So we're adding together 1 plus 1 in this case, and some price plus some price in this case. And after that, we just have to invoke some kind of action to kick off computation, and that's it. So what might that look like on the cluster we just visualized? Going back to our visualization, note that I updated the result of the map. So we now have what we've been working with here with this extra integer there. What happens with this data on the cluster for this code example now? Well, since reduce by key reduces the data on the mapper side first, the pairs on our 3 nodes are reduced and they look like this. So here's before, here's after. So what we had was 2 elements with key 100 on this node, 2 elements with key 300 on this node. We could reduce them together into a single element that looks like this. Notice that the logic in our reduce by key was essentially applied on the mapper side first. Imagine if this was a real data set with millions or billions of elements on each node. Now we have at most 1 key value pair per node. So that's potentially a very large reduction in the amount of data that maybe we have to shuffle. The idea is that hopefully we're shuffling less data now, and then we do another reduce again after the shuffle. And in the end, we should have the same answer, but we should have arrived at that answer in considerably less time, because the goal here is to reduce the amount of network traffic caused when we do one of these operations. So just to summarize, what are the benefits of this approach? Well, by reducing the dataset first, we can reduce the amount of data that's sent over the network during the shuffle, which could mean pretty significant gains in performance. And to make this all a little more concrete for you, I've performed this computation, the exact same code, on a real cluster, and we can easily see the gains in performance. This is done with billions of generated key value pairs representing the same datasets in the same code we just on the previous slides on a cluster of, I believe, 6 nodes. This was run in a Databricks notebook, and what we can see here is the amount of time it took to do the same computation with a group by key versus with a reduce by key. And as we can see, the group by key variant, this is exactly what we saw on one of the previous slides, the group by key variant takes 15.48 seconds to complete. Well, the variant using reduce by key, like I said, same as we had on one of the previous slides, takes only 4.65 seconds to complete. In this example, the reduce by key version of this program is up to 3 times faster than the group by key version. Imagine if this was an hours-long computation. This would mean a lot of saved time on a big data set. So I think we have a little more intuition now about how all of this works. The bottom line is that if we use operations like group by key a lot, the act of grouping all of the keys with their values requires us to move the values to be on the same machine with their corresponding keys. The one big question that we haven't yet asked is how on earth Spark knows which key to put on which machine. We just assume that Spark is doing something sane and is spreading the data out evenly, but how does that really work? Well, the answer is partitioning, and how this works we'll cover in depth in the next few sessions, and partitioning can make a big difference to how fast your job completes. In this session, we'll cover something called partitioning, which comes into play when shuffling data around a cluster. Partitioning your data intelligently can often save you lots of time when running computations. It's important to understand in general with distributed systems, and in particular when dealing with Spark RDDs. In the last session, we focused most of the session on a specific example involving the group by key operation. We saw that using this operation causes data to be shuffled over the network. This is because to group all of the values with their corresponding key, you've got to move all of the values to the same machine. But we ended last session asking ourselves, well, wait, I understand we have to move data around the network so some data is all on the same machine, but how do we know which machine to put which key on? So before we try to optimize that example that we saw in the last session any further, let's take a detour to learn more about what partitioning is and how it works in Spark. So let's first start with partitions. What are they? Simply put, the data within an RDD is split into many partitions. And partitions are very rigid things. Most importantly, they never span multiple machines. This is super important. Data in the same partition is always on the same machine. Another point is that each machine in the cluster contains at least one partition. Sometimes more, sometimes exactly one. Actually, the number of partitions is configurable, by the way. We'll learn about when and how the number of partitions can be changed by the user, though by default, when a job starts, the number of partitions is equal to the total number of cores on all executor nodes. That's the default. So for example, if all of the machines in your cluster have 4 cores, and you have 6 worker nodes, then that means the default number of partitions you can start with may be 24. And importantly, Spark comes with 2 out-of-the-box kinds of partitioning, which makes sense for different sorts of applications. These are hash partitioning and range partitioning. We'll talk about these in more detail in the next few slides. However, it's important to note that all of this talk about customizing partitioning is only possible when working with pair RDDs, since as you'll see, partitioning is done based on keys. So we partition based on keys, hence we need a pair RDD to do that. So let's start with hash partitioning. To illustrate this first kind of partitioning, let's return to our group by key example that we saw in the previous session. As we saw in the last session, by default in this example, hash partitioning is used. But what is it? How does it work? What does it look like? The way it works is like this. Since group by key knows it has to move all of the data around the cluster, its goal is to do that as fairly as possible. So the first thing it does is it computes the partition P for every tuple in the pair RDD. So we start by getting the key's hash code, and then we modulo that with the default number of partitions. So we said it was 24 in the last slide. And whatever the answer is of this computation is the partition that key goes onto. Then, when we actually do the hash partitioning, the tuples in the same partition are sent to the machine hosting that partition. So again, the key intuition here is that hash partitioning tries to spread around the data as evenly as possible over all of the partitions based on the keys. The other kind of partitioning is called range partitioning. This is important when some kind of order is defined on the keys. So examples would include integers or chars or strings. We have lexicographical ordering on strings, for example. And if we think about our previous examples where we were working with pair RDDs that had keys that were integers, we could hypothetically range partition these keys. For these kinds of RDDs with keys that can have an ordering, range partitioning could be an efficient choice for partitioning your data. Intuitively, though, that means when you're using a range partitioner, keys are partitioned according to 2 things. They're partitioned according to some kind of order, so like I said, a numerical order or lexicographical ordering, as well as a set of sorted ranges for the keys. So you have groups of possible ranges that the keys can fall within. And that means that tuples with keys in the same range will appear on the same nodes. Let's look at a more concrete example of each kind of partitioning. And let's start with hash partitioning. So consider we have a pair RDD with these keys. So we don't care about the values for now, but these are the keys that we have in our pair RDD. And let's say our desired number of partitions is 4. Also, just to keep things simple, let's assume that the hash code function is just the identity function for this example. And let's remember that to compute the partition, what we do is we call the hash code on the key, which, like I said, in this case is just the identity function, and we modulo that with the number of partitions. So in this case, this will simplify to just the key modulo 4 for the sake of this example. So let's compute the partitions that these keys belong in. So if we try to compute the partitions for each of these keys, and we use the formula on the slide previous, like this, then something wonky happens. This hash partitioning distributes our keys as follows amongst our 4 partitions. Remember, the goal of hash partitioning is to try and evenly spread out the keys, though it's possible to have situations like these where you have an unlucky group of keys that can cause your data on your cluster to be unevenly skewed, and for some nodes to have a lot more data and some nodes to have none or a lot less. Of course, this means potentially bad performance because a job could be evenly spread out on 4 nodes, and in this case, it's basically just spread out on 1 node right now, so it's not really very parallel. In this case, since we know the hash partitioning is actually skewed, and since our keys have an ordering and are non-negative, we can use range partitioning to improve the partitioning and to even it out significantly. So assuming that there are a set of ranges for 4 nodes, for example, for customer IDs 1 to 200, on the first node, customer IDs 201 to 400 on the second node, customer IDs 401 to 600 on the third node, and customer IDs 601 to 800 on the fourth node. This would enable us to distribute the keys more evenly across our partitions. So here's a scenario where we can more easily distribute our keys throughout the cluster. That is, we just put the keys in their corresponding ranges. So all keys between 1 and 200 on the first node, all keys between 201 and 400 on the second node, etc. This is clearly much more balanced, and of course we could imagine it being much more performant than before because the work is more evenly spread out. Okay, but what if I want to customize how my data is partitioned? We illustrated the concepts behind the hash and range partitioning, but we haven't seen yet how to customize and set partitioners for any of our Spark jobs yet. Well, there are two ways to create RDDs with specific partitionings. First, you can explicitly call the method partitionBy on an RDD, and you can pass in an argument, which is an instance of some kind of partitioner. Or second, you could just keep track of the transformation that you use on your RDDs because certain transformation use certain kinds of partitioners. So if you know the partitioner associated with the transformation you're using, you can also customize the partitioning of your data that way. But let's first look at the partitionBy method. So if you try to customize your data partitioning by using the partitionBy method, the result is that partitionBy creates a new RDD with a specified partitioner. So let's imagine for a second that we have this RDD of purchases that we've been working with in the previous sessions. And let's say that we want to use a range partitioner on it now. To do this, we first need to create an instance of a range partitioner here. This is done by calling new range partitioner and passing in the number of partitions that we want, in this case 8. And we also have to pass a reference to an RDD that we'd like to have partitioned. In order to come up with these ranges, we need to sample the RDD that we'd like to have partitioned, so that's why we have to pass in pairs here. Spark will take pairs and sample it to figure out what the best ranges are. Now we simply invoke partitionBy on the pairs RDD, and we pass in the new range partitioner that we just created. Do you see anything else interesting on this slide? I'll give you a moment to think about it. Yes, it's this call to persist here. Why would it be desirable to call persist here? Well, the answer is, due to Spark semantics and tendency to reevaluate chains of transformations again and again and again, this data would be shuffled over the network and partitioned again and again and again if we don't tell Spark. Basically, what we're doing here is we're saying, hey, once you move the data around on the network and repartition it, just keep it where it is, persist it in memory, else you could easily find yourself accidentally repartitioning your data in every iteration of a machine learning algorithm completely unknowingly. So just to repeat, to create a range partitioner, you must simply specify the desired number of partitions, and then you must provide a pair RDD with keys that are ordered so that Spark is able to sample the RDD and create a suitable set of ranges for it to use for partitioning based on the actual dataset. And again, I can't remind you enough, the results of partitionBy should always be persisted. Otherwise, partitioning is repeatedly applied, which involves shuffling each time the RDD is used, and of course you don't want this to happen. Earlier in the session, I mentioned that it was possible to partition using transformations as well. There are two ways partitioners can be passed around with transformation. In the first case, and probably the most common case, partitioners tend to be passed around via parent RDDs. That is, pair RDDs, which are the results of a transformation on an already partitioned pair RDD, is typically configured to use the same hash partitioner that was used to construct its parent. The other case, where transformations can actually provide a new partitioner, is when some transformations automatically result in an RDD with a different partitioner. Of course, this is usually when it contextually makes sense. So for example, if you use the sort by key operation, a range partitioner is used because you need ordered keys in order to sort them. And it makes sense that the keys, once sorted, are partitioned such that the similar keys are in the same partition. Conversely, the default partitioner when using group by key is a hash partitioner like we saw in an earlier example. Here are a list of transformations that either hold on to or propagate some kind of partitioner. This is important to remember because it could bite you for performance reasons later. These are operations that could result in a completely different partitioning for your data. So it's important to remember that by just using some kind of transformation, that something like this can happen transparently under the hood. One big thing you should notice, though, is that a certain function that you use all the time is not on this slide. That's right, map is missing, and so is flat map. Why aren't they on this list? Interestingly though, flat map values and map values are on this slide, and filter as well, and in these cases, these three operations hold on to their partitioner if their parent has some kind of partitioner defined. Otherwise, any other transformation operation that's not on this slide will produce a result that doesn't have a partitioner. And that includes map and flat map. If you use map or flat map on a partitioned RDD, that RDD will lose its partitioner. That could really screw things up. Just think about it for a second. If you've gone to great lengths to try and organize your data in a certain way across your cluster, and then you use an operation like flat map, then you lose all of that partitioning, and your data might be all moved around again. But let's focus on this point right here for a second. Why is it that all other operations will produce a result that doesn't have a partitioner? Why does that make sense? Think about the map transformation for a moment. Assuming we have a hash partitioned RDD that we intend to map on, why would it make sense for the resulting RDD to lose its partitioner in its result RDD? Think about all of the things you could possibly do in a map operation, and remember that partitioning only makes sense for pair RDDs, which are key value pairs. I'll give you a moment to think about it. Well, that's because it's possible for map or flat map to change the keys in a pair RDD. Here's an example. We can take a very intelligently crafted data set, called RDD in this case, and we could accidentally replace all of the keys in the entire data set with the same key, which is just the string dope. We can do this intentionally or accidentally, doesn't matter. So therefore, if the map transformation was able to preserve the partitioner in the resulting RDD, it may no longer make sense because maybe the keys are now different. So if I have some partitioner that makes sense, therefore if the map transformation was able to preserve the partitioner in the resulting RDD, it may no longer make sense because now the keys may be different. So they would no longer correspond to the correct partitions anymore. That should make sense with this dope thing, right? Because if I had some keys that made sense before and then I just replaced them with dope, then what? Now the partitioner doesn't correspond to the keys that I have. This is why the map values operation is so important. And this is why you should generally try to use it if you can. So if you're ever working with a pair RDD, you should try to first reach for map values. This operation makes it possible for us to still do map transformations while making it impossible for us to change the keys in a pair RDD, thus making it possible for us to keep the same partitioner around. That's clever, right? So if we do all of this work to intelligently partition our data across our cluster, we can still do a map operation, and we can still keep the partitioner around that corresponds to how our data is organized by using the map values function. That's great. In the next session, we'll continue learning about how partitioning can significantly reduce data shuffling and how it can be a really huge boon for performance if tuned carefully. In this session, we'll dig a little bit deeper into partitioners, and we'll cover why someone might want to use a partitioner. So far, we've seen the different sorts of partitioners, but we've not seen why they should really be used. In the last session, we saw that Spark makes a few different kinds of partitioners available out of the box to users. These were hash partitioners and range partitioners. And we got a little bit of a sense of when one might be used versus the other. We also looked at the sorts of operations that either may introduce new partitioners, or which may carry along an existing partitioner, or which could even completely discard a partitioner. Said simply, the biggest reason why someone would want to care about partitioning is because partitioning can bring enormous performance gains, especially in the face of operations that may cause shuffles. The basic intuition is that if you can somehow optimize for data locality, then you can prevent a lot of network traffic from even happening. We know that network traffic means huge latencies, so partitioning can mean significantly reduced latencies, which of course translates into better performance. As usual, let's look at an example to see how much partitioning can actually help performance. Let's return back to this group by key versus reduce by key example that we saw in previous sessions. When we left off with this example, we were pretty happy with the 3x performance boost from using reduce by key instead of group by key. However, we can still do better than that. You might not believe it, but we can use range partitioners, and we can optimize our earlier use of reduce by key so it doesn't even have to involve shuffling over the network at all. Here's how we do it. All that we've done differently in this example is that we've started by partitioning our initial dataset. So all of this right here, this is still the same from before. So we start by creating a simple range partitioner here. It has 8 partitions, because perhaps this number of partitions makes sense for our cluster. And then we pass into our partition by function this range partitioner that we just created. And finally, we persist this newly partitioned RDD. Then we just do the same thing that we did previously. We make a pair RDD, and then we use the reduce by key, and that's it. Seems simple enough, but how does it compare when we run it on the cluster? Well, it's significantly faster. This is the result here. We have almost a 9x speedup over the group by key version. So 9x speedup over this one here. So imagine instead that these computations weren't running in seconds, but they were running in minutes or hours. This 9x speedup is a pretty big difference then. Okay, so let's look at another example. This one comes from the Learning Spark book, which is a really great book. And you can find this example on pages 61 to 64 of the Learning Spark book. So let's imagine that we have an application. And let's say that this application is a media application where users can, for example, subscribe to topics for articles. They want to read articles, so they say, I'm interested in a certain topic. And let's imagine that in this application, we have a huge table of user information, and we store that big table in memory in the form of a pair RDD. We can call this big data set user data here. And since it's a pair RDD, its key is a user ID and its value is user info, where user info contains a list of topics that the specific user is subscribed to. Now, imagine every now and then this application has to combine this big data set of user data with a smaller data set representing events that have happened in the last 5 minutes. We'll call the smaller data set events here, and it too has key user ID, but its value instead is of type link info here, which represents which links that user has clicked on in the past 5 minutes. And in this example, we may wish to count how many users visited a link that was not related to one of the topics that they've subscribed to. So this is kind of reminiscent of the CFF application that we saw in previous sessions. We know that we're going to have to join these two datasets somehow, because we're going to want to group the user info to the link info for those users that have been active in the past 5 minutes. So what might this program look like? Well, here's the full thing implemented on one slide. Of course, the most important part is this line here, where we take the user data and then we do an inner join with events. Now we have a new pair RDD called joined, which contains all of the users that have been active in the past 5 minutes and what they've been clicking on. Now all we have to do is filter that data set down to figure out if people are clicking on things that they're not subscribed to, so we do that here. And finally, we just count it up to see what that number is. So what do you think about this program? Does it seem alright? Logically, it seems like it should do what we want it to do, right? Well, although it might do the right thing, logically, it'll be really inefficient. This is because each time this function, here, this process new logs function, is invoked, the join has no idea about how any of the keys are partitioned in those datasets. So all that Spark can do is hash all of the keys of both datasets and then send the elements with the same key hash across the network to be on the same machine. Then once that's done, it can join together the elements with the same key on that machine. And it does this every time this method is invoked, even though this really huge pair RDD called user data doesn't change. So there's no reason to keep sending this thing around if it's always the same, right? It shouldn't have to keep moving all of this data around the network. To give you some sense of what this looks like, here's a little diagram. This is the user data dataset, and then you have the joined dataset here. Basically what's happening is that we have this big shuffle between user data and joined. While it might not seem like it, fixing this is actually quite easy. As you might have guessed, all we have to do is partition the really big user data RDD right at the beginning of the program. So you remember here, we create the user data RDD. So all we have to do is add these two lines here to user data. That is, we just call partition by, and we pass to it a new hash partitioner with some fixed number of partitions. In this case, we say we want 100 partitions. And after that, all we have to do is just persist the user data. So since we called partition by while we were building up user data, Spark now knows that it's hash partitioned. And therefore calls to join on this user data thing here can take advantage of this partitioning. So now when we call user data join events, like this here, when we do user data join events like we saw in the original program, Spark only has to shuffle the event RDD, sending events with specific user IDs to the machine that contains the corresponding hash partition of user data. So the bottom line is that the tiny pair RDD event, the event one, the small one, should now be the one that's shuffled and not the big RDD full of user data. Or shown more visually, now that the user data pair RDD is pre-partitioned, Spark only has to shuffle the events RDD. This means that events with specific user IDs are the only ones that have to be sent to machines with corresponding hash partitions of user data. No more shuffling that big user data RDD. Now let's look back to our example using group by key. Let's try to understand a little bit about what's happening with these partitioners under the hood. We recall that grouping all of the values of the key value pairs of the same key requires collecting all of the key value pairs with the same key on the same machine. That's a mouthful. By default, grouping is done using a hash partitioner with the default parameters. And then the resulting RDD is configured to use that same hash partitioner that was used to construct it. This is what's going on under the hood. At this point, you might be asking yourself, well, goodness, how do I know when a shuffle will occur? Well, there's a simple rule of thumb to try and remember to determine when a shuffle might occur. A shuffle can occur when the resulting RDD depends on other elements from either the same RDD or another RDD. So certain operations like join, just given how they fundamentally work, the idea is that they should be depending on data from other parts of the same RDD or other RDDs. This should, by default in your mind, trigger some sort of warning that, aha, shuffling could occur. What can I do to reduce it? And of course, the answer is that if you intelligently partition your data, you can either greatly reduce or completely prevent shuffling from occurring. There are also other tricks and even methods that can help you figure out when a shuffle has been either planned or executed. On the one hand, you could look at the return type of certain transformations like we saw earlier in this session. Sometimes you might see a return type called shuffled RDD here. Of course, this is evidence that a shuffle has either already happened or is planned. There's also this very handy method called toDebugString that you can call on an RDD to see its execution plan. This will give all kinds of information about how your job is planned, and you can keep an eye out for warning signs like these shuffle RDDs here. But perhaps the best thing to do is just keep in mind which operations might cause a shuffle. You can usually tell by logically thinking through what the method does. In any case, here's a handy list of operations that might cause a shuffle. Of course, the usual suspects are here. We have the different kinds of joins, we have the group by keys, reduce by keys, combine by keys, and then there are other operations like repartition or coalesce. And as their names suggest, these operations sound like they have something to do with partitioning, so of course if they're partitioning data, they're going to be moving data around. These are the sorts of operations that may possibly cause a shuffle. However, if I've hammered anything into your head during this session, the one thing that you should try to remember is that it's possible to sometimes avoid a network shuffle by partitioning. There are two common scenarios where you can avoid network shuffling by partitioning. The first is when you use an operation like group by key on pre-partitioned RDDs. So this example here. This causes values to be computed locally since they've already been pre-partitioned or pre-shuffled, so to speak. So the work can all be done on the local partitions on the worker nodes without workers having to shuffle their data again to one another. And in this case, the only time that data has to be moved is when the final reduced values have to be sent back from the worker nodes to the driver node. The other common scenario here has to do with pre-partitioning before doing joins. So we can completely avoid shuffling by pre-partitioning the two joined RDDs with the same partitioner. Of course, we must also ensure that the pre-partitioned RDDs are cached following the partitioning, of course. This makes it possible to compute the entire join locally without any network shuffling, since the data that must be joined together from both pair RDDs has already been relocated to live on the same node in the same partition, so you don't need to move the data around in this case. So if you take anything away from this session, you should remember that how you organize your data on your cluster really matters. You can go from repeatedly shuffling large data sets while trying to join it with a smaller data set to not having to shuffle any data at all just by organizing and partitioning your data intelligently from the beginning of your job. And remember that we saw speedups of up to around 10x on small examples by just trying to ensure that data isn't transmitted over the network to other machines, and when it doesn't have to be. If we think back to the latency numbers that we learned in the first week, you should have the intuition that this 9-10x speedup could make a big difference in your day-to-day work. If you're trying to run a job that should complete in 4 hours, but you miss an opportunity to partition data or optimize away a shuffle, it could take 40 hours instead. So this is why partitioning is important. In this session, we're going to focus on wide versus narrow dependencies, which dictate relationships between RDDs in graphs of computation, which we'll see has a lot to do with shuffling. A recurring theme lately has been that not all transformations are exactly equal. Some are a lot more expensive in terms of latency than others. For example, some might require lots of data to be transferred over the network, perhaps unnecessarily, so operations that cause a shuffle are an example of this. In order to better understand when shuffling might occur, we have to look at how RDDs are represented, and then we have to think carefully about the operations that we're calling on our RDDs to understand when a shuffle might occur. We'll actually see that this unique way of representing RDDs actually makes fault tolerance possible in Spark. So we mentioned in earlier sessions that Spark is fault tolerant. We'll get a glimpse of how that's possible and actually kind of easy. So let's start with some terminology. Let's start with lineages. So if you think about a group of computations that are done on an RDD, we can call that group of computations a lineage graph. That is, when you do operations on an RDD, the operations can be organized into a directed acyclic graph representing the computations that were done on that RDD. So here's an example. We start with some input RDD, then we call a number of operations on that RDD. We can then reuse one of these RDDs in two subsequent computations. So we can reuse this filtered RDD in a count, and we can also reuse it in a reduce. If you try to visualize it, it makes a graph like this. And RDD is the RDD that's actually made from this input file. We can then do map and filter these transformations here on that RDD, and we'll get back a new RDD called filter, which we can persist in memory. And then we can use that filtered RDD in two different ways, with a count and with a reduce operation. This forms a graph of computations, a tree, without cycles. That's why it's called a directed acyclic graph. In Spark, these graphs, or DAGs, are referred to as the lineage graph. That means it's possible to step back up this graph to figure out how the result of this count operation is derived from input file. These lineage graphs are a big part of how RDDs are represented in Spark. And in fact, Spark can actually analyze this representation and do optimizations. We'll see what that means in a moment. But first, let's look at how RDDs are represented. So let's start with a visual example. Let's assume that this block here is an RDD. Usually we think of RDDs as some kind of abstraction that we invoke methods on. But an RDD itself is actually made up of partitions. Partitions are atomic pieces of the dataset, and they may exist on one or many compute nodes. So you might have one RDD spread out over many compute nodes, and all of the pieces that are spread out are the partitions. The next most important part of an RDD are dependencies. Dependencies model relationship between an RDD's partitions and the partitions that it was derived from in other RDDs. So for example, in this picture, if this is a parent RDD and this is a child RDD, and we're calling a map function on this RDD to get that RDD, then the dependencies are how these partitions map to those partitions with the map function. So while you might normally think of a map as one big arrow between this RDD and that RDD, actually dependencies model the relationship between some partitions and the partitions that they were derived from. So you could say in this picture that this partition was derived from that partition, this partition was derived from that partition, and so on. And finally, the last two parts of an RDD include a function. So you can think of this as the function that you might pass to a map operation on the previous slide. You can't compute a child partition without some kind of function to get that child partition from the parent partition. So functions are actually a big part of RDDs because they say how to compute the dataset based on an RDD's parents, so what to actually do. And finally, there's some metadata about the partitioning scheme and where data is placed that's a part of an RDD. So these are the four parts of an RDD. But you might ask, well, how does that relate to shuffles? If you recall, in a previous session, we developed the following rule of thumb. We said a shuffle can occur when the resulting RDD depends on other elements from the same RDD or another RDD. So here's a key word, depends. Now we have an idea of what a dependency is. In fact, an RDD's dependencies actually encode when data must move over the network. So that brings us to transformations. So we know that transformations cause shuffles, and we know that dependency information can tell us when a shuffle might occur. To differentiate between these, we can actually define two sets of dependencies called narrow and wide dependencies that can tell us when shuffles will happen. We're going to go more into depth about what a narrow dependency and a wide dependency means in this session. So let's define narrow and wide dependencies. A transformation has narrow dependencies when each partition of the parent RDD is used by at most one partition of the child RDD. So that means some child partition has only one parent partition, and not many. A transformation that has wide dependencies, on the other hand, is one where each partition of the parent RDD may be depended on by multiple children partitions. So that means you may have many child partitions, which were all derived from a single parent partition. Transformations with these kind of dependencies have wide dependencies. So what does that mean to us? Well, as you might have guessed, Transformations with narrow dependencies are typically quite fast. They require no shuffles, and optimizations like pipelining can occur, which is when you can group together many transformations into one pass. And as you may have guessed, transformations with wide dependencies are slow because they require all or some data to be shuffled over the network. So these are the transformations that cause shuffles. So let's try to visualize the differences between narrow and wide dependencies. Let's start first with narrow dependencies. So as I said on the previous slide, each partition of the parent RDD is used by at most one partition of the child RDD. So some example transformations include map and filter, because one partition depends on at most one other partition. And the same is true for union. We can essentially just put the data in this partition into the new resulting RDD here. There's no relationship between many RDDs when it comes to looking at who this partition was derived from. And what might surprise you is that this is also true for joins that are already partitioned. So if we recall in previous sessions how we actually were able to create joins where shuffles weren't required, this is the sort of join which has a narrow dependency. But just to go back to the definition of a narrow dependency, join with co-partitioned inputs is a transformation with narrow dependencies because each partition of the parent RDD is used by at most one partition of the child RDD. That is, this child dependency here is derived from only one partition in one of the parent RDDs. Said another way, we don't have an arrow going from this partition to that child partition and then also this partition here going to that same first child partition. We have just one relationship. This partition relates to that partition and that's it. On the other hand, transformations with wide dependencies, as we said on the previous slide, is when each partition of a parent RDD may be depended on by multiple child partitions. So one operation that we already know causes shuffles is group by key. Now when we visualize group by key with partitions and dependencies, we can see how a shuffle will occur. As the definition here says, we have parent partitions, which are depended on by multiple child partitions. So for example, this partition is depended on by both of the children partitions. So these are wide dependencies. Another operation with wide dependencies, of course, is join, when its inputs are not already partitioned. This means that we're going to have to move data all over the network to make sure that the resulting RDD has all of the values corresponding to some key on the same partitions. Before the join is called, they could be spread all over the network. So this is a pretty clear example of an operation that has wide dependencies, a join without already partitioned inputs. So let's take this visualization a step further and let's visualize an example program and its dependencies. So let's assume that we have the following DAG, the following graph of computations, where each one of these here are RDDs, right? So we have this big box is an RDD, this one's called A, this one's called B, this one's called C, D, E, F, G. They each have different numbers of partitions, so A has 3 partitions, C has 2 partitions, and these big arrows here represent the operations that we're calling on these RDDs. So A is the parent RDD, and B is the child RDD, and the operation that B is derived from is group by. So here's a quick exercise for you. If you had to draw the dependencies between each of these RDDs, what would they look like? Which dependencies are wide, and which dependencies are narrow? Try it for yourself. Try to draw it out on a piece of paper and think very carefully about what functions like group by and map actually semantically do. Ask yourself how many dependencies each one of these partitions might have on their parents. Well, here's the answer. If you think very carefully about what group by has to do, it has to group values by the same key in the resulting RDDs. So it has to move key value pairs around the network in order to make sure that they're all in the same partition, which means that many of the parent RDD's partitions are used in each partition of the child RDD. Operations like map have only one dependency. So this partition depends on only that partition, and it doesn't matter what's in this partition. So the next question I asked you are which dependencies are wide and which are narrow. Transformations like group by and join are wide because each child partition depends on multiple parent partitions. And transformations like map and union are narrow because each child depends on only one parent RDD. There's a one-to-one relationship between parent partitions and child partitions. Well, hang on a second, you might be asking yourself, well, why is this side of the join narrow? And the simple answer is that if you looked at the code, you probably cached B in memory because you knew you were doing a group by key, which does partitioning already. So you want to keep that partitioning in place when you reuse B. So said simply, B then is already co-partitioned. It's already partitioned and cached in memory following the call to this group by here. That's why this part of the join can have narrow dependencies. So I hope those visualizations were an aha moment for you when thinking about computations that you have to do in Spark. You actually have to think carefully about whether or not an operation that you want to use might have narrow or wide dependencies. And of course, we saw that sometimes some operations like join sometimes are narrow and sometimes are wide. So I can make a list here of operations that are usually always narrow and usually always wide, though there are of course some exceptions such as join here, because we know that join is not always wide. Sometimes it can be narrow depending on a partitioning scheme. But here we can roughly break down transformations into narrow and wide. Again, it doesn't always hold, but it's a rough approximation. So you can always look back at this list and use it as a little bit of a reference, but it's not always going to give you the answer. You're still going to have to think carefully about the operation that you're actually doing on the cluster. But sometimes maybe you want to be a little bit more certain than thinking critically about the operations that you're using. For that, Spark gives you a method called dependencies, and dependencies will give you a sequence of dependency objects, which are actually the dependencies that Spark uses in its scheduler to know how this RDD depends on other RDDs. When you call this method, you'll get back a sequence of dependency objects with different names. Dependencies called one-to-one dependencies are narrow dependencies. You might also see something called a prune or range dependency, but most often you'll see one-to-one dependencies for narrow transformations. And finally, wide dependencies are called shuffle dependency in Spark, which is a pretty clear indicator that a shuffle might occur. Here's a quick example of what the output to dependencies looks like. So if you have some pair RDD words, and you do group by key on it, and then you call dependencies, what you get back from Spark is a list with a shuffle dependency in it. So you know that this call to group by key is going to cause a shuffle. Spark also comes with another method called toDebugString. This method actually prints out a visualization of the RDD lineage along with other information relevant to scheduling. So if I was to use the same example on the previous slide, so we do map and then group by key on some pair RDD of words, if we call toDebugString, what we see is this. The resulting RDD from group by key is a shuffled RDD, which came from a map partitions RDD, which itself came from a parallel collection RDD. So this parallel collections RDD corresponds to words RDD. This map partitions RDD corresponds to the result of map on this words RDD, and finally shuffled RDD corresponds to the result of group by key. The indentations here actually show how Spark groups together these operations. So operations in the same indentation, like for example map partitions here, these groupings are typically separated by shuffles. So you can print out a lineage using toDebugString, and you'll be able to see how your job will be broken up into different groupings of operations separated by shuffles. So for example, you can have a group of many narrow transformations followed by one wide transformation, and you can see that from the indentation in the lineage printed out from toDebugString. And if you want to understand a little bit more about how Spark jobs are actually run, these groupings are called stages. So a Spark job is broken into stages by its scheduler. Okay, so we saw these lineage graphs and how they actually represent all of the relationships between RDDs and how we can determine when a shuffle will occur. But at the beginning of this session, I made this claim that lineage is related to fault tolerance. So how might that be the case? Well, actually, lineages are the key to fault tolerance in Spark. Ideas from functional programming enable this fault tolerance in Spark. This is because RDDs are immutable, so we can't update or change any of the data inside of an RDD. And then by using higher order functions like map, flat map, and filter to do functional transformations on our immutable data, what we have is effectively a directed acyclic graph. And assuming that we keep around this function that we pass to operations like map, flat map, and filter, what we can do is we can recompute at any point in time any of the RDDs in our entire lineage graph. So with these three aspects of Spark's design, RDDs being immutable, everything being essentially higher order functions, and then passing functions to these higher order functions, and building a directed acyclic graph, building a tree of transformations out of that. This means that we can actually recover from failures by recomputing lost partitions from these lineage graphs. So if you keep this information around, if you save this somewhere to stable storage, then you'll always be able to rederive individual RDDs in your lineage graph. That's the key idea here, and that's how Spark achieves fault tolerance without having to write to disk. This is how Spark can still do everything in memory and also be fault tolerant. Of course, this is always more easily understood visually, so let's assume one of our partitions from the previous example fails. So let's assume this partition here, for some reason, is no longer any good. Without having to have checkpointed all of that data to disk, Spark can actually just rederive it using this graph of dependencies that it already has. For example, we know that this piece of data is derived from this piece of data, which is derived from this piece of data. Assuming that none of it is cached in memory and I can't just reuse this, and all we have to do is recompute these pieces of data. So all we have to do is go back to this dependency information along with those functions that are stored with those dependencies and just recompute these pieces of data in order to recompute that piece of data, like so. And voila. Now note, recomputing missing partitions is fast for narrow dependencies, but it's slow for wide dependencies. Let's look again at our visualization to see why that's the case. If we lost this partition instead, we have to trace our dependencies backward. And because this child dependency depends on all of the parent dependencies in this union, we've got to recompute all of these intermediate RDDs in order to recompute this one piece of data here. Of course, it helps that this RDD is cached in memory, so we can just reuse this partition without having to compute this group by, but this is still going to be very expensive. So losing partitions that were derived from a transformation with wide dependencies can be much slower. Before we get into Spark SQL, which is the topic of this week, I first want to talk to you about structure and optimization to sort of motivate Spark SQL a bit. So before I say anything further about what I mean by structure and optimization, let's start with an example. So let's imagine that we're an organization called Code Award, offering scholarships to programmers who have overcome some kind of adversity. And let's say we have the following two data sets, where each one of these case classes will represent some kind of information about a person. So in the demographic case class, we have information like an ID number, we have a person's age, whether or not maybe they attended some kind of coding boot camp. We have the country that they live in or are from. We have information like whether or not they're some kind of minority or they have served in a military capacity somehow. And then we have other financial information like whether or not this person has any sort of debt, whether or not this person has financial dependents like children or anybody else that they have to financially support, or student loans, and finally income of this person. So we have these two different data sets full of these two different pieces of information about different people. One is called demographics, which is a pair RDD, where the ID is the key and the value is an instance of this demographic type. And on the other hand, the same is true for finances, where we have a pair RDD where the key is an ID number, and again, we have an instance of this finances thing as the value. Okay, so these are our two data sets. And let's assume that our data set includes information about people from many countries with many life and financial backgrounds. So given that, let's imagine that our goal is to count up and select students for a specific scholarship. So of course, every scholarship has some kind of criteria. So what is our criteria? Let's say that we have, for example, grant money given to us by the Swiss government, so that we want to target Swiss students, and we want to target people who are potentially in need financially. Maybe they have some kind of debt or they have many financial dependents. So as a first step, we want to have a look at our data set and see how many people might be eligible by this criteria. So first, let's count up the people in our data set who are both Swiss and who have some kind of debt with also financial dependence. So assuming that we just want to count the number of people in our data set that match this criteria, how could we implement this Spark program? So again, remember that we have two pair IDs available to us, one called demographics and one called finances, with ID numbers and instances of demographic and finances as the values, okay? So how do we implement this Spark program? I'll give you a moment to try and come up with an example solution. Well, the short answer is that there are many ways to implement this program. Since we know we need to combine both demographic and financial information, we need to do an inner join, because we need both demographic and financial information for a given person. The return type of this join will be another pair RDD with key integer, which represents the ID, and then a pair of demographic and finances. Once we've done that join, we can then filter out the people who meet our criteria. So in the first element that we have in the resulting pair of our join, which is of type demographic, we can check whether or not this person is from Switzerland. And then we can check in the second part of our resulting value pair, whether or not this person has financial dependence and whether or not they have debt. If all of these conditions are met, then we can pass that through the filter, and then finally we count it all up at the end. So just to summarize, in this solution we do an inner join first, then we filter to select the people in Switzerland, and then we filter to select people with debt and financial dependence. So we do an inner join first, and then we filter afterwards, and then we count it up at the end. So another possibility is to do our filters first. We could take our two data sets, finances and demographics, and then filter them down with the conditions that we already know we have. And once we've done that filtering, we can then join the filtered results and count them up. So in the finances data set, we pass through people who have both financial dependence and debt. And in the demographics data set, we pass people who are from Switzerland. And once we've filtered those two data sets down, then we do our join, and then we count it up. So just to summarize, we filter down the data set first, we look only at people with debt and financial dependence, then we filter to select the people only in Switzerland, and finally we do an inner join on this smaller filtered down data set. So the assumption here is that the data set should now be a little bit smaller, and we do a join on a smaller data set. And yet another possibility is to start with a Cartesian product between demographics and, this should be finances. This is finances here. So we start with the Cartesian product, and then we pass through our filter pairs that have the same IDs. And then finally we filter out people who are from Switzerland and people who have both financial dependence and some kind of debt as well, and then we count it up at the end. So this is yet another possibility that would give us the same answer. So again, this is finances, there's a typo here. So again, to go through the steps, we start by computing the Cartesian product in both data sets. Then we filter to select the results of the Cartesian that have the same IDs, so this is equivalent to an inner join. And finally, we filter out the people from Switzerland who have debt and financial dependence. So the bottom line here is that for all three of these examples, the end result is always going to be the same. However, the big difference is the time that it takes to compute the job. So while the resulting value might be the same, the execution time is vastly different. Here are the running times of the first two possibilities on a data set of roughly 150,000 people. In the first possible solution, where we did the join first followed by the filters afterwards, this computation took 4.97 seconds, so this blue bar here. Whereas in the second possible solution, we filtered down the dataset first before computing the join, it only took 1.35 seconds, so that's here. So the bottom line is that the running times of these two different possible solutions is pretty different. Filtering the dataset first results in a runtime that's 3.6 times faster than if we did the join first and the filter second. But that doesn't even compare to the possible solution where we computed the Cartesian product first. In this case, it took approximately 4 minutes to complete our computation versus 1.35 seconds or 4.97 seconds for the other two possible solutions. So this is 177 times slower than if we did an inner join instead of a Cartesian product. This is kind of common sense, but the bottom line here is to show that you can get the same result while having vastly different running times. Since a recurring theme of the course so far has been that we have to carefully think about what our Spark jobs are doing, I would hope that you wouldn't think to use a Cartesian product first. However, it is conceivable that you might have found yourself in a situation where you lost a factor 3 or 4x of performance by choosing the join first before the filter. Many people would think to join first and then filter down second, whereas upon retrospect, it does seem more sensible to filter first and then join afterwards. Wouldn't it be nice, though, if Spark automatically knew if we wrote the code in possibility 3, which was the Cartesian product code, or even if we wrote the code in possibility 1, that it could rewrite our code to be possibility number 2? So Spark would just automatically know that it would be smarter to do a filter before the join rather than the filter after the join. It would be great if Spark was smart enough to do that. What I hope to convey over the next few sessions is that given a bit of extra structural information, Spark is actually able to do many of these optimizations for you, and that all comes in the form of Spark SQL. So the key here is that structural information will enable optimizations. And in order to get a little bit of intuition about how that might be the case, we've got to start by looking at what I mean by structure. So to start, all data is not created equal in a structural sense. Data falls in some kind of spectrum between unstructured and structured. But what does structured mean? Well, structured is something like a database table, like SQL, or something that is very rigid with a fixed schema. On the other far end of the scale is unstructured data, so things like dumps of log files, or just unstructured text data of some kind, or even images. Images are another form of unstructured data. In the middle, we have semi-structured data, so things like JSON or XML. These are data sets that carry along some kind of schema, and they're so-called self-describing. So they describe their own structure. However, their schemas are maybe not as rigid as those schemas in a database table. So as you can see, there's a little bit of a spectrum here, from unstructured to very structured. And so far with RDDs, we've kind of been focused on this side of the spectrum. We've been typically reading in data from logs or data from JSON somehow. We've been manually parsing the JSON ourselves into case class objects, and then we've been doing some kind of large-scale computation on all of that once we've parsed it into Spark somehow. But how does all that relate back to Spark? Well, so far Spark and the regular RDDs that we've been looking at have no concept about the schema of the data that it's dealing with. So it has no idea what the structure is of the data that it's operating on. All Spark knows, given some RDD, is that RDD is parameterized with some kind of arbitrary type, like person, account, or demographic, but it doesn't actually know anything about these type structures. It just has a name. It has a name, it knows that it should have a person inside of it, but it doesn't know anything about what that person is made up of. Perhaps a little more visually, assuming that we have a case class account with these fields, name, which is of type string, balance of type double, and risk of type boolean, with an RDD of type account, all Spark knows about account is that it has these blobs of objects called account. We know nothing about them other than their names. Spark can't look inside of these account objects to look at their structure and analyze what parts of their structure might be used in a subsequent computation. For example, it's conceivable that this account object might be bigger than these 3 fields here. It could have hundreds of fields, and perhaps a certain computation only needs one of those fields. But Spark, as is, would serialize each one of these really big account objects and send them all over the network, even though it's not necessary to use most of the data that it's sending around. Spark can't do optimizations like these because it can't see inside of these account objects, and it can't optimize based on their structure. On the other hand, in a structured data set, in some kind of database table, for example, computations are done on columns of named and typed values. So absolutely everything about the structure of a data set is known in a structured setting like in a database table or in Hive. So absolutely everything about the structure of a data set is known in a database table. And in fact, databases tend to be heavily optimized. So given all of this structure, optimizations like I had mentioned with this account object can be done. Because we know the structure of the data set that we're operating on, and we know which parts of it we're going to use, and we can optimize based on that information. So far we've been talking about structured versus unstructured data, but the same could also be said for computation. So there is also structured and unstructured computation. So far, in Spark, what we've been doing is we've been doing functional transformations on data. So we pass some kind of user-defined function literal to a high-order function like map, flat map, or filter. So we're passing essentially some kind of lambda function, some sort of function, we're passing it around. This too is completely opaque. Just like in the previous example, Spark only knows that this is called some funny name like a non-dollar sign blah-de-blah. So in this case, this is also completely unstructured and opaque. Spark can't look at the operations that we're trying to do and then make some optimizations based on those optimizations. Again, we have some kind of opaque blob that Spark can't optimize on. Whereas in databases, typically we do declarative transformations on the structured data that we have in this data set. And all of these operations tend to be very specialized, very structured, very fixed, very rigid, predefined operations. So we know all of the possible operations that somebody could potentially do. And we can do lots of optimizations based on knowing all of the possibilities for these operations. So just to put these two things next to each other, in summary, what we have when we look at Spark RDDs is basically a bunch of these unstructured objects that we don't know much about, and some kind of functionality that we also don't know anything about. So just some kind of lambda function that we can't look into and make optimizations based off of. And on the other hand, we have databases where we have this very structured data set. Everything is some kind of specified data type. It's organized in rows and columns in this very rigid structure, and there are this very fixed set of operations that we can do on this structured data. So on the one hand, we have not much structure here, and it's difficult to aggressively optimize with so little structure. And on the other hand, we have lots of structure here, and optimization opportunities abound, which gives us all kinds of opportunities to do optimizations like reordering operations, for example, and putting filters before joins. So that brings me back to optimizations in Spark. How does all of this talk about structured data and structured computations come back to Spark? Because as we've seen, RDDs essentially operate on unstructured data. We have to parse it ourselves, and there are a few limits on the computations that we can do. Our computations are defined as functions that we pass to higher-order functions that we've written ourselves. On our own data types, we define our data types as well. As we painstakingly learned over the past 2 weeks, we have to think a lot about what's happening on the cluster, and we have to do optimizations ourselves. We have to think about how we can optimize our computations. Whereas in the databases world, optimizations are done automatically for you. Wouldn't it be nice if Spark could do some of these optimizations as well for us? Well, that's the whole point of
Spark SQL.
Spark makes these optimizations possible. So the one caveat is that we're going to have to give up some of the freedom, flexibility, and generality that we've learned to love in this functional collections API in order to give Spark some structure and thus more opportunities to optimize. In this session, we're going to dive into a very important component of Spark called Spark SQL. Despite Spark's rising popularity, SQL has been and still is the lingua franca for doing analytics. However, despite how widespread SQL is used, it's still a pain in the neck to connect big data processing pipelines like Spark or Hadoop to a SQL database. Usually for an application, one has to choose either SQL or something like Spark or Hadoop. Though wouldn't it be nice if it were possible to seamlessly intermix SQL queries with regular Scala code? And even better than that, wouldn't it be nice to get all of the optimizations that we're used to in the databases community on Spark jobs as well? So it's pretty common in databases to do all kinds of very advanced optimizations. But so far we have to optimize our compute pipelines in Spark by hand. Spark SQL is a component that delivers both of these two nice things. It makes it possible to seamlessly intermix SQL and Scala, and it also optimizes Spark SQL code very aggressively, kind of like using many of the same techniques from the databases world. So Spark SQL has 3 main goals. The first of which is to support relational processing in Spark. So this is that goal of intermixing relational code, declarative SQL-like syntax, with functional APIs like Spark's RDD API. And this is because it's sometimes more desirable to express a computation in SQL syntax than with a functional API and vice versa. So you could imagine that, for example, selecting an entire column out of a database is easier to do with a single line in a SQL statement than it is to do somehow with a map or a filter operation. And the other 2 main goals of Spark SQL is, of course, high performance, like previously mentioned, and support for getting data more easily into Spark. Wouldn't it be nice if we could just read in semi-structured data like JSON, for example? So Spark SQL seeks to add relational processing to Spark, bring super high performance from optimizations in the databases world, and to support reading in data from semi-structured and structured data sets. That said, what is Spark SQL? Is it like another system that we have to learn how to use? No, it's just a component of the Spark stack. So you can think of it as a library. It's a Spark module for structured data processing or sort of doing relational queries, and it's implemented as a library on top of Spark. So you can think of it as just adding new APIs to the APIs that you already know. You don't have to learn a new system or anything. And the 3 main APIs that it adds is SQL literal syntax and a thing called data frames and another thing called data sets. So these are the APIs, these are the things that you see and have access to. And on the back end, it adds 2 new back-end components. It adds something called Catalyst, which is a query optimizer. This is the component that will optimize your code. And another component called Tungsten, which is an off-heap serializer. Or said another way, it's a system that encodes Scala objects in a very, very efficient representation off-heap, away from the garbage collector. So these are the main things that Spark SQL adds: APIs and some stuff on the back end that should speed up your code quite a bit. Just to give you a visual depiction of how Spark relates to the rest of the whole Spark ecosystem. So we have this system called Spark, and inside of it we have this RDD API. We've been operating this entire course on these things called RDDs. We've been doing functional transformations on them. They're sort of the core data structure of Spark. Spark SQL sits on top of Spark as a library. It has its own APIs, and it has this thing called the Catalyst Optimizer, and while it has its own data frame API, it ultimately runs on RDDs under the covers. And on top of Spark SQL, you have everything else, like the console and regular user programs, so a user can write programs both using the data frame API and RDDs and freely intermix them. But the bottom line here is that we have this API that then does some optimizations and ultimately runs RDDs under the covers. So Spark SQL is a Spark component that provides a SQL-like API on top of Spark. This is neat because everything about SQL is structured. In fact, SQL stands for Structural Query Language. It has a fixed set of data types, so things like longs, integers, strings, arrays even, and it has a fixed set of operations, select, where, group by, etc. And for decades, both research and industry surrounding these relational databases have focused on exploiting this rigidness, these known data types and these known operations to get all kinds of performance speedups. Since knowledge of SQL or databases wasn't a required prerequisite for this course, I'm just going to quickly spend a slide running through vocabulary. When thinking in SQL, data is organized into one or more tables. So here's an example of what a table might look like. There's a header. Tables have columns, which are named, for example, customer name or destination or ticket price, and then there are rows, so records. And a table typically represents some kind of collection or data set. So you might have a table and think of it as a table of customers. So we can think of this as the CFF or SBB customer data set. So like the train data set that we were looking at in an earlier session. This is how you think about a table. It's kind of like a collection of data. Other words that you might hear used, a relation is just a table, and attributes are columns. So this customer name here is an attribute. So this is just a column. Rows are also called either records or tuples. So this row here represents a record or a tuple. This record represents, for example, a ticket purchase. This is the last name of the customer, the destination of the customer, and the price that the customer paid for their ticket. This is one record in our data set representing that purchase. So this is the terminology that we're going to use. We have tables, also known as relations. We have columns in our tables, which are also known as attributes. And then we have rows, which are also known as records or tuples. Now back to Spark SQL. Spark SQL's core abstraction is known as a data frame. And every time we use the word data frame, you can imagine it as being conceptually equivalent to a table in a relational database. So data frames are conceptually distributed collections of records. And these records, they have a known schema. Okay? And super important is this point here, that unlike RDDs, which are also a kind of distributed collection, data frames require some kind of schema information about the data that it contains. Data frames are also untyped. Okay, this is an important point that's going to come back to. What do I mean by untyped? Well, I mean that it doesn't have some kind of type parameter that the Scala compiler statically checks. Compare that for a moment with RDDs. RDDs have a type parameter. So we can always make sure that the type that's inside of an RDD makes sense. However, data frames have no type parameter. They can contain rows, which can contain any schema, which the Scala compiler doesn't have a lot of ability to type check. And finally, one last terminological point, transformations. Transformations on data frames are called untyped transformations. This terminology is going to also come back to us later. Real quick before I go any further, we got to talk about the Spark session object. So if you remember the Spark context from the rest of this course, the Spark session is basically the Spark context for everything Spark SQL. So you're going to now have to switch to using this Spark session instead of Spark context. And to create and use one of these Spark session objects is still pretty straightforward. You just import the Spark session object, and there's this builder pattern here. You can add custom configurations that you'd like, but in general you have to start with a builder, you have to name your app, and then you have to say get or create. So you can have any number of configuration options in the middle here, but this is the general shape, and this is kind of the minimum that you need to start a new Spark session. Another important thing to note is the Spark session object, I believe, is meant to supersede Spark context down the line. So this is something that you should start looking into. So let's get into it. How do we create a data frame? There are two ways to create a data frame, either from an existing RDD or by reading in some kind of specific data source from files. So reading in some kind of common structured or semi-structured format like JSON. And for creating a data frame from an existing RDD, we can do it via two ways, either by inferring the schema or by explicitly providing the schema that should be contained inside of our data frame. So the first way to create a data frame that I'm going to cover is to create one from an existing RDD by reflectively inferring the schema, okay? This is probably the most convenient way to create data frames. So assuming that you have some kind of RDD, let's just say in this case it's a tuple RDD. To turn our tuple RDD into a data frame, all we have to do is call toDF on it. We can pass arguments to toDF, which represent the names of the columns. If we don't pass this list of column names to toDF when we call it, then Spark will assign numbers as attributes or column names to your data frame. They'll be usually something like this, _1 or _2 or _3 for the number of the column. However, if you have an RDD of case classes, things are even more convenient. So assuming we have this case class person and we have an RDD of person, all we have to do is call toDF on this RDD of person objects. And in this case, the column names automatically get inferred to be the names of the fields of this case class. And again, this is done all via reflection. The other way to create a data frame from an existing RDD, which is quite a bit involved, is to explicitly specify a schema. And this is useful for the case where you don't have some kind of predefined case class that you can use as its schema. Like I said, this is a bit involved, so bear with me here. It takes 3 steps. First, you create an RDD of rows from the original RDD. Then you create a schema separately that matches the structure of rows. Then, finally, you apply that schema to your RDD of rows using this method called createDataFrame. So let's step through a quick example, and like I said, this is a little bit involved, so please bear with me. For the sake of this example, I'm just going to stick with a case class, even though I know it's possible to use the toDF method. Just stick with me here. So assuming I have an RDD full of these person objects, I first have to encode the schema in a string, so I have to do this manually. Then I have to build up a schema using these struct type things and struct field things that matches the shape of the data that I'm trying to build a schema for. So this is done by breaking up this string and then mapping on it and creating a struct field for each part of the schema, which has the name in the string here as the parameter. It has a type called string type, which we'll see later, and nullable is set to true. Like I said, we'll see some of these things later, and then all of that goes inside of something called struct type, and now we have a schema. So this is what a schema looks like. We build up a schema from these things called struct type, struct fields. Then we convert our RDD of people to a row RDD. Then we convert our people RDD into a row RDD by breaking it up and mapping everything to row objects. And finally, we can use this createDataFrame method on the Spark session object and pass to it the row RDD that we just created as well as the schema that we just created. So that's how you manually explicitly build up a schema and then create a data frame from that schema. It's a bit involved, but it's sometimes necessary. And finally, likely the most convenient way to create a data frame is by reading in data from a source file. So using the same Spark session object, you can read in a number of semi-structured or structured data types using the read method. So there's this read method on the Spark session object, and then you can read in, you can specify what you'd like to read in, for example, JSON, and then you specify a path to this JSON file. It's kind of like read text file, but it's better. It'll parse semi-structured and structured data, and it will build up a data frame with that schema of that semi-structured or structured data. And of course, it's important to note that there are a handful of formats that Spark SQL can just automatically read in for you. Can't read in arbitrarily anything, but the most common are probably going to be JSON, CSV, and Parquet. There are more methods available for directly reading in semi-structured and structured data. To see that entire list, you can visit the docs, which are here in the slides. Now that you know how to make data frames, once you have a data frame, you can freely write familiar SQL syntax to operate on your data frame. So how do we use plain old SQL syntax on a data frame? Assuming that we have a data frame called peopleDF, all we have to do is register our data frame as a temporary SQL view. So there's a method called create or replace temp view here. that you can call on your data frame, this gives you a name that you can refer to in your SQL from statement. So in order to use SQL syntax, you need to register your data frame as a table, and then you can operate on it in regular SQL syntax. So now that I had this temporary SQL view registered called people, I can freely use it inside of a SQL query. So to do a SQL query in Spark, once you have a data frame, call the SQL method on the Spark session object and pass to it a SQL query, which refers to a registered temporary SQL view. So in this case, people. So in this query, we select all rows from this people table where the age field is greater than 17, for example. It's quite convenient, isn't it? Now, since you know you're writing SQL queries on top of Spark, which is not a SQL database, you might ask which SQL statements you have available to you. Well, the SQL statements that are available to you are largely what's available in the Hive query language. So this includes standard SQL statements such as select, from, where, count, having, group by, order by, sort by, and of course all of the joins. And also importantly, you can do subqueries as well in this syntax. Most everything from HiveQL is supported, so you can usually just try it out and see if it works. But if you want to collect more information about what syntax may or may not be supported, I've included a number of links for you here in the slides. There's a cheat sheet for HiveQL, a list of supported Spark SQL syntax, and an updated list of supported Hive features in Spark SQL on the Spark official documentation. So let's do a more interesting SQL query, because so far we've just created data frames and we've done a really simple query. Let's now assume we have a data frame representing a data set of employees. So how do we create that data set of employees? Well, we have a case class employee here with a number of fields: ID, which has type integer, first name, last name, both type string, age, type integer, and then the city that this person lives in, type string here. And to create a data frame, we simply create an RDD and then call 2df on it. So now we have a data frame full of these employee records here. Now it's time for a little quiz. Let's query this data set to obtain just the IDs and the last names of the employees working in a specific city. Let's say Sydney, Australia. And then, once we've obtained that, let's sort our result in order of increasing employee ID. So that means we want the IDs and last names column of this employee data frame for only employees that work in a specific city. And then after we're done with that, we want to sort our employees in order of increasing employee ID. So I leave it to you. How would you write this SQL query? Well, it's not too difficult. Let's assume that we have a table registered with the name employees. I left that out on the last slide, but assuming we have this table registered, all we have to do is say select ID and last name. So we select these two columns from this employees table, and we filter out everybody who lives in Sydney. And then we just order by the ID. To make sure we understand this query, let's visualize it. So assuming that this is our data set here, so we have this employee data frame. So assuming we have this data set here, this is our employee data frame. And remember, we register it as a table called employees. This is what the result of the query looks like. We've obtained our resulting dataset by selecting only these two columns, and then filtering out the records where city equals Sydney. So we get rid of these two people that live in New York here, and then we sort the elements by order of increasing ID numbers. So in this dataset, the IDs are backwards, and here they're now in the right order. So this is how we... So the bottom line, now we know how to create data frames and how to do arbitrary SQL queries on top of them. Pretty cool. In this session, we're going to dig deeper into the data frame API. So far, we got a little bit of an intuition about what data frames are, how they fit into this whole Spark SQL thing, and, we saw how to create them. We saw that if we have a data frame, we can use SQL syntax and do SQL queries on them, which is pretty cool. But it doesn't just end there. Data frames have their own APIs as well, in addition to being able to use just arbitrary SQL syntax on a data frame. In this session, we'll focus on that data frames API. In particular, we'll dig into the available data frame data types. We'll look at some of the basic operations that are available on data frames that you should know about, because it's not like RDDs. And finally, we'll look at how to do aggregations on data frames, because there's also a little bit of a different way to do that as well. Okay, data frames in a nutshell. Let's recap some of the key points to remember when using data frames. So the first point is that data frames can be thought of as just a relational API over Spark's RDDs. So you're running ultimately on top of RDDs, the same RDDs we learned about in previous sessions, but you have a nice relational API over them now. And the reason for this is because it's just sometimes more convenient to use a declarative relational API than it is to use functional APIs for analysis jobs. We saw this in the last example, in the last session, where we saw this nice little query where we were trying to select some information about some employees and then filter it and sort it, and it was done in almost no code at all, and it was extremely clear to read. It would have been a little bit more involved and a little bit less clear to read if we had done it with a functional API. The next key point to hold on to about data frames is that they're able to be aggressively optimized automatically. So Spark SQL takes many years of research in the database communities, and we apply them in Spark now that we have some computations that are built up in sort of a relational way. We can apply these relational optimizations to get the same optimizations that people in the databases community have been enjoying for many years. And finally, one thing that you're really going to have to remember, maybe it won't bite us right in the beginning of this session, but it definitely will later, is that data frames are untyped. So the elements within data frames are rows, and they're not parameterized by some types. So the Scala compiler can't type check Spark SQL schemas in data frames. They're just opaque to the Scala compiler. There's all kinds of analysis done by Spark SQL, but the Scala compiler doesn't do any type checking. So they're effectively untyped. So as I've mentioned a few times now, Spark SQL's data frames operate on a restricted set of data types. This is in order to enable optimization opportunities, so we always know exactly what the data looks like. So here's a list of the basic data types in Spark SQL. So in this column we have the Scala type, so all of the types that we're used to already seeing in this course, and these are the types that SQL sees, and this is a description of each of the types. These are all pretty standard Scala types, or pretty standard primitive types. We have things like bytes, shorts, ints, longs. We have strings here at the bottom. Interestingly enough, there's timestamps and dates from Java. We have things like floats and doubles, big decimal. These are all pretty uncontroversial data types, but these are the data types that Spark SQL uses. These are the core data types that Spark SQL is built around. In addition to these basic data types, Spark SQL has a handful of complex data types available to use, such as arrays, maps, and, well, in this case classes, but structs. So these are complex data types that can contain basic data types or other complex data types themselves. So you can build up richer data types using these things, these arrays, maps, or in this case, structs. Since each of these data types are represented a little bit differently in Spark SQL because of their history in regular SQL, I'm going to run through each of them to show you sort of the main differences. And really the main difference has to do with this contains null thing here. So in this case, an array, for example, an array of string in SQL is an array type with a string type, which is its parameter, with this Boolean here. And in this case, this Boolean is this contains null thing, which is set to true if the elements in the array tuple, in the array type, can have null values. So if it's possible for this array to contain nulls, we're going to have this conditional set to true, otherwise it will be set to false. So there's always this additional piece of data hanging around here called contains null. So we have not just type information about the type contained in the array and the fact that it's an array at all, but we also have some knowledge about whether or not this thing can contain nulls. The next complex data type that we're going to look at is a map. Just like maps in Scala, maps have keys and values, and the SQL version of this has types that correspond to the keys and types that correspond to the values. So a map type contains a key type and a value type, as well as this Boolean here, which represents whether or not the value type can contain null. Okay, so it's similar to what we just saw on arrays, but this contains null thing refers to the value instead. So if whatever is in this value, so in this case a string, if this value can be null, then this is set to true. So we know the type, this is nullable, basically. And finally, struct. So structs are a little bit less rigid than arrays and maps. The struct type contains a list of possible fields of different types. So unlike arrays and maps, which were one type or two possible types, structs can be any arbitrary number of types, but you have to have something called a struct field, which contains a name for the field, the type of the field, and then again, this nullable value here. So You can build up more interesting data types this way, and this is how you can take, for example, something like a case class and map it to something that SQL can understand. So in this case, we'll be using case classes in Scala, but in SQL, the same case class would look like this. So if we have a case class person with a field name and a field age, the name is type string and the age is type int. This can be realized as a struct type in SQL with a list of fields. One field, so one struct field, has the name, it has the type string, and it's nullable, it's possible to be nulled. And again, another field which has type has name age, has type integer, and also is nullable. So this is how we could represent, for example, a person case class object here. So these are the data types that Spark SQL can operate on. This is pretty important because if for some reason your data type doesn't fit into one of these shapes, it can't be worked on in Spark SQL. So just to repeat, Spark SQL has a restricted set of possible types. Nothing fancy happening in these types. You have basic structs, basic arrays, basic maps, and then you have this list of effectively primitive types that I showed you on the previous slide. And every computation that we will be doing in Spark SQL has to be able to be represented by these sets of types. And just to show you that it's possible to arbitrarily nest these complex data types, here's an example where I've taken some Scala types here. So these are actually rather complex and nested. So I have a type called account, which contains a field called balance and a field called employees, which is an array of employees. But employee is defined as another case class with these fields here with a primitive fields int string. And finally, there's another case class called project with a type string as a title, and then another array of these employee objects, and then a value of type account here. So this is a rather complex data type, this project thing here. So if I wanted to represent this project type, I could do it here, just like this, in SQL. It's super involved, it's difficult to read. But this is actually just a realization of this project type here, which contains accounts and employees types. So you can basically write this code and then expand it to be this, right? So this here is project, right? And I'm sorry about the wonky trues here. Something happened in the PDF reader, but these are all struct fields, and these true things are the nullable booleans. And you have things like arrays. You have things like more struct types within struct types, and then you have, of course, primitive types. So here's a struct field of type string type with the name, for example. So again, these things can be nested and built up to represent reasonably complex data types. And one important note, so this is actually going to come up again and again throughout Spark SQL. Spark SQL really requires a lot of imports. Throughout this and the next few sessions, I've tried to tell you everywhere where you might have to have some special import to use one of the things that I'm showing you, though if ever in doubt, have a look at the Spark docs. In this case, in order to use any of the data types, you need to import all of Spark SQL's types. So that can be done like this. So again, if you're ever going to use a Spark SQL data type, you actually need to explicitly import the types that Spark SQL operates on. Okay, so what sorts of operations are defined on data frames? So far, all I told you is that the data frames API is all about relational operations, a relational API. So said simply, the data frames API actually is quite similar looking to SQL. Example methods include select, where, limit, order by, group by, join. You might notice that this is quite different looking from RDDs that you're already used to, because we've been operating on things like maps and filters, and with reduces and stuff like this, we've been passing functions to higher order functions like map, reduce, and filter, right? So the main difference between the RDD API and the data frames API was that when introduced, the data frames API was designed to accept just these Spark SQL expressions instead of arbitrary user-defined function literals like we used all over the place when we were learning about RDDs. And the reason for this was to give the optimizer a restricted set of operations that it already knew how to optimize based on. So these relational optimizations, it needed relational operations to do those relational optimizations, right? So here's a selection of some of the more often used methods, but we'll go into more detail in subsequent slides. But first, before I do that, I got to show you one important trick so you can actually see what you're doing with these relational operations. So to see what your data looks like. So there are a couple of methods in Spark to show what your data looks like. The first that I'm going to be using all the time is called show. It pretty prints the data frame in a tabular form, and it shows only the first 20 elements. So it looks something like this. So if I have this employee data frame again, right, which we use 2DF on, and if I do show on it, it prints out this nice thing here, which shows all of the elements. In this case, there's only 4, otherwise it would show up to 20, but it prints these out nicely so you can visually sort of parse this easier. And then the other operation that we can use to get a look at our data is called print schema, which prints the schema of the data frame in tree format. So here's an example of what this looks like. I'm using the same exact data frame here. So this employee data frame that we saw earlier. And so here's what it looks like when we say print schema. So this is actually quite a simple schema. Basically, this is the root, and there's just one level of fields here. I have just 5 fields, one of type integer, string, string, integer, string, right? And all of them are nullable. Remember this nullable thing that we saw in previous slides. There's always this nullable Boolean that has to hang around to say whether or not one of these data types can be nulled out for some reason. Okay, so let's actually look at some of these transformations. 2 things to remember. We're talking about transformations right now, which means that transformations always return a data frame as a result. And second, don't forget that they're lazily evaluated. Okay, so just like regular RDDs, these are lazily evaluated too. Some of the most common transformations include select, which I'm sure you already have kind of an idea of what it might do. It selects a set of named columns, so more than one column potentially, and it returns a new data frame with these columns as a result. We saw this earlier when we said we wanted to select 2 out of the, 5 or several columns in the SQL query that we did in the previous session, where we took the employee's last name and the employee's ID number out of our data frame and returned a new data frame with those columns. So just visually, if you have a table with 4 columns and then you say I want to select columns A and D, then you get back a new data frame, or new table, I guess, with just these 2 columns. And you use select by passing the names of the columns to the select method. There are a few other overloaded versions of these. You can have a look at the Spark docs to see the different choices for selecting columns, but this is ultimately the idea here. The next transformation that's going to come up is called aggregate. So this one is peculiar, and we're going to go into more detail into it later in this session, but the short story is that aggregate performs aggregations on a series of columns, so on one or more columns, and it returns a new data frame with the calculated output, with the aggregated output. Okay, so we'll get more concrete about what that means a few slides from now, but moving on, group by, which you can kind of guess what that might do. So it groups the data frame using the specified columns. So it's important to note that this is a little bit of a weird method here. I say that it returns a data frame, but it doesn't exactly return a data frame, because this group by method is actually intended to be used right before an aggregation. So typically you would be doing a group by and then an aggregation after the group by. So we'll go into a little bit more depth when we talk about aggregations about what this group by exactly does, but you can think about it right now as grouping the data frame by some specified columns. Okay, and then we'll do an aggregation on it in a second step. And finally, one of the more commonly used operations is, of course, a join. There are many ways to interact with joins. We'll go into detail in the next session about all of the ways to use joins. Just remember that all of these things are transformations. Either they explicitly return a data frame or they indirectly return a data frame as a result. Of course, there are several more transformations, such as filter, limit, order by, where, as, sort, union, and drop. These are all basically the same operations that we know from SQL. All of these, along with their overloads, can be found in the Spark SQL docs. So I'd like to show you an example of how to use some of these transformations, but before I do, I have to talk a little bit about columns. So if we go back to the previous slide, we'll note that sometimes you pass strings to these operations, and sometimes you pass a column. And usually the strings are meant to refer to a column, but what's a column? So how do I actually talk about these columns in the context of these Spark SQL programs? So there's a few different ways to specify columns, and it can sometimes be confusing if you just jump into a code base without anybody telling you what these things mean. So the main 3 ways that you'll see people referring to specific columns in a data frame are as follows. Most commonly, you'll see this $sign notation, which is just a shorthand for specifying the name of a specific column. So if you're calling, for example, filter on some data frame, so I go to dataframe.filter, and if I want to filter on the age column, I can do $, and then in quotations, put the name of the column, and then I can do whatever operation, whatever SQL operation I want to do. So this basically means the age column of this DF data frame here. So another way to refer to a specific column is to actually explicitly refer to the data frame. So we can, just like above, we can explicitly say, okay, the DF data frame here, and then the age column, we pass a string to it. So we pass age as a string, and then that's a signal to Spark SQL to look in this data frame for that column. And finally, the last way to do it is to use a SQL query string. So just like what we saw when we were actually writing out the SQL queries in this syntax like this, where the SQL query was a string here, Spark SQL actually parses that with a SQL parser and then figures out what are columns and what are operators from this string that you pass to it. So you can do the same thing here, where you can pass sort of a SQL query kind of and hope that Spark SQL can parse it correctly. There's sometimes some errors with this, so I would, if I were you, I would probably go with one of these two methods over this method, because these are a little bit less error prone. So now that we know how to refer to columns inside of these data frame operations, let's look at an example. Recall the example SQL query that we did in the previous session on this data set of employees. So we've been looking at this employee data frame now for a little while. Rather than using SQL syntax like we did in the last session, let's convert our example to use the data frame API. So if you remember what this example asked of us, it asked us to obtain just the IDs and the usernames of the employees working in a specific city. Say, in this case, we want to select just the people living in Sydney. Okay, and then let's sort the result in order of increasing employee ID afterwards. So once we've grabbed these columns and then filtered out the people who live in Sydney, then we sort them by the employee ID. So how would we solve this with the data frame API with some of the methods that you've seen so far? I'll let you try it first. The data frame solution actually looks a lot like the SQL query that we did in the previous session. In the previous session, we used a select statement followed by a where statement followed by an order by statement. We can do essentially the same thing here. So given the employee data frame, all we have to do is select the ID of the employee and the last name of the employee. So now we've selected those two columns, and then we filter out everybody who does not live in Sydney. And finally, we order the records or the rows by the ID. And as always, it's nice to try this out in a real data set. So this is the input data set. So this is what employee DF looks like. So in this case, we have these 4 records. And after running the Spark SQL expression here, what we get is a new data frame called Sydney employees DF, like this, with only 2 columns. And then the ID numbers and last names of the people who live in Sydney, sorted by the ID numbers. So David Walker is now first, because he's 221. He lived in Sydney, so he's the first element, and then the next one is Slate Markham, who is now second because his ID is 645, and he also lives in Sydney, and the New York people are nowhere to be found. So here's an example of a few transformations on a data frame. Also, it's important to note that there are 2 methods available for filtering in Spark SQL. One is called filter, and one is called where. Both of them are the same. One is just an alias of the other, so you can always think of these things as completely equivalent. When filter looks better, write filter. When where looks better, write where. And also notes that it's possible to make filters a little bit more complex too. We can have Boolean expressions, ANDed or ORed, and we can also use several different columns in these expressions, so we can compare between columns as well. The only thing to note is that if you do a lot of this, it can be a little more difficult for the Spark SQL Query Optimizer Catalyst to optimize your queries. The last topic I'm going to cover in this session is grouping and aggregating on data frames. I mentioned kind of awkwardly earlier on that the aggregate method is meant to be used after a call to the group by method. Let me show you a little bit more what I mean here. So there's some special operations for grouping and aggregating, and this is because one of the most common things that you want to do with a table is to group data by some column, by some attribute, and then to do some kind of aggregation on that column or that attribute, like a count. So these things are a pretty common pattern. For grouping and aggregating, Spark SQL provides this group by function that I mentioned earlier, which returns this strange thing called a relational group dataset. This is when I said the type was simplified. We'll talk about that in a second. And then it has several standard aggregation functions defined on it. So these are defined on this relational group dataset, some of which include count, sum, max, min, and average, amongst many others. So you have kind of this 2-step thing going on here. You've got to do group by, you get back this relational group dataset thing, and then you get some of these aggregation functions that you could potentially use. This can get a little hairy with the types, so the API docs are really your best friend here. But the basic pattern you have to remember is that you have some data frame, you do a group by on it, and then you call some other method like ag here, which I'll talk about in more detail in a moment, or count, things like this. So this count operation is defined on this relational group data set thing, and it returns another data frame. So then you get back to data frames again. So this API basically requires you to go through 2 steps. First call group by and then call some other operation to get you back to a data frame. This can look a little complicated, so let's look at an example to clear it up. So let's assume that we have a data set of homes currently for sale in one entire US state. Let's try to use these grouping and aggregating operations to calculate the most expensive and the least expensive homes for sale per zip code. So we want to do this per zip code. We want to find the most expensive and the least expensive per zip code in this entire state. So assuming that we have a data frame full of these listing things here, how could we compute these most expensive and least expensive homes for sale per zip code? I'm going to let you try it. Feel free to go back to the last slide if it helps, but see if you can use group by and some kind of aggregate function to do these calculations. Here's how we can do it. First things first, we're going to have to import another SQL import. So this one's called functions, and it gives you these things here, like the max and the count and all of that. So you're going to have to import that if you're going to want to use any of these grouping and aggregation functions. Otherwise, you just do group by zip code, which is pretty straightforward, right? We're grouping by the zip code, and then per each zip code, we want to know what the maximum price is of the listing. So the price is of type int. We can easily calculate the max. And we're grouping by the zip code, which is also an int, so now we have the maximum price per zip code, and likewise we can do the same thing with minimum, so we can just group by the zip code, so now we have groups of zip codes, and then we can choose the minimum one in each the minimum price in each zip code. This is extremely readable, extremely straightforward. If you want to see how this looks on real data, I encourage you to go to the Databricks Community Edition notebooks and to try this out on a real data set. You can almost exactly copy the code here. Okay, that was kind of easy, wasn't it? Let's try something a little harder. Let's assume that we have the following data set representing all of the posts in a busy open source community's discourse forums. So just think forums with subforums, okay? And we have this case class post here, which represents some activity or some post in this forum. Each post has an author ID. It has a location where this post was made. In this case, it was made in a specific subforum, and a number of likes for that post, as well as the date that it was posted. Now, assuming that we have a data frame full of these posts, let's say we'd like to tally up each author's posts per subforum and then rank the authors with the most posts per subforum. Okay, so basically what we want to do is we want to count up all of the posts that people are making in each subforum, and then we want to basically figure out who was the person with the most posts in each subforum. So maybe we're going to give this person a community award or something, so we want to know who's the most busy in each one of these subforums, okay? How could we do this using these grouping and aggregating functions on data frames? I'll give you a few minutes to try it yourself. Okay, so first things first, we've got to import our SQL functions here. And after that, we just got to do a group by, an aggregate, and an order by. So let's step through this. So we want to group author IDs and subforums together because we're trying to figure out who's posted the most in each subforum. So we need both the author and also the subforums. And then we do an aggregation on these. In this case, I've used this interesting aggregate method, which itself takes another call to a function. I actually didn't need to use this here. I could have just used count, but I wanted to show you what it looks like to use it. And then I specify that I want to do a count on the author IDs. This gives me a new data frame with the following columns. I get an author ID column, a subforum column, and then a count column. So the number of counts per that author ID in that subforum, okay? And finally, I can just rearrange the order, and I use order by. So I have 2 parameters here because I want to first order by the subforums, and then I want to order by the counts. But notice I do this here, which says, okay, I don't want it to be in increasing order, I want it to be in descending order. So the count column will be in descending order, okay? So what does this look like on real data? This is maybe not the most beautiful data set that you're going to have a look at, but note that there are 2 subforums. They have actually similar looking names if you glance really quickly. One is called design, another is called debate. And let's just say I have 3 authors, author ID 1, 2, 3. Author ID 1 posts a lot in the design forum, for example. And this is what the result of the group by aggregate followed by the order by looks like here. So as you can see, I've ordered by the subforums now. So I've got the debate subforum first, followed by the design subforum. And then I have the counts in decreasing order. So the author with the most posts in the debate forum is author number 2. And the author with the most posts in the design forum is author number 1. As you might have noticed, there's kind of 2 APIs here. There's this API that's available inside of this relational group dataset thing here, and there's also an API available for use with this aggregate method here. And each of these have individual Scala doc pages that you can look at to see what operations are available to you. So there's a set of operations available within this aggregate thing here, and you can figure out what all of those operations are by going to the Spark SQL functions page of the API docs. You can see a full list, and if you want to see a full list of the operations that you can call following a group by, have a look at the API docs for this relational group dataset thing here. In this session, we're going to continue diving into the data frames API. So far, we developed a little bit of an intuition about what data frames are, how we can create them. We learned how to do transformations and, importantly, also aggregations on data frames. So we have a little handful of operations that we know how to do on data frames, in particular relational operations. And in this session, we'll continue to focus on the data frames API. In this session, we'll cover how to work with missing values or how to deal with things like null. We'll look at common actions on data frames. So we saw transformations and aggregations. These were both transformations of some sort, but we didn't look at any actions yet, or so we think. Then we'll dive into joins on data frames, and finally we'll talk a little bit about optimizations on data frames. So let's get started with cleaning data with data frames. Anybody who works with real data sets knows that data is never pretty when you start with it. Often it's full of unwanted values like null or NaN, or not, which stands for not a number. In these cases, it's often desirable to do something about these unwanted values. In particular, often we like to drop rows or records with unwanted values like null or nan, or sometimes we like to actually replace those values with something that is less problematic than null. For example, maybe if null is in a numeric column, we'd like to replace it with 0. Spark SQL offers a handful of methods to help you clean your data. For example, on the dropping front, there are a number of methods or overloads of this drop method that we can use to clean up some of these unwanted values. The most commonly used is the method called drop without any parameters, and if you call this method on a data frame, what this does is it drops rows that contain either null or nan in any column and returns a new data frame without those problematic values. Which means if you have some row with many values in it, and most of them are good, but one is null, then that entire row gets dropped. That behavior might not be desirable sometimes. Perhaps we know we can deal with that null value and replace it with something else in some other way. In that case, you might want to use the drop method while passing all to drop. And in this case, what we do is we just drop rows that contain null or nan in all columns. So another way, that just means that if we have a row with all null values, then we drop the entire row, but only if all of the columns are null or nan. And finally, there's another variant of drop that we can pass an array to, which contains column names, and this means that we only drop records that contain null values or nan values in these columns. So that means we only drop columns, for example, if the ID in the name has a null value, but we don't care about other columns with null or nan values, for example. The other class of operations that we can do to clean up our data sets has to do with replacing unwanted values with something else. There are a few different variants of the fill method. This variant here that I've chosen to show, if you pass a parameter to it, in this case a number, 0, then what we can do is replace all occurrences of null or nan in numeric columns, if we pass something numeric to fill, with this specified value. So in this case, if there is a null or a nan found in any column that has a numeric type, we replace the value with 0 instead. And of course, we return a new data frame. This variant to fill gets a little bit more specific. In this variant, we can pass a map to fill, where the keys are column names, and the values are what we'll replace null or nan with. So perhaps we want to handle different columns differently. So say we've got one column called minimum balance and another column called name. Perhaps we want to replace minimum balance. If there's a null, we want to replace it with a 0, but if there was another column called name, we would maybe instead replace the null that we find in that column with some other string that could be more useful. And finally, there's the replace method here, which is good for replacing specific values. So let's say I messed up my data set accidentally. Perhaps there's a row where something isn't what it should be. I can make corrections with this replace method. In this case, what we're doing is we pass an array to replace and a map as well. So the array contains column IDs and map contains values that should be replaced. So in this case, what happens is in the column called ID, we replace the specified value, which is 1, 2, 3, 4, with 8, 9, 2, 3 if we come across 1, 2, 3, 4 in the ID column. So the idea is I can one-off replace erroneous values, for example, using this replace method. So these are just a gist of some of the methods that you can use to clean your data. These are the main variants of the 3 methods that we can use on data frames to clean up data sets. So drop, fill, and replace are the main methods. They each have a few variants, but we've covered most of them so far. You might have noticed that we covered transformations in the last session, but we didn't say anything about actions. Just like RDDs, data frames have their own set of action, and we've actually even used one of these actions several times already. In fact, the actions that are found on data frames aren't all that interesting. They're actually very similar to the actions found on RDDs, so I'm not going to show you examples of each one of these things being used since we've already seen them many times already in the RDD sections. But there is one that is particularly interesting, and that's this one here called show. And this is the one that we've actually already seen several times already. This one is rather special for data frames. So as we saw, this one displays the top 20 rows of the data frame in a tabular form, so it pretty prints it in a very nice way, so it's easy to actually look at and visually parse this table. The other common actions are actions that we already know, such as collect, which returns an array that contains all of the rows, in this case, of the data frame back to the master node. There's also the count operation, which returns the number of rows, so this is an operation that returns the number of rows specifically. And then there's a method first or head. These are both the same method, which returns the first row, the entire first row in the data frame. So if you ever want to just take a peek at what's in your data frame, you can just grab the first row on top using this first or head method. And finally, there's the take method, which we're already also very well familiar with. The idea is return the first n rows back to the master node. So it returns an array of rows, and once we get back this array of rows, we can then introspect it. And that's actually about it for actions. There aren't so many special actions on data frames, and in fact, we're actually often using aggregations more than we're using these actions. Okay, so let's get into joins. What's pretty neat is that joins on data frames are actually pretty similar to those on pair RDDs, with the one major difference that because we don't have key-value pairs anymore, we have to specify which columns we should join on, because with pair RDDs, we were always implicitly joining on keys. Now we have just a table, we have to say which of these columns in the table should behave like the key that we should focus on in our join. So just like in pair RDDs, there are several joins to choose from, and we have to tell Spark which one we want to use. And to do a join, the syntax is just a little bit different. This is, for example, how we do an inner join. So assuming we have 2 data frames, one called df1 and the other called df2, we can do an inner join by saying df1.join and then pass as a parameter df2. Now this here is how we tell Spark SQL which column should behave as keys. So in this case, each of these data frames, this should be 2, both of these should be 2. So in this case, each of these data frames have a column called ID here, and we want to join on these ID columns. So what we do is we select the column via this $sign notation here, that we want to make sure that both of these IDs are equal in our join, and that's it. We just pass the data frame that we want on the right side of our join, as well as which operators should be the keys, essentially. Unlike joins on RDDs, joins in data frames always use the same method named join here. In RDDs, we were using different methods, left outer join, right outer join, to specify the different kinds of joins that we wanted to do. To specify that we want to do a different kind of join than an inner join, all we have to do is pass another parameter. In this case, we say right outer for the right outer join. So we're saying that we want to do a right outer join with this data frame 1 on the left and data frame 2 on the right. We want the IDs again to be our keys essentially in our join, and then we say that we want to do a right outer join as the third parameter here that we pass to join. And that's all there is to it. Now in order to change this join type to anything else, we can pass one of these strings instead of right outer. So if we wanted to change this to a left outer join, we pass this string here, or an outer join, we just say outer, for example. So let's look at an example. Recall this CFF dataset that we saw from earlier in the course. So this was the dataset with the train passengers and the train tickets. And let's try to adapt that to the data frames API. So this is the code for the data that we used in our example. I've adapted it a little bit to put it into a data frame format. So I've made everything case classes. So now we have case classes representing the subscriptions. They're called abo. The ID is the key, which is of type int, and the value is a pair of strings which represent the customer's last name and the type of subscription that they have. So that's the case class abo. And the case class loc, which stands for location, the key is an integer and the value is a string, and this string represents the cities that this customer most often travels to. So assuming that I have a sample data set here, I can create two different data frames, abos df, by calling 2df on the RDDs that I created in the previous example, in the RDD example. So I just used this 2df method that we saw earlier, and now I have a couple of data frames. I have a data frames for the subscriptions called abos df, and I have a data frame for the locations called locations df. And if I call the show method on each of these two data frames, this is what it looks like. So in the case of abos df, I have 3 records, customer 101, 102, 103, 104, and here's their information. So this is the last name, and this is the type of subscription they have. So this person has an abonnement général, which is free train pass all over Switzerland, and these people have what's called a demi-tariff, which is a half-price fare card. Okay, so they get a 50% discount on their train tickets. And in this data set, I have customer numbers and the cities that these customers most frequently travel to. So, for example, customer 101 frequently travels to Bern and Thun, for example. And customer 103 travels quite a bit. They go to Ruhr, St. Gallen, and Zurich. So these are our two data sets. This is what they look like. Now, say we'd like to combine these two data sets such that we have a new data set that contains only customers that both have a subscription and where there exists location info. So how would you do it? I just showed you how to perform joins on data frames. So all you have to do is figure out the right join to use, and then you just have to put it into the shape that I showed you on the previous slide. So what would this program look like? Well, we perform an inner join, of course, because as the problem statement says, we want to combine these two data sets such that we have a resulting data set that contains only customers that have both a subscription and location info for. So we want an inner join. That said, assuming that we have abos df and locations df, all we have to do is call abos df, then we say join locations df, we say, okay, our key is going to be ID here, and that's it. That's all we do. This is by default an inner join if we don't pass a parameter to it specifying the join. So by default, join is an inner join unless we say otherwise. And this is what the resulting dataset looks like. So you wind up with both ID columns in the resulting dataset, but this is correct. Notice that we have all customers, 101, 102, and 103 in here, and not customer 104, because customer 104, if you recall, didn't exist in the locations dataset. So it's correct that customer number 104 is missing in this case, in the inner join case. So let's do another example. Let's assume that the CFF wants to know for which subscribers, so this is the key word here, subscribers, people who have subscriptions like the half fare card, we want to know whether or not we've collected location information for each of these subscribers. So it's possible to have the scenario where maybe somebody has some kind of subscription like a demi-tariff, but they don't use the CFF app, so it's impossible for us to collect location information about them. It would be good to have a data set where we could see situations like these in case we'd like to suggest, for example, that this user should download the mobile app. So if we wanted to join these two datasets together into one that shows which location information is available, which join do we use? What program would we write with data frames to accomplish this task? I'll let you try it for yourself. Well, the answer is that we would choose a left outer join. So we choose a left outer join because we'd like to keep all of the keys in the ABOS DF dataset. So in this case, this is the one where we make sure we have an entry for each one of these elements, which means that our resulting dataset looks like this. So notice that there exists a record on the left side here for every single person in the subscriptions dataset, in the ABOS dataset. And everybody who has a subscription seems to use the mobile app except for customer number 104. This person has null values. So in this case, this is a customer for which we have no location data, but we do have this person in our data set, which is what we wanted. So now we could do a filter on this data set, and we could then know to suggest to user number 104, hey, would you like to download the mobile app? So as expected, customer number 104 has returned because we chose a left outer join. Okay, so now that we're familiar with the data frames API, we're familiar with all of the major operations, we've seen all of the untyped transformations that we care about using, we've seen aggregation and grouping operations, we've seen joins, we've seen actions. Let's revisit that example that we looked at in the first session on Spark SQL. So remember this example about selecting scholarship recipients with a certain data set. In this example, we imagine that we're an organization called Code Award that offers scholarships to programmers who have overcome some kind of adversity. And we have two data sets in this example. We have one full of records represented by this demographic case class, which contains demographic fields about a certain person. So each person has an ID number, they have an age, they have other information associated with them, like the country that they're from or whether or not they served in the military, for example. And the other data set that we had was one containing financial information. So we had many instances of this finance data type here, which also contained an ID and then had financial information such as whether or not this person had debt, whether or not this person had financial dependence or student loans, and also income information. So if we rearrange that data set into data frames, so imagine then we have two data frames full of these two pieces of information. So we have two data frames, one representing this demographic information and another one representing this financial information. One is called demographics DF and the other one is called finances DF. So let's imagine now that our goal is to tally up and select students for a specific scholarship based on some kind of criteria. And if you recall, the criteria that we chose was looking for students that are from Switzerland and who have debt and some financial dependence. This is the criteria that we want to search for in order to figure out how many people are eligible for a certain scholarship. So again, we want to count these up. We want to figure out how many people are eligible for a scholarship with this criteria. How might we implement this program with the data frame API? If you recall, I showed you three different possible solutions to this problem, and I showed you also that the performance was vastly different in each case. So think about what you can do to achieve good performance when solving this problem. Well, that was sort of a trick question, because if you use data frames, the sales point is that all of the optimization should happen automatically for you thanks to the Catalyst query optimizer under the hood. That means that you can just write this query however is most comfortable, and Spark can usually optimize away all the unnecessary operations and make it as fast as possible. So in this case, I would just do the most natural thing, like what we did in solution number 1 when I first showed this example to you. If you recall, in solution number 1, the most natural thing to do was to first do a join and then to filter out the people who didn't meet the criteria that we had established on the previous slide. So our steps were join first and then filter down our data set so that it meets the criteria as a second step, and finally to sum it all up. So looking a little bit more carefully at our code, we take the demographics data frame, we call join, we pass to it the finances data frame, and then we say that we want to choose as keys the IDs from both of these data frames, and finally we're just explicit here about the fact that we want to do an inner join. We want to keep all keys that exist in both data sets, and then we filter out and then we pass through the people in the filter that have debt and they have financial dependence, and we pass through the people who live in Switzerland. And finally, we count the rows in our resulting data frame. So if you recall the performance numbers from the first session in this sequence of sessions about Spark SQL, you'll remember that the first solution, the one where we did join first, filters later, took 5 seconds to complete, whereas the second possibility, which did the filters first and then the join second, took only 1.3 seconds to complete. So the second possibility, where we reordered things and put the filters first and the join second so that we were joining less data, had a 3.6 times performance boost. And there was also a Cartesian product that we could do that was 177 times slower. So how does the data frame solution that we just look at compare to these other three possibilities? Well, this is what it looks like. The data frame examples performance numbers are here. And actually, it's even faster than these other two possibilities here, because the Cartesian product version is 193 times slower than this data frame version here. So the data frame version actually took only 1.24 seconds to complete, as compared to 1.35 seconds for the filter join version and 4.97 seconds for the join filter version, right? And notice I do join filter, it doesn't matter because, so what Spark does under the hood is it reorders these operations to try and get the best performance. And in this case, this is where we're at. It's 4 times faster than this first naive solution here that we did with the join first on a regular RDD. So that's a pretty big difference, isn't it? Imagine that if instead of seconds, these were hours. Okay, so let's briefly cover the sorts of optimizations that Spark does. I'm not going to dive deep into the query optimizer or Tungsten, which is a data encoding framework. I'm just going to give you a general gist of what these things do. So recall that Spark comes with 2 specialized backend components. On the one hand, it comes with Catalyst, which is this query optimizer that I mentioned, and on the other hand, it comes with this thing called Tungsten, which is an off-heap data encoder or serializer. So focusing on Catalyst, remember this map that we saw earlier on about how Spark SQL fits into the whole Spark ecosystem. Spark SQL sits on top of regular Spark and RDDs. It takes in user programs with this relational data frame API, so users are writing this relational code, and ultimately it spits out highly optimized RDDs that are run on regular Spark. And these highly optimized RDDs are arrived at by this Catalyst optimizer here. So on the one hand, we put in relational operations, Catalyst runs, and then we get out on the other end RDDs. So what's important to remember is that Catalyst compiles Spark SQL programs down to an RDD. So if you recall this picture from an earlier session, on the Spark RDD side of things, there's not a lot of structure. Things are just blobs of account objects, for example, or some kind of object. We don't have very much visibility into the structure of this data. And then we have this opaque operation, this opaque function operation that does some kind of operation that we don't know what it is because we can't see inside of it. So there's a lot of ambiguity here, not a lot of structure that we can easily see, which makes it really difficult to aggressively optimize. And on the other side, we have these tables in data frames that are very, very structured, very, very rigid, and we have this set of operations which is also very, very structured and very, very restricted. So we know more about what a user intends to do when they write in this sort of syntax than if they write in this sort of syntax here. So assuming that Catalyst has this information, assuming that it has a full knowledge and understanding of all of the data types in the program, assuming it knows the exact schema of our data, so it knows which fields that we have in our data set, and assuming that it has detailed knowledge of the computations that we would like to do, so assuming that it has these 3 things, there are a number of optimizations that it can do. So one example is reordering operations. So the fact that all of our operations are still lazy and that we now have this structure gives us the ability to analyze and rearrange this DAG of computations or logical operations that the user would like to do before they're actually executed or run on the cluster. So before this DAG of operations runs as an RDD, we can rearrange this stuff real quick. That makes it possible for Catalyst to rearrange and fuse together filter operations and to push all filters as early as possible or to push operations down to the data layer. Pushing filters up enables us to filter data out so we can do expensive operations on less data like we saw with the join examples. Another sort of optimization that Catalyst can do is that it can reduce the amount of data that we must read. So if we have a full knowledge of all data types that are possible to be used in a program, and we know the exact schema of our data, and we know the exact computation that will be done, I know exactly which field might not be used in a computation. This means I can move less data around the network. Because if we recall a few slides back, so if there are numerous fields that we don't need in a computation in one of these blob of objects that exist inside of an RDD, in this case, we don't know that. Because these are blobs of objects that we don't know much about inside of an RDD, there's no way for us to somehow focus on only a small piece of these objects because, like I said earlier, we have no idea what's inside of these things. So that means if we have to do some kind of operation that involves shuffling data over the network or moving some of these objects around, that means we have to serialize this entire thing and send it to another machine, even though we know we don't need most of that. Not knowing the structure of the data could indeed be more expensive later. Also, it wastes memory if we don't need most of this sitting in memory. So Catalyst can narrow down, select, and serialize and send around only relevant columns of our data sets. So we don't have to send the full data set all over the network if we don't need to. Another kind of optimization that Catalyst does is pruning unneeded partitions. So it analyzes the data frame and filter operations to figure out and skip partitions that are unneeded in some computation. So it can know in advance that we don't have to run a certain computation on certain partitions, which of course also saves some time. Of course, there are many more optimizations that Catalyst does, so I hope this gives you a little bit of an intuition about what some of these optimizations actually do. The other backend component that I mentioned earlier is called Tungsten, which is Spark's off-heap data encoder. So since we have a very restricted set of data types that we know literally everything about, that gives Tungsten the ability to provide highly specialized encoders to encode that data. So we know how to serialize these things super efficiently, which is column-based. And I'll talk about why that's great in a moment, but it's also off-heap. So that means it's free from garbage collection overhead. So what I mean by highly specialized data coders is that Tungsten can take schema information, and knowing all of the possible data types that a schema can be built out of, it can super optimally and tightly pack the serialized data into memory. So this means more data can fit into memory, and we can have faster serialization and deserialization, which is a CPU-bound task. So this is a highly optimized, highly specialized, super performant data decoder. The idea is that we keep data serialized in a special format in memory so that we can keep more data in memory and we can access it more quickly. The next feature of Tungsten is that it stores everything in a column-based format. So storing tabular data in a columnar format actually comes from the observation that most operations that are actually done on tables tend to be focused on doing operations on specific columns or attributes of the data set. So when storing data, it's actually more efficient to store data in these columns, grouped in these columns, rather than storing them grouped by these rows. The idea is that it would take more time to look up each individual element somewhere specific in a row than it would to just grab an entire column of data, knowing that we have the entire thing already logically grouped together. And this is actually well known to be most efficient across all kinds of different database systems. So these highly specialized data encoders and decoders, they store everything in a column-based format. And finally, everything is off-heap. So Tungsten knows how to tightly pack all of this data in this columnar format off-heap in memory that it manages itself. So that means that we can avoid garbage collection overhead and garbage collection pauses and things like that. So to summarize, Tungsten lets us put more data in memory and gives us a lot faster access to that data that's stored in memory. So taking together these two systems, Catalyst, the query optimizer on one hand, and Tungsten, the data encoder that's super performant on the other, these two systems offer ways to significantly speed up your jobs, even if you initially write your jobs very efficiently. So it knows how to rearrange these computations, it can store these computations in an efficient format, it can reduce the amount of data that it needs to send over the network because it knows what sorts of patterns of computation you want to do. So Catalyst and Tungsten together are actually what provide these enormous speedups. Well, that said, you might be wondering, well, man, these data frames, they seem too good to be true. Of course, they come with some limitations, so let's talk about some of those now. The first major limitation that you're going to come across, which maybe we haven't shown you in these slides, is that they're untyped. I mentioned that they're untyped, but we really weren't bitten by it. So what happens a lot of the time with these untyped APIs is that code like this will compile even though there doesn't exist a column called state. So this code happily compiles and it runs, but an exception is thrown at some point saying, oh, sorry, nope, I can't find state. I only have columns street, zip, and price. I don't have a column called state. So this can be pretty annoying because errors aren't caught at compile time. Instead, they're caught as exceptions later on. It would be really nice if this error here was caught at compile time like we're already used to, and we're used to the compiler catching us when we make errors like this, so this is a little bit uncomfortable if you come from Scala. It also means that you'll find yourself having to cast elements in rows to certain types that you know exist in the schema because rows aren't typed. So this can be not just annoying because you have exceptions every now and then, but it can also be a little bit verbose and hard to read because you'll find yourself writing row dot as instance of integer, for example, which nobody wants to really do. We want to just talk about specific fields, for example. So things being untyped in data frames can be a little bit annoying sometimes, especially when you come from Scala and you're really used to this nice compiler that helps you out a lot of the time. Another limitation is that we can only use a limited set of data types. So if your data can't be expressed by case classes or products or these standard Spark SQL data types, it might be difficult to ensure that a tungsten encoder exists for your data type. So one example of a situation where using data frames might be problematic is if you have an application which already has some kind of regular Scala class that's super complicated and you want to create a data frame or a data set of this super complicated thing that you already have. In this case, it might be difficult to break it up and represent it as case classes, products, and these SQL data types. So having these limited data types can sometimes be difficult. A big reason that data frames can be difficult to use is that perhaps your data set isn't semi-structured or structured. Perhaps you have an unstructured data set. So in this case, data frames wouldn't be appropriate because you don't know the structure of your data, because you don't have any real structure in your data. You don't have some kind of schema. It's not self-describing like JSON is, or it's not some existing table that already has an existing schema. There is no structure to it. So in these cases, it might be better to just use regular RDDs. In this session, we're going to talk about the last and the newest major Spark API called datasets. To motivate datasets, let's start with an example. Let's say we've just done the following computation on a data frame. And let's just say that our data frame is full of these things called listings here, and each one of these listings represents a home for sale on the market. What we've done with this data is we've calculated the average price of house for sale per zip code. So we've gone through all of these listings, and for each zip code, we've calculated the average price of the homes for sale in that zip code, okay? So that's what the program looks like here. So all we do is we take our listings data frame, we say group by the zip code. So now we have everything collected in groups per zip code. And then finally, for each group, what we do is we call the average function, and we pass to it the name of the price column because we want to calculate the average of that column. So that's the computation that we've done. Great, wonderful, it seems just fine. Now let's do something completely normal. Let's call collect on it to kick off this computation, and let's try to bring back average prices data frame in the form of an array back to the master node. Oops, or oh no, or what was this thing again? I don't remember. I thought I was getting back an array of doubles representing the average prices. What is this row thing here? We've seen them in the last few sessions, but we didn't really look at them very closely. What's in this row thing again? Okay, that's right, because a row is untyped, we have to cast the stuff in the row, but that means that I have to remember the order of the columns in that row so I know which things to cast. So you might ask yourself, okay, well then how many columns was my result again, and what were the types of those things, because now I've got to count them and then index into them and then cast them to the correct types. So here's one attempt. So I have a value called average prices again, and what I do is I take the array of row objects, and for each row I say, okay, the first thing in my row, I'll just cast it to a string because that's something, I don't remember what that was, but I think the second one was the price. Let's just cast that to an integer, and let's see how it works. Nope, got a class cast exception, so that was wrong. Let's try again. Instead of randomly trying different casts, let's look up the API docs for row. Okay, so I can call head on my array of rows, and then once I have a row, apparently there's a method called schema, which gives me the schema, and then I can pretty print it nicely in the form of a tree. Okay, wonderful. So this is my schema. The first element in the row is an integer, and the second element in the row is a double. That's great. Okay, so my average price is this one here. Good to know. Okay, so let's try that again. Hooray, so now I've casted this correctly. So this is an integer, it matches with the first element in the row, and then the second element is double. Wonderful. It all works. It's just really ugly. It's really hard to read. I have no idea what's happening here. And as you can imagine, I could be randomly trying different casts until something works, and I could still be wrong. So this is pretty error prone. But hey, at least it worked. Though wouldn't it be nice if we could have both these wonderful Spark SQL optimizations and actual type safety so I didn't have to do this? I would really much rather select the price in a way like this, where I just call .price on something and it turns out to be all the right type and everything works. This is really inconvenient. So wouldn't it be cool if I could have these Spark SQL optimizations as well as that type safety? Because on data frames, we don't have that type safety. Everything is untyped, remember? Well, that's where datasets come in. They're kind of the holy grail because they combine these nice optimizations with type safety. Okay, maybe that's too extreme of a metaphor, but you get what I mean. Though before I go any further, I have to admit that I've been holding some information from you. It's rather important information, and that is that data frames are actually datasets. So this whole time we've been talking about this thing called a data frame. It's actually really a dataset with type row. So data frames are actually datasets. They're actually the same thing. But okay, what the heck is a dataset then? Well, a dataset can be thought of as a typed distributed collection of data. So kind of in the same way that we think about an RDD. It's a type distributed collection of data. However, datasets have a little bit more than RDDs. So the dataset API actually unifies this data frame API with the RDD API. So let's think back to the last few sessions where we were looking at these very relational operations that looked very different from the operations that we learned in RDDs. Now we can call both sets of these operations on the same Spark distributed collection. And what's even cooler is that we can mix and match these things. So we can have both functional operators and relational operators all intermingling in the same code. And finally, one other major difference between datasets and RDDs is that, like data frames, data sets require structured or semi-structured data. So your data has to have some kind of schema associated with it in order for it to be a dataset. Another way to think of datasets is to think of them as a compromise between RDDs and data frames. So on the one hand, you get more type information with datasets than you did on data frames, but on the other hand, you get more optimizations on datasets than you got on RDDs. So Spark was able to do a few simple optimizations on RDDs, like some pipelining optimizations, but it couldn't do all of the cool stuff that the Catalyst optimizer could do. So datasets get some of those optimizations, while having that nice flexible functional API as well. Let me tell you what I mean by mixing and matching these two APIs. So here's an example of that same computation that we were looking at a few slides back, where we were trying to calculate the average price of all of the homes for sale in different zip codes. So let's assume that we have a data set called listings.ds. It's the same shape as it was before. It's a case class with some fields in it, but the most important field is, of course, the price and the zip code field. And the first thing we do is we can do group by key on it. Remember group by key from RDDs? And then look at this. This is super cool. We're passing a lambda to the group by key function. In this case, what we're doing is we're telling our data frame which one of our columns is going to be our key. So we pass a function to do that. So here we are passing functions. It looks a lot like RDDs again. And the next operation is one of these aggregation operations that we became familiar with on data frames. So here we are calculating the average per key grouping. And then we're telling Spark that the type of that calculation is a double. And the point here is to show you that in the same line of code, I can have both of these different APIs or both of these different ways of thinking about writing code. I can have this nice functional thing here, and then on the next line I can have a very relational expression. So I can mix and match these things however I want. And the types match up because everything is a data set, so it all works out. So just a few more observations to give you a little bit of an intuition about what datasets are all about. So datasets are kind of something in the middle between data frames and RDDs. And importantly, a data frame is just a data set, so they're the same type, which means I have the same operations on both of them. So you can still use all the relational data frames operations that we learned in the previous two sessions now on datasets. So we can just effortlessly carry over the knowledge of that API to this session now and use everything like we've used it before. In addition, datasets add more typed operations that can also be used. So these typed operations include actually relational operations. So we can have both typed and untyped relational operations. And then of course we have these functional transformations, which are all typed as well. So now we have these higher order functions like map, flat map, and filter again, which we didn't really have on plain data frames before they were mixed together with datasets. Datasets are a good choice of abstraction when you want to mix and match functional and relational transformations while still benefiting from some of the optimizations that we saw on data frames. And of course, we can't forget that it's got almost a type-safe API as well. So it's not completely perfectly type-safe, but it's pretty type-safe, let's just say. Okay, so let's get right into how to create these things. So since Spark 2.0, creating datasets is super easy. You can create datasets from data frame. All you gotta do is call 2ds on your data frame, which is a convenience method that creates a new dataset from a data frame. Though note, in order to use these 2ds convenience methods, you need to import this thing called Spark implicits. Another way to create a dataset is to do it using these operations for reading in structured or semi-structured data from file. So if you remember from the last session, we were using these to create data frames. Now if you provide some type information, so in this case we say, okay, this JSON file here is full of person instances. And if we define a case class whose structure and names and types all match up with the structure and schema in this people.json file, then this dataset will be read into memory from file and will be perfectly typed. Until now, we've always had to do some kind of parsing or some kind of casting to massage types in order to get the datasets into memory all with the right types. So this suddenly makes things a lot easier. We can also create a dataset from an RDD by using the same convenience method. And the same even goes from common Scala types. We can just call toDataset on this list, for example, and there you go, we have a new dataset of type string. Before I can dig into some of the operations on data frames, I've got to remind you about these column things here. So recall columns from the data frame sessions. We were always using these column things and there was this syntax for using them. In data sets, because everything is now typed, we now have the notion of typed columns. So if you try to use the same old syntax that we've been using in the previous sessions, you'll get a type error saying, nope, this is a column and I was expecting a typed column. And you might ask, well, okay, how do I create a typed column then? Well, it's pretty easy. You just got to use this as method with the type that your column contains, and then this creates a new typed column. This is going to be important throughout the session because many methods will expect typed columns. Okay, so let's get right into the transformations on datasets. So do you remember how I kept on reminding you that transformations in data frames were called untyped transformations? Well, that's because the dataset API introduces a whole host of typed transformations as well. So you have also typed variants of some of the untyped transformations as well. So on the one hand, we have these untyped transformations, which are the same ones that we learned in the data frame session. And then on the other hand, we have typed transformations. So like I said, these are typed variants of many of the data frame transformations. And then we also have additional transformations like these higher order functions on RDDs that we like so much. So when you look at the datasets API, you're going to find transformations grouped into these two categories, and it's going to be very important. Because if you accidentally use an untyped transformation, then your nice dataset could lose all of its type information, so you're going to have to keep these two things straight in your mind. Because everything is a dataset, because both data frames and datasets are datasets, these APIs are seamlessly integrated. That means you can call a map actually on a data frame, even though I didn't show that to you in the previous session. But when you do call a map on a data frame, you end up getting back a dataset, for example, and of course this can be problematic because if you have no type information, how do you suddenly create type information? So here's an example down here below. Let's say I have a data frame of pairs here, and now I want to do a map on it, and I want to increment all of the digits in the keys here in these key value pairs. But again, I have this ugly thing going on here where I have rows, and I have to cast each element of them if I want to do something with them. So in this case, in order to add 1 to the first digit here in the pairs, I've got to do this ugly cast and then add 1. It's really not clear what I'm doing. So all these two APIs are seamlessly integrated. You could accidentally do things like this and end up with no type information at all when at one point you did have type information. So again, you got to be careful about that. And it's important to note that not every operation that you know from RDDs are available on datasets. And even operations that are available on datasets that you've seen on RDDs, they don't always look 100% the same on datasets as they did in RDDs. So you can't just, without looking at the API docs, start programming RDDs on top of datasets. You're going to get lots of compile errors. So just keep that in mind. So let's go through some of the common type transformations on datasets. All of these look pretty familiar, don't they? So we have a map operation, which takes a function from T to U and returns a new dataset. Just like all the other maps that we're used to. The same is true for flat map, and the same is also true for filter. So filter takes a predicate and it returns the dataset out. Distinct is also the same. Distinct returns a new dataset with all the duplicates removed. So these are all transformations because they return datasets, and they're all typed because they keep this type information around. So I hope these familiar operations make you comfortable, because already with group by key things start getting a little weird again. So coalesce and repartition look the same as what we're used to, but group by key gets a little weird because it has this return type called key value grouped dataset, which is a little strange. How is this a transformation if it doesn't return a dataset, right? Well, we'll see in a moment that ultimately group by key in 2 steps will return a dataset. But we're going to see right now that ultimately group by key does return a new dataset. It just does so with an extra step in the middle. So let's look at grouping operations on datasets now. So if you remember in the last session on data frames, we also had this weird 2-step process. We had these special set of aggregation operations that were meant to be used after we called, in the case of data frames, after we called group by, just regular group by, not group by key. But on datasets, if you call group by key, again, we have a special type full of aggregation operations that can be used on the result of the group by key that was called on dataset. So it's the same 2-step thing that we saw in the last session. In the case of group by key, we return a different type called key value grouped dataset. You're going to have to remember the name of this if you want to look up some of the aggregation operations that you can use. And in this key value grouped dataset thing, there are a number of aggregation operations defined which return datasets. Okay, so how do I actually group and then aggregate on datasets? Well, you call group by key on a dataset, you get back one of these things, and then you just call a method on the results of group by key that you've gotten out of this key value grouped dataset thing here, and it returns a dataset to you. And that's how you do a group and then an aggregate on a dataset. So we'll come back to group by key a little bit later, but let's first talk about some more. So let's talk about this key value group dataset thing here. Let's talk about the aggregation operations that are available to us on that thing after we do a group by key. There are several operations. I'm going to list just a couple. One is called reduce groups. So what this thing does here, it's basically a reduce function, but it does a reduce on the elements of each group. So after the group by key was done, we look at the individual elements that represent the collection of values that have been grouped, and then we do a reduce on that. So that's reduced groups, and that returns a data set when it's done. The next thing is called aggregate, which is this kind of mysterious general aggregation function that we saw in the previous session on data frames. And this can be pretty general. And this aggregation can be pretty general. Also note that it takes as a parameter a typed column rather than a regular column. So this is basically a typed variant of this general aggregation method that we saw in the previous session on data frames. But if you remember, there was also an API on this thing too. Let's have a look at that more closely. So just like in data frames, there was this general aggregation function, and it has this mysterious typed column argument, which I don't know what to do with. If I pass a typed column to it, what does it aggregate? Usually we want to calculate an average or a mean or a standard deviation or something. Well, typically we go to this function object that's defined in the Spark SQL package, and we select one of dozens of different aggregation optimizations. There are many numerical and statistical aggregation operations. There's things like max and min. There's really dozens of different choices for aggregation operations that you can choose out of this function thing here. And then all you do, in this case, let's say we've chosen one called average. So we pass a column name to average, and then we pass this average of the column to the aggregate function. And that's how we get this aggregate where we compute the average in a certain column. Oops, the same thing happened that happened earlier in the session. We forgot that this was supposed to be a typed column, so we can't just pass the column name to the average function here. We have to use this as method to convert our untyped regular column into a typed column. So okay, we just say that this is a double, the parentheses in the wrong location here. Okay, we do this. And everything is all better now. This average function here, which returns a regular untyped column, now has been converted into a typed column. And so the column that we're looking at is now a typed column, and we can compute the typed average on that column. So again, we keep the type information around. So let's go back to this key value group dataset thing again. While normally the operations on these group datasets are aggregations, there are a couple of not really aggregation methods that are also very useful. So one is called map groups, which is very similar to the reduce groups that we saw earlier. And what this method does is that it applies the map function that you pass to it to each group of data. So you could imagine going to the collection of the values, and here what map groups does is it basically does a map on that collection of values. And it returns a new data set as a result. And we have the same thing for flat map. So exactly the same idea, just the flattened version. But okay, I just went through a list of transformations, and there was one super ridiculously important transformation that we learned about on RDDs, and it was nowhere to be found. So what happened to reduce by key? Well, the short answer is that datasets don't have a reduce by key method. But we can do a little challenge right now. I just went through a number of operations on datasets, and I also showed you these grouping operations where you first do something like a group by key, and then you have these aggregation operations that you do on the result of the group by key. So we went through all of these things. And I argue that with some of that information, it should be pretty easy to emulate the semantics of a reduce by key transformation on a specific dataset. Maybe this isn't a completely general reduce by key, but let's say given this dataset here, which is a number of pairs, so we have pairs of type int string, so we have these weird little string snippets and a bunch of integers here as the keys, and your challenge is to try and emulate this call here. So if you pretended that these pairs were in a pair RDD and then you called reduce by key on them, and you passed this function here, my challenge to you is to compute the same logical result using some of the operations that I've just showed you, but to do it instead on a data set. I really want you to try this on your own, so I'm going to give you a moment to try it yourself. Of course, there are several possible solutions, but this is the one I've chosen right now. So remember that now this key values thing has type dataset int string, and now we call group by key on it. And this function that we pass to group by key basically tells group by key which column or attribute in the dataset should be viewed as the key. So since the elements of this dataset are a pair, and we know that we want to use the number here, which appears to be some kind of ID as the key, what we do is we select the first element of the pair here. And so what this does is it does group by key on the integers here. And remember, now we have back one of these strange types, these key value grouped dataset things, right? So it's not a dataset what I got back, and now I've got to do something else on it to make it a dataset. So I'm going to use the map group function here. And if you recall, what this does is it takes a function from a key and a value to some other type. So this k is an integer, and this vs here is a collection of strings that represent the groups of the values. So what I'm going to do, because on an RDD reduced by key, when having elements like this, it first groups by the indices, and then it reduces on the values. And if you remember, our reduce function and reduce by key was a simple concatenation, so we were concatenating all these pieces of strings together. So I'd like to do the same thing in this map groups function. So I again return a key value pair, where I keep the key as it is, and then I just take this collection of values and I do a fold on it and concatenate all the strings together. So that's how conceptually, with this specific dataset, I can basically emulate what a reduce by key operation does. And just like on data frames, if I call show on the results, I get now a visualized table here. So here it is. These are my keys and these are my values. And look, there's something interesting happening here. Suddenly, this jumbled stuff makes a little bit of sense. Let's sort that actually another time to make this get into a better order. So if we sort the records now by ID number, where we put 1, 2, and 3 in the right order, then we have a cute little, this is a secret message, actually, from all of these pieces. So that's how we know we did it right. That's the intended result. So while that might have worked, there's actually a problem with this approach. The only issue is that the API doc gives us a big hint of the danger of using this map groups function. So map groups does not support partial aggregation, and as a result requires shuffling all of the data in the dataset, which is of course extremely expensive, and we don't want to do that, right? So if an application intends to perform an aggregation over each key, which is exactly what we're doing, it's actually best to use something else. It's best to use the reduce function or to use this thing called an aggregator. Okay, so mental note, don't use this map group things unless you really have to. But okay, let's follow the advice of the docs. Let's try doing it with a reduce function. How would you do that? Remember, there was a reduce function that we saw in the key value grouped dataset class. In fact, it's called reduce groups. So conceptually, it's a little bit similar to map groups because it's focusing on the grouped values, and instead this is doing a reduce on the group values. So all we got to do with the result of our group by key is call map values, because reduce groups has to work on individual strings and not pairs. So map values basically goes and takes out all of the strings here and passes them down the line to reduce groups, which then concatenates all of those strings. And voila, that works. I could print out the dataset and it would be exactly the same thing. But the docs also suggested this weird aggregator thing here. What is that thing? So an aggregator is a class that helps you generically aggregate data. So you'll notice that some of the aggregation functions that you'll be able to choose from are very specialized, and you don't have the ability to create your own aggregation function. So this aggregation class here is supposed to let you do that. And actually, if you think about it, it's kind of like the aggregate method that we saw in RDDs, because it will give you a couple of functions that would look just like the two functions and the zero that we would pass to the aggregate method on RDDs. First things first, you got to know where this thing is. It's inside of Spark SQL expressions, so you're going to have to import this aggregator thing to use it. Okay, but what is this aggregator class? The first thing you might notice is that it has 3 types. A type in, a type buff, and a type out. So if you think about this aggregate method that we saw before on RDDs, it allowed us to change the types and to do things in parallel. So we broke up our computation into a couple of functions so it was possible to compute some pieces in parallel and then to combine them all later. So this is exactly what this class aggregator is going to do. And in this case, the in type is actually the input type to the aggregator. So this would be the type that we got out of the group by key function that we saw earlier. Buff is the intermediate type during aggregation, so if we have to change the type to something else in the middle of this computation, we have this buff type that we can change it to. And finally, out is the type that comes out of the aggregation if we want to change the type. And all of these types can be different. And this is what an aggregator looks like. So all we got to do is create a new aggregator here. We've got to define what these types are, and then we have to implement these peculiar methods here. So this should be pretty clear what it does. This is the initial value of the aggregation. So this is like the 0 that we pass to fold left, for example. So this is the initial value. Now, reduce and merge, these are like the 2 functions that we pass to the aggregate method on RDD, where the reduce method adds an element to the running total, and the merge method is what merges these independently computed aggregations together. And finally, this finish method basically gives us a chance to change the type one more time before we return the value of the aggregation. So despite how scary it looks, it's actually not so hard once you get the hang of it, once you get the hang of this structure and you look at things in terms of these input, buffer, and output types, and you just kind of keep this schema in your mind. So let's try to emulate that reduce by key on an earlier slide with one of these aggregators. Let's create our own aggregator. So again, we assume the same key values data set here, and we start by looking at the types in these things. We can break this into steps. The first step is determining what these 3 parameter types should be to the aggregator. Remember, input, buffer, and output. So what's the input type? Well, remember, the input type was what came out of the group by key method. So in this case, it will be a pair of int string. So we know that this is going to be a pair of int string. And we know that the output type is going to be a string. Since these are pretty simple data types, the buffer value can also be a string, because we're just going to be concatenating strings together inside of this aggregator. Okay, so first step is complete. Our input type is pair int string, and then our buffer type is string, and our output type is string. Great. Now we have to fill in the rest of the types. That's completely easy to do if you go back 2 slides. And here we have a template of where we can plug in these different types. So actually everything is going to be a string because buff and out are all strings, and the only thing that's not a string is this input type, which is a pair. So we just mechanically plug these types in. Now we have to figure out what these methods should actually each do. The 0, or the initial value, is pretty straightforward. We're going to be concatenating and building up a string, so this is definitely going to be an empty string. Okay, cool. So the next method that we have to figure out what to do with is this reduce method here. And actually these types that we already plugged in give it away. So this is the function where we have to somehow take the string out of this pair and concatenate it with this other string here. So that's pretty straightforward. We just take B, we pull out the string out of A, and we concatenate them together. Now this is a string. And this merge function, since we already have a string, we just want to merge together 2 strings. So we just do another set of string concatenation, and since, again, we need to return a string, we just return R without doing anything to it, and that's it. There's our aggregator. The last thing that we do is we convert it to a column, so there's this 2-column method here. Because remember, if we're going to pass it to an aggregation method, it needs to be of type column. So here we go. We pass our aggregator, which we named string concat. We pass it to this aggregation function, and of course we make it a typed column because this is just a regular column. We do as string because the result is of type string, and that's it. Voila, we have our aggregator. Oops, except we don't. We got a compile error. So there was something missing. It might be hard to read, but what it says here is that there are 2 unimplemented members, one called buffer encoder and one called output encoder, and they're of type encoder. Okay, what's an encoder? Well, believe it or not, we heard about these things in passing during the data frame session. Encoders are the things that convert your data between these JVM objects that you're used to operating on and this highly specialized internal tabular representation that Spark SQL operates on. And I mentioned this at the very beginning of the session, but these encoder things, these things are required by datasets. So every dataset has encoders to go along with it. And these encoder things are extremely specialized, optimized code generators that generate custom bytecode for serialization and deserialization of your data, and they do it all in this special internal tabular representation that we heard about. And this special representation is Spark's internal tungsten binary format, which allows these operations to happen on already serialized data, which actually greatly improves the memory utilization, so we can put more stuff in memory and we can not have to unpack so much of it, basically. Well, that's the context for these things, but since these encoder things are all about serialization, you might ask, well, why isn't Java or Cryo good enough? Well, for a couple of reasons. It starts with the fact that we have a very limited set of data types, which we have encoders defined for, so all of the primitives and things that are case classes, all of the Spark SQL core data types, these things that we already understand super well, we can make sure that there's always a super optimal encoder available for these core data types. So that gives us an optimization opportunity. But perhaps most importantly is the fact that these encoder things actually contain the schema information. So they're not just serializers and deserializers, they're serializers and deserializers that make all of their decisions based on this schema information. So they know in advance the structure of the data that they're serializing and deserializing. This thing here basically is what enables Tungsten to do all of the optimizations that it does. Since Spark already understands the structure of the data that's stored in its datasets, it can actually create a more optimal layout in memory when caching these datasets. So this is kind of the magic that Tungsten does. So this is where we get this great memory utilization from. And that goes without saying that it uses significantly less memory than Cryo and Java because we have this extremely compact special format that we're keeping this stuff in memory, which is a lot smaller than Cryo and Java. And it's actually even 10 times faster than Cryo, which is one of the fastest industrial serializers that are around. So these encoder things all tie back to this Tungsten component that does all of these optimizations in memory and with the representation of the data that we're operating on. And I told you that there's an encoder for every dataset, so every dataset has encoders for its types. But we've been creating datasets all over the place, and we've never seen these encoder things before. Well, that's because the most often used way to introduce an encoder is to do it automatically via implicits from this Spark session object. But as we saw, sometimes we run into the situation where we're required to explicitly pass an encoder to something. And for that, Spark SQL actually has an object called encoders in the SQL package, which contains a big selection of methods for creating encoders from Scala primitive types and products and things like that. So here are three kinds of encoders. So there's encoders for int, long, string, etc., for primitives that are nullable, right, which isn't the case for all of Scala's primitives. And then there are methods that create encoders for the Scala primitives. So Scala int, Scala long, Scala byte, etc., the list goes on. And finally, there are methods that create product or tuple encoders, because sometimes we're building up complex types via case classes. So here are some examples of how one might go about creating an encoder. So you just call this the name of this package object, then you invoke this method, for example, Scala int, and you get back an encoder of type integer, of the Scala integer. And the same goes for string or for product, for example, as well, if we have a case class type like person here. So that was a quick introduction to encoders. So let's finish up the implementation of this aggregator. All we got to do is choose the types for these encoders and then look up the right methods to use in the encoders object. Well, that's pretty simple because buff and out are both strings, as we saw before. So all we need is to get the string encoders out of this encoders object. And voila, that's it. So I've implemented my encoders. So now all I got to do is take this custom string concat aggregator column thing here. I've got to make it a typed column, and then I got to pass it to this aggregator method that we saw before. And that's it. Here's the result. Just as we expected. So that was a whirlwind tour of actually some of the more advanced ways one could go about grouping and aggregating data. So now you know how to make your own custom aggregators in case you don't find an aggregator that you need in the Spark API. So I hope this slide is refreshing. So we're changing directions a little bit. We saw transformations and then grouping and aggregating on datasets. Now let's look at actions on datasets, and you'll be very happy to notice that these actions are all exactly the same as the actions that we've seen on RDDs and on data frames. There's nothing different about them, in fact. Like data frames, we have a show method, and all of the other methods, like for each or count or collect, they're all the same. So I hope this is reassuring, something super familiar after digging into those aggregator things a few slides back. Everything is as expected with actions. Phew, so that's an introduction to datasets. So the general gist is that they have the same operations available to them that data frames have available to them, in addition to more of these higher order functions like map, flat map, and filter that we liked from RDDs. And of course they're also mostly type safe, which is really nice if you've ever had to wrangle with a bunch of exceptions that were thrown by the analyzer when having to deal with data frames being untyped. So at this point, I've given you three APIs, three big main different APIs. One is called datasets, another one is called data frames, and then we spent a bunch of time on these things called RDDs. And so your head must be spinning right now, and you must be like, well, when on earth would I use one or the other one of these things? So I've prepared a simple criteria for when you might be interested in choosing one abstraction over another. So the first thing to remember is that RDDs are really the core abstraction that everything else is built on top of. So this is becoming almost like bytecode to Spark because they're building all of these richer abstractions on top of these RDD things, and they're generating RDDs. So datasets and data frames, we go through these optimizers, and in the end we have RDDs that we're actually running. So we write code in datasets, and in the end what Spark is running is an RDD, right? So you can think of RDDs as a little bit more low level and totally free form. It's up to you to do your own optimizations on them, and we learned that the hard way in several sessions earlier in the course, that it's super hard sometimes to know exactly what these things are doing under the covers. So RDDs are a good choice in the situation that you have data that won't fit for some reason into a dataset or a data frame, or you have to super fine-tune and manage low-level details of your RDD computations. You can't just trust the optimizers to do it for you. Or finally, if you have some kind of complex data type that cannot be represented or serialized with these encoder things, which is a real possibility, encoders can't yet nicely deal with user-defined data types. So these are situations when an RDD might be necessary. Otherwise, you might often want to reach for a dataset or a data frame, especially if you're going to read in some kind of structured data format like JSON or XML. You can just use that wonderful read operation to read in a JSON file and map it to a case class. Datasets do that really well for you. So this is a situation where kind of getting data in suddenly becomes really easy with things like datasets and even data frames. So when you have structured or semi-structured data, it's often really nice to go with a data frame or a dataset. Data frames are generally a good choice when you want to rely as much as possible on these optimization components that Spark provides. So if you really want to just write code, not think about what it does, and have something else optimize it for you and generally trust that it's going to be okay, data frames are a good choice if you can deal with the fact that they're not typed. But like I said in the very beginning of this session, datasets are a really nice compromise because maybe they're not as performant as these data frames here, but they still have good performance. They still have some optimization done on them. So datasets are a good choice when you want type safety, you want to work with functional APIs, you have structured or semi-structured data, and good performance is good enough. It doesn't have to be the best. So it's up to you to decide which one you prefer based on the data that you have and the sort of computation that you want to do. Perhaps it's easier to do it with sort of functional APIs and types, or maybe it's better to do it totally with relational operations. It really depends on the problem that you're trying to solve. But this is a good set of criteria to help you make that decision. So before I wrap up this session on datasets, I wanted to just run through some of the limitations of datasets that might not have been completely obvious. So one thing that I alluded to but didn't quite explain is that datasets don't get all of the optimizations that data frames get. And I gave you some hints throughout the course about why that's the case. I talked many times about structure and how giving more structure helps optimization. To be a little bit more concrete, relational operations tend to be more performant and able to be easily optimized by the Catalyst Query Optimizer, because with information about the structure of the data and the structure of the computations, then the Catalyst Optimizer knows it can access only the fields that are involved in, say, for example, a filter. So if we focus on a filter that looked like this, because we have the structure of the data, we have the structure of the computation, we can see into everything. We can see the data, we can see the computation. Then Spark's Optimizer can know that it only has to access certain fields involved in that filter and skip over lots of other ones without actually having to instantiate the entire data type. So that's why Catalyst is good at optimizing this case. Catalyst actually cannot optimize functional filter operations or functional operations that include passing around function literals or lambdas. And the reason why is because when you pass a function to Spark, all Spark can know when you pass it this function blob is that you need an entire record serialized, so an entire object serialized, and you need to apply this function to it, and you don't know what's in it. So you need to create an object and then apply this function to this thing, and you don't know what's inside either of these two things, which requires Spark to do potentially more work than it has to in order to do the baseline minimum that it should have to do. Because Spark just can't see into lambda functions. It has no idea what they're doing. So Catalyst can't do very much for operations that involve passing around these function literals. And of course, you don't miss out on every possible optimization. You just miss out on some important ones. So the key takeaway here is that when you use datasets with higher-order functions like map, you end up missing out on many optimizations that Catalyst does for data frames. So that's something to keep in mind. This is why sometimes datasets are slower than data frames. However, that doesn't mean that every operation on a data frame doesn't get these wonderful optimizations from Catalyst. Or if you choose relational operations like select or the relational filters or any of these operations, then you get all of Catalyst optimizations on datasets. So it really depends on the operations that you're doing on datasets, whether or not you get the full sort of suite of optimizations that are available. Finally, that's not to say that datasets that use things like map operations don't get any optimizations, they still have tungsten always running under the hood, storing and organizing data in highly efficient and optimized ways, which of course can still result in large speedups over regular RDDs. So that's not nothing. So you basically just lose out a little bit on Catalyst if you use high order functions, but you still get all the benefits of tungsten. So I hope that gives you just a little bit of intuition about the capabilities that Spark has to optimize operations on datasets. And the two last limitations, which are also shared by data frames, is the fact that the number of data types are limited, so you end up having to express all of your data with case classes and these standard Spark SQL data types, these primitive data types. If you can't do that, then it might be difficult to ensure that there's a tungsten encoder that exists for you. So this could be also a problem. You can't just put any data type ever into Spark. And finally, there's that point about semi-structured and structured data. Sometimes there are just data sets that are completely unstructured. You have no schema, they're not self-describing, there's no way to sort of programmatically guess the structure of these data sets. And in those cases, data sets might not be a good fit because it might be really difficult to shuffle that data around and put it into some format that's comfortable for data sets to deal with. It might be easier to just parse the bits and pieces that you need in with regular Spark RDDs.